Prueba de audio, check. Hello.
Sí, sí. Hola, hola. Okay. And now, okay, that's your presentation. Nice. Let's gonna check if everything works. Yes. Okay. Okay. So I'm gonna, if you want, yeah, you can. Yeah. Although you can go downstairs and then go upstairs when I present you, or you can. Which one? What? I don't know. Yeah. ¿Cuándo arranca? ¿Arrancamos? Welcome everyone. Welcome to the second day of KHIPU. I hope you have had an amazing day yesterday and you have charged your batteries for the day that we are going to have today. Now I'm going to present to you Leo Sampaio. Leo is a professor at the University of Sao Paulo, USP. Leo specializes in the area of computer vision, AI for images, and during her doctorate at USP, Leo worked on the subtopics of representation learning and content-based image search, specializing in the use of transformer type architectures. She was a postdoctoral researcher at the State University at Campinas, where she began working with the Araceli project, which is in progress, working on the automatic recognition of sensitive content under low data protocols and domain generalization. So please, let's gonna welcome Leo.
Okay, it's working. So I was already introduced. I'm Leo, and I'll be talking to you about computer vision. So we'll be going over how I need to study contrast so that you can read the white text. No, I'm kidding. So we'll be going over the classic pipeline for image processing and computer vision. And we'll talk about how that classic pipeline transforms into what we have today, and how we go in cycles of a sort. Then I'll introduce you to the concept of CNNs, convolutional neural networks. We'll talk also about vision transformers, so you'll see a little bit more about transformers today. And then I'll talk about what I believe will be the future, or is becoming the future of computer vision, which is using contrastive learning instead of classification only to do many tasks. Okay? Good. So we start with the common pipeline. So maybe you have seen this already many times if you have been studying machine learning. But this is the idea that when we do machine learning, we want to sample the universe, the world that we have, this continuous and infinite space of information. And we use sensors to do that. So we use a camera, we use a microphone to capture information from the real world. And that's the sampling step. And then we pre-process that data, prepare it on a computer to do other stuff. And on the classic pipeline, what we would do is design features to be extracted from these data, right? So we would think about what we want to solve, a classification problem, segmentation problem, and then do, from the ground up, design these feature extraction methods so that we can represent in a computer the ideas of color, of shape, of rate of change on a signal, on an image, that kind of stuff. And then, only then, we would use an algorithm to train a classifier and have our final results. So this classic pipeline is stayed in place for a long time. So yesterday we talked on the lectures a little bit about the AI winter. And a lot of this AI winter includes this pipeline. So what happens is classifiers and machine learning kept developing. And they kept getting very good. And at some point, we had almost perfect classifiers or classifying algorithms. But these algorithms, they depended on how we represented the data always. So research moved into the field of creating new feature extraction methods. And we focused on that for like 20 years, from the early 1990s to the 2010s. We focused on improving those classifiers and improving these feature extraction methods. So just to give an example of how this used to work, we would take a picture. The example here is we're taking a picture of an apple. The apple would have, when we sample the image, we would have the 3 channels, RGB, and probably the red channel would have more information because the apple is red, or this apple is red. Then we would do some pre-processing, do some feature extraction. On this example, I chose to extract the color only. So you can think of this as extracting a single number. So the average of all the pixels, this pixel is red. So we have a single number that tells us that this object that we took a picture of is red. And then I'm going to go through a simple perceptual network that you saw yesterday. You saw the formulation, how it works. And we're going to use only this information that we chose manually to extract to decide whether this is an apple or something else. And you already know how to train something like this. So this is a perceptron. So we have a single input, single output. We would initialize the weights, and we would find the optimal W and weights and biases based on the loss function. This is the same idea you saw yesterday. So this is just showing a common loss function that we would use, and we would adjust the weights using gradient descents so that when we have another class that's not an apple, an orange, for example, it would eventually, during the training process, be mapped into the correct space on our loss function. Okay? Everyone good with that? Okay. This is a simple perceptual network, but when we're working with other features, we're not going to extract a single feature. We're going to want to have a multi-layer network, probably, to have hierarchical information being extracted. We're going to want to have multiple inputs. So if you're extracting, for example, the information about the rate of change in an image that tells you about the texture and the shapes, you would have a large vector that describes how the rate of change is behaving along the image. You would have like 256 or 512 dimensions going into this network, and things start getting big. And we would also like to have more than one output because we're not predicting only binary classifications. And things get big very fast, right? And we will have a bunch of weights. These are just an example of a very, very tiny network with only one input, one number, and we already have a bunch of weights to keep track of. And what we did find out eventually, around the 2010s with the AlexNet mostly, we found out, well, AlexNet made things work with the technology that we had. CNNs were not invented in 2012. They were invented in 1998. But we found out that it would be a good idea to mix the task that we want to perform with the feature extraction process, right? So the way we got to that point is by looking at what we had for feature extraction. So we had color, shape, regions, domain transformations, and we had specific descriptors. So the one I like to mention a lot is the histogram of oriented gradients. To do this one, what you would do is extract the gradients of an image and then look at the direction of the gradients over the whole image and do a histogram of those gradients. And people found out through research that this information was very useful for identifying if there were people in an image. This was all very manual, a very manual process, and it takes years to figure out what kind of extraction works for each different task. And I mentioned HOG because HOG depends on the shape extractor, the Sobel filter, that is actually a computation of an image gradient, as you see. So the interesting thing about the Sobel filters and other shape filters is that they are based on the concept of convolution. So, yes, okay. So what is a convolution? It's a binary mathematical operation. It is defined for n-dimensional tensors. So it works in 1D, and it works in 2D as well. This is what we want. This is the symbol. No one uses the symbol anymore, but you will find it being used in books. So if you see this symbol again, that's the one. And that's the formulation for the discrete convolution. So basically what's happening here, we have the definition of a continuous convolution as a signal being slided over another signal, and we are multiplying one signal by the other, and you have a filtered signal as the outputs. When we're looking at a discrete version, we have a similar thing. This is the best GIF on the entire internet. It's from Wikipedia, and no one credits the author, and actually the author did this for Wikipedia only. That's the only place you'll find this GIF. And it's very good because it describes very well what's happening. So we have two matrices. We're thinking image processing, so we have one big matrix that will be our image. We have a tiny one that we're going to call a kernel or a filter. And we're sliding this filter over our matrix and just multiplying where the values fall on top of each other. And then we're summing them up. So we have over there, our filter is 5 with -1 at the corners. So it will multiply the center by 5 and the corners around it by -1. We'll get a sum. And the effect that we get here, you'll see an example, is a high-pass filter, a filter that keeps information where the rate of change in an image is very high. You'll see it will make a little more sense in a bit. So I'll go with the operation. OK. So the thing about convolution is that convolution is traditionally used to filter images, to transform images or signals, if we're talking one dimension, into another image or another signal and extracting useful information. So I told you about the Sobel operator. Let's see if that works. You can see that. OK. So I talked about the Sobel operator. And this is a Sobel left Sobel filter. And what it's doing is it's keeping information, it's making it white, only where the image changes fast from left to right? So we have a simple image. It's very simple. It's just the apple. The background is white, which means that as the filter slides along, we get all the white parts do not have a response and activation for that filter. But when we get to a border, and that border is aligned to the left, we are going to get white values. So we are extracting the gradient of the image, and that's what we use to build like a histogram of gradients, which was a very well-used feature extraction method. So that means that a convolution is one of the ways that we extract information. And it is defined by matrices, by these filters. And the idea of a convolutional neural network then is, what if instead of us extracting this information manually, we just let the gradient descent process and everything that happens when we're training a neural network actually define those filters as well, right? So we're entering into what are CNNs. And they are neural networks, as usual, but instead of having a simple weight being multiplied by the values, what we have now are convolutions. So instead of doing multiplication, we do convolutions. Instead of having inputs that are single numbers or vectors, and each number of the vector is considered for one connection, we actually make connections between collections of matrices, right? So we have as input our images, and now our entire images, and not information pre-extracted from those images. And we have, for our neurons, we have our filters. Instead of just a single weight, we have a whole matrix of, that makes a filter. And we have as output another collection of matrices. So the way this works is that we get our filter, and a filter is made of one kernel, so one of these matrices, for each of the input channels that we have. I have to press for each animation to go. And no, that one was by itself. And when we, oh, sorry, but I'll not come back. So we have one kernel for each of the channels in our input matrices. So if we're starting at the start of the network, we have an image, it's a photograph, so it has 3 channels, one for each color. So we're going to have, for each of our filters, we're going to have 3 kernels, one for each of the channels. We're going to compute a convolution between these kernels and our matrices, and we're going to sum the results together of those 3 convolutions, or those n convolutions, depending on the number of channels. And then we do that for each of our neurons. We really went away from the biological inspirations here. Now, there is a biological inspiration for convolution, but really, those are not neurons anymore. So for each of our neurons, we're going to have those one kernel for each channel, and we're going to compute and sum. And we're going to have, as a result, another pile of matrices that we call now, after the first step, we start calling them feature maps, because we're extracting features automatically. Or we're learning to extract features that would be better for the task at hand. Okay? Sounds good? So just to recap with the shapes, every time you're going to implement a convolutional neural network, or any network for images for that matter, you're going to be looking at the shapes a lot, because problems will happen when you try to implement these. The shapes will not match, and then you're going to look at them and try to figure out what they should be and how you're going to fix them to be that way, okay? So we have as inputs, we have our images. So they have a width, they have a height, and they have a number of channels. I'm talking only about RGB images, but if you have magical images, they would have a different number of channels. And a single kernel, it will be a k by k kernel. And a filter is composed of the number of kernels that would be compatible with the number of input channels on our image. And by the end, you have a filter collection. That's the number of neurons that we have on each of our layers. And we have, as a result, our output feature maps that, on this example, we're keeping the width and the height, But if you think about it, when we apply a convolution, actually we lose a little bit of information because we have to fit a matrix on top of our image, right? So we can't center our filters on the corner of the image unless we do some kind of padding. So I'm considering padding was done here, and we kept the width and the height of the images intact. Okay? And then, instead of having this many weights, you're going to think that when we do a convolution, we're going to have more weights, because now each connection we have a 3x3 matrix instead of a single weight. But I want you to think about how we're not extracting features beforehand now anymore. So when we get inputs to our network, it's going to be our images. And our images, they're not tiny. You know, usually you extract features and you have, I don't know, at maximum 1024 dimensional vector. But an image, 256 by 256 will have 65,000 pixels and 3 channels, so that times 3. And 256 by 256 is a standard value that we use for image processing. But that's a very tiny image. Usually you take pictures with your phones and they're like 12 megapixels. Those are 12 million pixels. You know, we make them very small to do image processing and computer vision. And still we can extract a lot of information. Don't try to run any neural network with 12 billion pixels. This is not going to go well, okay? But anyway, what I was talking about is that convolution helps save on the number of weights, because now we have a huge input. We have like 65,000 pixels as inputs, but we can keep the number of neurons about the same as we would keep on a perceptron or a multi-layer perceptron network. And we can, and the multiplication, the number of weights does not go up exponentially, right? Because we are looking at the inputs not as a single number anymore, but as the entire matrix. So the entire matrix will be convolved with each of those features. So if we have 256 neurons and we have 3 channels, the channels is where you do the multiplication and not the actual number of pixels, right? Because we're defining the number of filters based on the number of channels, and we are using the same weights to go over the entire inputs, the entire image. So we're saving a lot of space. Instead of having to have all the connections between 65,000 and 256 on the other side, now we have connections between 3 channels and 256 channels on the other side. So we're saving a lot of space when we have a huge input, such as an image. Okay? Very good. I'll not, okay, it's fine to add it on this slide. The other thing to mention, it's important when we talk about transformers, is that by the design that we have on a convolutional neural network, it seems like it's especially tailored to work with images, because we have a matrix that gives importance to pixels that are close to each other. So this is called an inductive bias, and this helps because usually when we think of pictures, we think, oh, okay, the pixels that are close to each other, they make sense to be processed together, and that's what we're doing when we do a convolutional neural network. And the other thing is that when you move an image around, the filter will slide over the image anyway. So that means it is translation invariant for the most part. So we have translation invariance, and we have the inductive bias that is especially good for images. And that helps us train models that are good for computer vision tasks. I'm going to mention some, but the most famous one is, of course, image classification. And in the context of image classification, now I'm going to talk about the history of how we scaled deep learning in general, but especially convolutional neural networks. So everything started in 2011, at least 11, I think it's 12, with the publication of AlexNet, and it was a turning point. Oh, I'm moving the microphone. Sorry. Okay. Is that better? I think, okay. Sorry. So the publication of AlexNet made a big difference because even though we did have CNNs, as was mentioned yesterday, we didn't have CNNs that could run on our computers on a scale that was good enough to solve problems, right? So the great discovery here is mostly engineering a network, convolutional neural network, to work with the hardware that we had in 2012. That was mostly the GPUs that we had. So when they developed this model, no frameworks existed. So they wrote their own CUDA code to make everything work. It was probably very painful, but they made it work, and they showed the potential for using those graphical processing units to do convolutions, to do matrix multiplications, to do research, and that made all the potential more clear to the research community. So the contributions beyond their original CNN were that they started using the rectified linear units as an activation function. This is a simpler activation function. I think you saw an example of it yesterday. So basically, if it's below 0, it's 0. If it's above 0, it's the value itself. It's a linear, it's an identity function. Why does that make sense? Well, it has the simplest gradient of all, right? So if it's below 0, there is no gradient. And if it is positive, the gradient is just the slope that is fixed. You can change the slope on some values, but the slope is fixed. So it makes the computation simpler, and it still works because it's still a nonlinear function. Because it excludes half of the space, the continuous space, so it is nonlinear. A combination of values works very well, and they were first used on CNNs on AlexNet. They also started using max pooling. So the pooling operation, it makes the matrices smaller. The point of doing that is that if we keep all the information all the time, we are always processing those neighborhoods that are 3 by 3 or 7 or 5 by 5 or 7 by 7. And when we're going over the layers of the network, we want to look at more pixels at the same time. So the idea of doing pooling is that we downsample our feature maps, basically. And then a 3 by 3 matrix that was seeing a space in the original image is now seeing more of that space because the image or the feature map is smaller now. Good? And the difference here, pooling was already on the original CNN, but the difference of max pooling is that they found out that instead of doing the average downsampling, so just doing the average of the regions of the image to the downsampling, if you got the maximum value, that would be better for doing discriminative learning, so for doing classification, basically, because it's going to keep the highest activations within our feature maps. And finally, they also introduced the concept of grouped convolutions that we don't really do anymore, but it was a concession to have some of the filters in one GPU and some of the filters in another GPU, because in 2012, the GPUs had very little virtual video memory, and you couldn't fit the entire AlexNet on a single GPU, which I know if you're working with that, it sounds absurd. So they had to break the tiny network that is AlexNet into 2 of those GPUs. OK, after that, things started to grow almost uncontrollably. So VGG came next, and they brought this idea of having simpler blocks within our convolutional neural network. So they would do a block of 3 by 3 kernels, a bunch of them, and then they would do a max pooling, and then do another block of 3 by 3 kernels. So keeping the kernels very similar and doing these downsampling operations in small blocks so that we can build bigger networks easier. We have like a protocol for building convolutional neural network architectures. And those are the blocks. After that, people wanted to have more layers. And what happens when you have a very deep network, when you're going to do gradient descent, you're going to compute the backpropagation of these gradients over the entire network. So you'll have to come back all of the layers. And what happens is that the first layer has very little influence on your output. So the gradient getting there becomes 0 very quickly. So the idea of ResNet, or residual networks, is that we add skip connections so that the gradient can keep flowing to the back to the start of our convolutional neural network. And that way, we can increase the CNN to many, many, many layers. And each of those layers came with improved accuracy. We found out later that these gains, they have diminishing returns. We can't keep going deeper and deeper because we have other dimensions to increase. So on this paper, they found out that we can scale the width, or the number of neurons, together with depth, and we have a better yield of performance. And in this paper, mobile nets, they found that using depth-wise separable convolution, that's a special kind of convolution. You can come talk to me later too. I can explain how they work. And they can also scale width and resolution and get better gains than doing just depth. And finally, scaling resolution. So this is another paper showing that scaling resolution also had a significant impact. And this is just to show all the authors. There are many authors. And finally, we have efficient nets, and that's probably what we're going to work with. When you work with CNNs, you're going to start with something like a ResNet derivative or an efficient net, because they created a protocol to scale a network to any size, basically. So they have a very tiny one, and then they have an equation that tells you how many layers you have to add at each step to get a bigger and bigger one. OK. So this is just the conclusions from all the papers that I was talking about. And some of the applications that came with CNNs. So this is faster as CNN. I'm just doing a bit of a highlight reel of advancements. So we started doing much, much better at object detection. That was very hard to do with manually extracted features. We also were able to do much better at general image segmentation. We were able to do image segmentation with very well-behaved images using manual feature extraction. But now we can do it with more general tasks, such as those two. There's a cat and a dog being segmented here. And we also started to having generative models for images that we didn't have before. We're starting with the generative adversarial networks that are not currently the state of the art, but that's where things started for image generation as well. And image generation is interesting because to this day, even though we have transformers for images, convolutional neural networks are still used to generate images, even if they're not GANs, as they were at the start. OK, also, this is another one. That is human pose estimation. That was also a task that we thought would never be solved, and then came in large convolutional neural networks, and we got that working as well. So our common pipeline, then, I'm going to mention that it's not only used for classification, it was used for all of those tasks. And just so we can keep that idea of a cycle of research going over and over, I'm going to mention that during the time that the common pipeline was very common, the retrieval problem, it was solved mostly using bag of visual words. So this is like a preparation for you so that when we get to transformers, you see the cycle going around, okay? So the idea of bag of visual words is that we would do feature extraction as usual, manually. We would invent features for things that we want to search for. And then we would cluster the patches of the images based on the features we extracted, right? So when we got to the search step, we would be comparing how many of those patches the images we have as a query have in common with the images we have in a database. So we would build a dictionary of image patches, and then we would search through this dictionary of image patches to recover images that have very similar patches. And if you're thinking that image patches can be a sequence in a transformer, you are on the right path, right? So this idea of using patches as a way to search, it will come back now that we're going to talk about transformers for images. So you saw this a little bit yesterday as well. So this is the original transformer paper. The core idea is that we're going to use attention for everything, for every step of our network. This is the attention equation, the self-attention equation. And I'm going to try to open it up a little bit. So just a little bit of a recap from yesterday. So we have, let's think we have two sequences of vectors, and we want to compare all against all. So we compare all the vectors. We have a number that defines how similar one vector is to another vector, and we do that for all possible pairs. And then we have an attention matrix, right? We use these weights to do a weighted average of a third sequence of vectors. And then we call these queries, keys, and values. So the way to think about self-attention is that we are actually doing a search. We have our queries. We are searching our dictionary through their keys. And then we are getting the result as an average, a weighted average of our values. So that's where the comeback of doing a dictionary and doing search comes back. And we call this self-attention, of course, because these three sequences of vectors are derived from the same sequence of vectors, okay? So they are just projections of X, the inputs to our self-attention layer. And when we do the weighted average, we do a softmax on top. That's the little sigma over there, so that we have something that sums to 1, and it's properly a weighted average of our values. Okay? Don't worry about the division by the dimension. That's a normalization term, because otherwise high-dimensional vectors would explode the value of those distances. Okay? Good. So this is a transformer, a traditional transformer used for translation on natural language processing. And we have three things to highlight so that you remember what we're talking about. And we're going to change one of those mostly for doing vision with transformers. So you remember from yesterday, the embedding lookup part is where you have words. And those words, they can't be words on a network. They need to be a vector. So we have a big matrix that is like a little bit like a dictionary, where each word is represented by one vector. And then we build our sequences of vectors representing all of our sentences, all of our texts. Good? We have positional encoding. Now, that's an interesting one, because positional encoding exists because when we do self-attention, that is an operation that is invariant to permutation. So when we permute two vectors on our sequence, the output is permuted equally. The result does not change. So the operation does not care about the order of our words. And that is bad for natural language processing. It's going to be bad, it's going to be worse for images when you get two images. So the positional encoding is an extra value that we add to our vectors to tell the network, many quotes here, what position that vector is within our sequence, so that our sequence is a little bit less invariant to permutation. So this is a good feature, but it will get in the way, especially when we talk about images. OK. Oh, I forgot two texts in Portuguese here. And they also introduced the idea of multi-head attention. So instead of having a single self-attention, they use multiple heads of attention to diversify the outputs of each of the layers. And they also break the dimensions per head. So it also saves a little bit on computational time. OK, so this is a transformer. You are all recapped. So how do you do this for images? So this paper is the visual transformer, known as VIT. And the idea here is that we start with an image, and we're going to break that image into patches. You see? We are going back to the bag of visual words. So we're breaking the images into patches again. And we are comparing those patches against each other to do search. But now we're doing search within our own image instead of across a database. OK. So we get those patches. We flatten those patches. Now they're vectors. They are tiny vectors, like probably 16 by 16 patches on the first visual transformer. And we do a linear projection of these flattened patches. Linear projection you can think of as just a single layer of a multi-layer perceptron. And we get, as a result, the input to a common transformer. So we do positional encoding as usual. And now we have one vector representing each patch. So it's like each patch is one word on our sentence. That is our image. The other thing that we do that is special for the visual transformer, and that happens because we're doing classification, we're not doing translation, we're not generating text, and we're not generating images. So we need a way to do classification. And the way to do that is that aside from having all of the patches as inputs, we have one special vector that is a learnable classification token. That is like a special word that we include. That's just a vector. It starts randomly, and it learns together with the gradients descent process of our network. OK? So this vector is useful because when we go through a transformer, however many layers, we get a sequence of vectors. And our original vectors each represent one of the patch of the images. And we don't want to pick one special patch to be the patch. So instead, we pick our learnable classification token at the output and use that to do classification as usual, using some layers of what would be an MLP. OK? All make sense? Very good. So what is bad about a transformer? Why didn't we all move to using only transformers? So I did a similar tutorial some 3 years ago. And I said during that tutorial that transformers would never work for images, which, sorry. And this paper was published already. And the problem with this VIT design is that transformers don't have the inductive bias that CNNs have. So they are made for sequences of vectors. And those sequences, they are permutation invariants, which means that for this design, we don't have anything on the architecture that is tailored for images, right? So things that are close to each other don't really matter for this network. And as they do, so I'll compare them to convolutional neural networks, where things that are close to each other actually do matter. They don't have translation invariance that is important for images as well. And basically, those are the biggest problems. And what this causes, what this means really, is that when we do attention, we can represent more functions. So in theory, we can solve more problems because we're not locked by the translation invariance or the inductive biases of a CNN. So in theory, we can represent more problems and solve more problems, but that also means that we have a larger search space for all of the possible combinations of weights that can give us a solution to our problems. And we don't want that, because we're training using stochastic gradient descent. That is a stochastic process. We start from random weights, and by making the search space larger, that means we need more data to make solutions work, right? Because on convolutional neural networks, things work if they respect that inductive bias that they have imbued in them. Here, we don't have, it can do any task, but we need to give it more examples. So when I critique their original VIT paper, it's because they can't even train on 1 million images. This visual transformer doesn't work with 1 million examples used to train it. So the solution came very little time after I gave my talk saying that it wouldn't work. And, the solution, and you will be surprised by this, because everyone is using visual transformers to do everything today, classification-wise. And the solution is to train a very big CNN and then copy the response, the features of that CNN to a transformer. And then the transformer learns faster because it's copying the CNN, and it also performs better by the end of this process, right? So using a CNN as an intermediary step, so you're using the inductive biases, and you're stealing the inductive biases of a CNN to get it to a transformer, and then you can train a transformer with less data. There are advantages of using a transformer instead of CNN, and the biggest one is that, in general, you can fine-tune more easily a transformer than a CNN because it is more malleable, more adaptable to more tasks. So if you start with a pre-trained transformer that is already very good, you can probably reach a better result than when you start with a pre-trained CNN, specifically for discriminative tasks. Good? OK. So we talk about those two. And then I'll just finish my talk by speaking about what I think would be the future of discriminative work with images. And that is contrastive learning, mostly. So we talked about the common pipeline, and we talked about how now with neural networks, CNNs or transformers, whatever flavor you want to use, we do feature extraction using those networks. This entire idea is called representation learning. It was called by Benju and friends. You probably know all of those friends. And so the idea is that now we can take a step back and think, OK, so we're doing feature extraction for our tasks. Can we use those features for other things beyond classification? Can we use those features without retraining our models? Can we just use that as a feature extractor that we learned, as we did before? So again, we're going in a cycle. We come back to the idea of extracting features and then doing some other task on top. And these features can be used directly, for example, for content-based image retrieval, for pre-training something for multiple tasks, for recommendation systems, because we're comparing vectors, for face recognition, because we're comparing representations of faces, for unsupervised learning, because we're wanting to cluster images without knowing anything about them, and for self-supervised learning, where we don't have any labels, but we can still learn, right? So the idea of training a network to be only a feature extractor, it becomes contrastive learning as the literature evolves. And we started contrastive learning a long time ago with this paper from 2005. It was presented on CVPR 2006. Contrastive loss, the first contrastive loss, that's not the one you probably have seen before. It appeared here, and I'll try to explain how it works. So we have 2 examples. We don't have one image only. We're extracting 2 feature vectors. So we're not doing classification. The task is comparison. So we have 2 vectors representing our images. Each x then is a sample, and y is a binary label that tells us if those 2 images should be similar or they should be dissimilar. So these are the network weights, okay? And D is a distance function between our 2 images. And if the pair is similar, then we want to decrease the distance between those 2 vectors. And if the pair is dissimilar, we want to increase the distance between both of those samples. But we have a little margin there, because we don't want to use all of the space in the universe. We don't want to throw the examples too far apart from each other. And this M is our margin. So we are extracting 2 vectors, we're comparing them, and if they're similar, we want those distances to go down. If they are dissimilar, we want this distance to go up. Okay? That's the core idea for all contrastive learning. Another example of contrastive learning came from Fastnet. That was, at the time, the state-of-the-art for facial recognition using only 1 image of the person as an example. And they did a reformulation of the contrastive learning into what we call a triplet loss. So it's a triplet because we have an anchor, we have a positive, the circle is on the wrong one, sorry. We have an anchor, we have a positive sample, and we have a negative sample. The positive sample is similar to the anchor, and the negative sample is different, should be different from our anchor. So now we are taking 3 examples at once. The margin, it actually limits not how far we want the negatives to go, but it limits the relative distance between positives and negatives. So the effect is that we're going to, at the same time, get the negatives far away and the positives closer, and the difference between those distances will be about close to the margin. Okay? This is a little better because we don't run the risk that we have on contrastive learning, the original one, of collapsing all the vectors into a single vector. But it has other problems. For example, the shape of this loss function is very flat. So it can easily get to a gradient 0 and you don't learn anything. So what we use today, there are more comments on the slides. What we use today, actually, mostly, is information noise contrastive estimation. So this is an evolution of all of those contrastive learning ideas. And the core idea here is that we have an anchor and we have a positive pair as inputs. And we also have as inputs all of the other examples that are within our batch. So a bunch of negatives, a single positive. So we are actually looking at the distances between everyone and everyone. You see, we're doing search again. We're actually comparing all of the distances, and then those exponentials, what they're doing is a softmax function. So we are doing a probabilistic distribution over the distance of one example against all the others, and we are making this fit within it sums to 1 as a probabilistic distribution, okay? And then we train this using cross entropy as we would a classification task. So that function is very well behaved. We know how cross entropy works, and it works in general. So it is like we have our anchor and our positive, and we are classifying if those two are the same, and comparing to all the others, and the loss will tell us that those two should be the same, they should be similar, and it should be different from all of the other examples. That's the sum that we have down here. So it should be closer to the positive and far away from all the other examples within a batch. And it works because the shape is good. It's just showing all the parts. It works because we are controlling this distance by making it a cosine similarity. So we also normalize all the vectors. Everyone is contained within a ball with radius 1. So it can go too far. We don't need a margin. And it works also because I didn't circle the temperature. OK, we'll get to the temperature. Yes. And it also works because we have this idea of a temperature that also shows up when we do transformers. And the temperature helps us control the spread of this probabilistic distribution. What that means is that when we divide by a larger number, we're going to get a flatter distribution. So it won't make the examples too far away, just a little bit far away. And if we get the temperature down, we are going to get larger numbers within that exponential, within that normalization. So we're going to get larger peaks within our distribution. And that is a way of telling our model how we want it to behave between being very discriminative from one example to another, or being very soft and letting everyone be close together, close to a uniform distribution on that ball with radius 1. OK? How is contrastive learning used? So one of the best known use is for self-supervised learning, because now, because our classification task is comparing samples, we can use that to compare samples to themselves. So what I mean by that is that we can get an image, do something to that image, like rotate, change the color a little bit, and then we extract information from those two images that were the same images at some point. And now we compare those vectors with our loss function, and we want those samples to semantically be close, because they are the same image. And we do that with information noise contrastive estimation, that loss function. And now we are learning what semantics mean without having any labels. And the way self-supervised learning is used is that you train that representation. Now you have a nice space where the images fall into as their representation vectors. And now you can train that for other tasks, any tasks. So the example in the graph over there is for our classification, and they show that they do better than using supervised traditional learning for image nets when they do this contrastive self-supervised learning first. The other interesting thing, and that's where we're going really, is that using contrastive learning to approximate information, we also get to do that across modalities. So this is KHIPU. This is a very famous paper. You saw a mention of it yesterday as well. So the idea here is that we have two encoders. We have an encoder for the images. We have an encoder for the text. And now we can do information noise contrastive estimation to approximate text, the captions of images, to their images on the same space. And now we have images and text that we can use to compare to each other. And this is very helpful to do generative work. This is very helpful to do image descriptions later on, and very helpful to do classification as well, because now dogs will be close to words that describe dogs or that are similar to dogs in their descriptions, and other animals will be also on the same space, both in the way of text and in the way of images as well. And that ends my presentation. Thank you very much. If you have any questions, feel free to ask.
Thank you, Leo. That was an amazing talk, amazing lecture. I think that everyone had followed you very, very well. But we have also some minutes for questions for the audience, so please raise your hand, and we are gonna. Okay, there is a question over there.
Hi, here. Thanks for the presentation. So I wonder, in the last topic, in the contrastive loss, you said that doing data augmentation, you get different images that you want them to be close. But what happens if there is a very similar image in the data set that is not the original one, and you are trying to keep that away? Is that something that has effect in large data sets, or it doesn't matter?
Well, so the idea of doing self-supervised learning is to start a model, basically. So that when you actually do a task, you get those weights and you get those representations that are already well distributed in space, and then they will be easier to fine-tune to a final task. But also, contrastive learning has been used to do actual supervised learning as well. So instead of doing this with the same image, you do that with images from the same class. The famous example is SupCon, that's the name of the paper, that's supervised contrastive learning. They do exactly that.
Thank you.
Here. Thank you for the talk, really nice talk. Maybe I didn't understand well what you said, but you said in the multi-head attention that the different heads splits the dimensions. Is that common for NLP transformers too, or this is something for? I never heard about that. Maybe it's.
That is a hidden information, I think.
Thank
You look at the code, and then you see, but they do that for NLPs as well, or at least the codes that I looked into. So you have like a vector that's 256, and you have, I don't know how to do math on stage, sorry. So you have like 4 heads, and you break 256 by 4 heads, usually, because that saves a lot on computation, and you get all the benefits of multi-head attention together with that. So that is usual.
Hi, hello. Thank you for your talk. It was great. I'm also working with contrastive learning, so thank you for your presentation. It was very complete. Have you ever worked with data that doesn't have to do with images by any chance, or have you worked only with images?
I have worked very little bit with time series. Yeah. So that's I worked with sketches. So sketches can be interpreted as a time series of strokes that you go doing. That's what I did for my PhD, doing sketches and images. But we found out that sketches actually are better represented, usually, by using the pipeline for vision instead of the pipeline for vectors.
That's really interesting, because I work with time series, and I'm working with transformers. And so I was wondering if you could very briefly go back to what you mentioned about transformers not working for images and using convolution and stuff, because I didn't quite catch it broadly. So
okay. Yes. Oh, we can go back very quickly. That. Oh, it's not showing. Okay, so I'll try without the slides. It's fine. So the idea is that I don't think this may apply a little bit to time series as well. So the things that transformers, they are permutation invariants, even when we use the positional encoding meant to solve that problem. And The thing is that they have less bias within their design, and that makes the search space of possible transformers that you can have much larger. And if the search space is larger, you need more information to get to where you want to go. So when you're doing time series, we used to do RNNs, and RNNs had the very strong inductive bias of it being a sequence, right? Because you could only process the next step if you process all the previous ones. So we also lose one inductive bias when we go to transformers. So I think the solution will not be the same, because on vision we have the solution of training a CNN and then getting those responses into a transformer. The solution would not be the same because RNNs were never really known for, working super well for time series. So that wouldn't be a solution. You'll probably need a way to have more data on your. I already have 1 million. Oh, okay, okay. You already have 1 million. You're starting good. 1 million, maybe not enough, but Can you get more?
I can, but I don't think the issue is going to be only data. I think it's just the nature of it's a time series, but it's not a discretely sampled time series. It's irregular sampled time series because it's a light curve from astronomy measurements.
Okay.
So the complication there is that you have a time series that has a measurement at a set time. So it's really like 2 vectors of the same size. Same dimension. It's 1 vector for the data, 1 vector for the. Should I? No, it's okay. I'm going to repeat it very briefly, but I work with light curve data, which is a type of measurement in astronomy, and it's a time series, but it's not discretely sampled. So it's not regularly sampled. It's irregularly sampled. So one of the struggles that we have is that you have to provide the measurement, but you also have to provide the moment of the measurement. It's relevant to classify astronomical observations.
Yes.
So how do, the great issue there is how do I combine the data, or how do I provide the inductive bias in order for my transformer to, quote unquote, understand that there's, that the measurement is relevant, but also the moment of measurement is relevant. So that's what I'm struggling. So I would love to hear your input if you have time, right?
Okay. No, this is it's a complete guess, but I think what you need is to change how positional encoding works on your network, right? Because the positional encoding is meant to tell the network. It's not a being. So I don't like the word telling. To tell the network where things are. So if you have moments and they come back again, maybe you can use the same encoding for moments that are the same, even though they are within the same sequence. So you can use the traditional position encoding of sines and cosines and do a trick with that, repeating the frequencies. Or you can do learnable positional encodings as well, and then you have the same learnable positional encoding. Oh, you are doing that.
Oh, sorry guys, but I know the discussion is so amazing, and you can keep doing that in the coffee break because
Okay.
Leo, it's amazing what you have showed. Sorry, I feel like a bummer, but this is my job. So thank you, Leo. Everyone is invited to join you.
Yeah.
You're gonna be here until
I'll be here the whole week.
the whole week. So you are gonna have this amazing discussion with Leo. So thank you very much. That was amazing,
Thank
and
you.
we appreciate that.
Do you have also the change?
Yeah, exactly. Can you put it down on the pocket?
Okay.
Yes.
I did a post-up.
Yes.
can do Paula Costa. It's okay.
Oh,
Okay.
so this is for the pointer?
Okay.
This is working, and I'm going to ask them to. You have also the
Okay.
pointer there?
Okay. Thank you. No.
It is in share mode.
Yeah. Okay. Thank you.
Okay, so we are going to welcome our next speaker. These are the spotlight sessions. Each one of the speakers is going to have 15 minutes. And now I'm going to present to you Paula Costa. Paula is a professor at UNICAM's Department of Computer Engineering and Automation. She holds a degree in electrical engineering, a master in mobile communications, and a master and a PhD in computer engineering. Her research focuses on generative AI, multimodal AI, and effective computing. She coordinates the cognitive architectures research line at the UNICAM's AI and Cognitive Architecture Hub, and he's a member of the Brazilian Institute of Data Science. Her work bridges AI, cognition, and human interaction, shaping the future of intelligent systems. Please welcome Paula.
Are you hearing me? It's okay? Okay. So good morning. It's a great pleasure being here. Today I will talk a little bit about our scenario of artificial intelligence in Brazil. So I would like to start remembering that 500 years ago, a new technology, the caravels, changed our fate in Latin America. This technology carried conquest, devastation, cultures were erased, lands were stolen, millions of native people lost their lives. Caravels also carried chains. We had this history of slavery in Latin America. So technology is not neutral, right? Is AI our new caravel for Latin America? If it is, who will control it? So we have some cues already. This is a report from the Stanford University, and we see here the AI patents granted by region. And I believe that you can maybe find Latin America here. We are this pale blue line, right? So from this scenario, Latin America is a consumer only of technology. Also in Brazil, we are already facing some strange situations. Let's call that. So I don't know if you heard about, but in Brazil, the X platform was banned for some weeks. Also, Brazil was against the new policies of Meta, and recently we had this strange project scanning iris in our country, and we are also fighting against that. So, foreign companies collect our data and extract wealth without leaving local benefits, right? So we are here at Chile, participating in this KHIPU, to build collaborative networks, to develop regional policies, maybe discuss about that, right? Maybe trying to find a joint strategic AI agenda, and it would be nice to strengthen our institutional cooperation, and of course, promoting student exchange. What I would like to say about that is that for us, it's not a matter of choice, okay? We need to do that as Latin Americans. So I'll talk a little bit about opportunities in Brazil. So right now, Brazilian has an AI plan that is called IA para o bem de todos, AI for the common good, maybe it's a translation. And our government has a national plan for investments on AI from the last year until 2028. In this plan, we probably will spend more than $1 billion in infrastructure of AI, over $230 million on training and qualification, and the whole plan totalize more than $4 billion on AI. What's the Brazilian view for AI? What's IA para o bem de todos, right? So it's an AI that's human-centered and inclusive, that addresses social, environmental, and economic challenges, an AI that tries to defend our national sovereignty, that is transparent, traceable, and responsible, and we look towards global cooperation on fair and mutual beneficial terms. And it is explicit in our plan that we want an AI that promotes human progress, information integrity, and democracy. So in terms of Brazil, it's important that you know that we have at least two main funding agencies that I would like to tell about for students, that is CAPES and CNPq. And this is the way, if you want to go to Brazil through some scholarship, we can talk more about that on the coffee break. And I'm here also to talk a little bit about Campinas and why Campinas. So we are here, right? Let me find the pointer. We are here, and Campinas is on the São Paulo state. So we are in this very wealthy region of Brazil. And I also would call the attention to FAPESP, that is another funding agency that has scholarships for foreigners to go to São Paulo state to make their research. And Campinas is not so far from Rio de Janeiro. We are 90 kilometers from São Paulo, 90 kilometers from São Paulo. We have an international airport, so actually we have two international airports in the region, and Campinas has over 1.1 million inhabitants. Talking a little bit about my university, Universidade Estadual de Campinas, Unicamp. It's the second largest university in Brazil. 8% of our academic research in Brazil is produced at Unicamp. We have a huge number of undergraduate and graduate students, over 1,000 professors, and it's really important to highlight that Unicamp is a public university. Both undergraduate and graduate programs have no admission fees or tuition costs. And also, I would like to highlight that Unicamp has a strong culture on entrepreneurship. We have over 1,000 patent registrations. Campinas is known as the Brazilian Silicon Valley. We have all the ecosystem of startups growing there. Also, just to give a perspective, in terms of Latin America, Unicamp is considered the third, among the top 3 universities in Latin America, right? We are in the 3rd place. But I highlight that Campinas Unicamp is the youngest of them. I'm a professor at the School of Electrical and Computer Engineering, and we are one of the schools that gave rise to Unicamp, right? And we recently celebrated over 1,000 PhD defenses performed, and 12% from those students at the graduate program already come from Latin America countries. So we have a great Spanish speaking community there. Well, at Unicamp, if you observe our map is actually our logo, right? And we have 2 big institutes, 2 big schools that works with AI. So we have my home, that is the Faculdade de Engenharia Elétrica, and we also have the Instituto de Computação, and we share the managing of a computer engineering course. So at Unicamp, you have 2 courses, computer science and computer engineering. They were the first courses related to this subject in Brazil, and they are also considered the best computer science courses in Brazil. So I'm telling this because if you go there, you are really going to find an excellent community in computer science. My group is called Artificial Intelligence for Multimodal Signal Processing. Right now, we have 1 postdoc, 5 PhD students, 8 master students, but what I would like to talk about them is that they are, all of them, fully funded. We have 1 physicist, 1 mathematician, 1 linguist, 1 plastic artist, and we already have people from other countries than Latin America. We embrace diversity because we studied information theory, and we understand that entropy is good to carry information. So I will not talk about my research lines today. You have a QR code, you can check there. I will proceed to talk about some research centers that we have there to finish my talk. So we have our hub of artificial intelligence and cognitive architectures. This is a hub where we are advancing research on many dimensions of artificial intelligence. We also have at Unicamp the Brazilian Institute of Data Science, and what is interesting about the BIOS Center is that we have those 3 axes: health, agricultural, and methods, and we have specialists that are dedicated to make this connection of AI with their areas. So Rodolfo is a doctor, medical doctor. Jurandir and Priscilla, they are agricultural engineers. And Leonardo is an engineer that is specialized in methods. And one thing that's very interesting about Unicamp is that we have a hospital university, and we have a lot of data of health. Also, I will finish talking about Horus. It's another center that is related to Recode AI. That's a huge lab that we have there in Campinas. And to summarize, AI is already a public policy in Brazil. Unicamp is strategically located, highly connected. We welcome you. Some guidance may be needed to find the funding opportunities. Please talk with Brazilian people here. We have a lot of students from the Record Lab. Please see the t-shirts and ask them, but also speak with me. Walking around yesterday, I noticed that sometimes people are a little bit shy to talk with me, maybe because their English are not that good. Don't worry about that. There is a fact that Portuguese speakers understand Spanish speakers better than the other side. And there's a linguistic reason for that I can explain to you because I work with text-to-speech synthesis. I understand that a little bit. So my invitation to you is let's write a different story for Latin America. When I was in high school, I didn't study Spanish, but I studied English. I didn't study the Colombia history, Chile history, or so that, but I studied a lot of European and North America history. But I learned a lot of jokes about people from Argentina, because usually we were adversaries at the soccer, and the fact is I even don't like football, right? But I cheered a lot for Argentina on the World Cup. And remember, technology is not neutral. Muchas gracias. Obrigada.
With thanks, Paula. Now we're going to go to our next speaker.
Creo que no, aquí viene. Okay.
Ay, pero yo lo subo. Ahí ya me lo...
Hola, ¿me escuchan? Can you hear me? Okay. Super.
Now we're going to hear from Gilberto Ruiz. He's a researcher in computer vision, medical image computing, and surgical data science affiliated to the Advances AI Research Group at Tecnológico de Monterrey. He obtained an Erasmus in computer vision and an Erasmus Mundus Master in Computer Vision Robotics from Haydock World University, and a PhD in Computer Vision and Electronic Imaging from the Université de Bourgogne, the Laboratory d'Imaging. My French is amazing. Vision Artificiale. He has such a big summary that I would love to hear from you. I'm not reading all this because we are running out of time. So let's welcome Gilberto, and let's gonna hear from you.
Thank you. So thank you very much for the invitation to Enzo and all the organization team. So I will try to go quick. So I come from Tecnológico de Monterrey, which is one of the probably the largest private university in Mexico, but it's a non-profit university. We have 27 campuses all around the country, more than 11,000 professors, almost 1,000 researchers. And funnily, we have this agreement with the University of Chile that is called La Triada. That's why they put the map there with the UC Andes and this university. That is actually the first time I'm visiting here. Although I was in Valparaiso 1.5 years ago. Guadalajara is in the west of Mexico. I just put this slide. And Time Out magazine named the city one of the coolest in the world in 2023. But now that I am visiting Chile, and Santiago in particular, I think I disagree. I prefer Santiago, is really cool. I will mention a few of the, I belong to the artificial intelligence group in Tec de Monterrey, and I will showcase the research of two of my colleagues. This one is from Mauricio Antelis, a Colombian guy who does assistive technologies, very nice stuff. He works with MIT, really nice work with people who cannot walk, and this kind of thing, assistive technologies. And also because we have tequila in Guadalajara, we have plenty of colleagues that are working with drones to assess the quality and illnesses, diseases in the plants and so on. So you can work with us in these kind of topics. In my case, I lead the computer vision and image analysis biomedical engineering team. I collect insights and different iterations of the group through the years. Also some colleagues from Tec de Monterrey, and what we do mainly is that we want to create maps. One of the things is that we want to create 3D maps of our hollow organs, like the colon, the stomach, and so on. And I love this cartoon. I don't know, you know Futurama, but they make a lot of allusions to this technology. So basically, we work in endoscopy, laparoscopy, surgical stuff. We work a lot on computer-aided diagnosis and detection. And I will be giving a talk on Thursday on computer-assisted navigation, basically creating 3D maps for enabling doctors to see and do better diagnosis. Some of the stuff we do, instrument detection, segmentation tracking, lesion characterization, lesion detection, and segmentation, and so many other things with visual models, language models, and so on. And because we are in the intersection of medical computing and computer vision, we go a lot to conferences like ISV. This one was in 2023. I don't remember I met Enzo in ISV, in Cartagena. We also go a lot to ICCV, CEPR. This was in 2023, I think. I couldn't go because I was in Mikai. We went to Mikai as well, 2023, I don't remember. 2024 was in Morocco. And we organized a computer-based medical systems conference in Guadalajara last year. Was lots of work, but it was really nice to be able to meet lots of friends. And from my research, I have several collaborations. One of them is this Recondit project that we do with the Centre de Recherche en Automatique de l'Analyse, a French institution. Several of my PhD students are getting degrees from France and Mexico at the same time. And in this particular project, we are interested in doing visual recognition of kidney stones, a very interesting topic that has been going on for like 4 or 5 years. We also work with the University of Leeds, this one more related to minimally invasive surgery. And I also have to thank Microsoft because we have received help from them for 3 years now. We have received almost $300,000 in credits for our research. And if you're interested in the PhD, some interesting stuff from the PhD is that Tec de Monterrey gives you full living expenses, full tuition fees. You get a conference per year, fully paid. And we also have several collaborations on some of the acceptance requirements. So if you want to talk with me, you are welcome. I still have 10 minutes, interesting. I'm going very fast. So because I don't want to take your coffee. I will talk a little bit some of the projects we do. I think some of you already met Laura from Latent.AI. Yesterday, we have been working on Latent.AI for several years now. For example, we have this program called the Supercomputing Initiative for the Advancement of AI in Latin America. We got this gift from NVIDIA to have this computer, to have this program, receive projects in order to give proposals access to supercomputing and training. So this was a collaboration with Latent.AI, Tec de Monterrey, and some people from, and I did this presentation in Texas 2 years ago. So basically some colleagues, probably some of you know, Nils Murrugarra, he's from Peru, very active guy. We have been working a lot on this. And also we have lots of input from the community, and actually I'm very happy to see some people we invited to have some discussion on how to use this machine. So we invited Enzo at some point, Cesar that is somewhere around as well. So it was really nice program and effort. This was the inauguration in Guadalajara 2 years ago. Since last year, we also have been running the Google Explore CSR Latin undergraduate research program in computer vision was we got several 30 students or something to have the scholarship to work with people. I think some of them were working with ENSO as well, and some with other people for sure. We got 96 Menti applications, and some of these coming from these countries. And at the end, we accepted 18 because we were given the money and time to work on this. We also have some online workshops in which we invited ENSO, I think, at some point as well, and some other people. So we held these very interesting workshops, online workshops, and the idea was also that some of the students will go to CEPR. So we invited some of the best students to Seattle to this LXI workshop. I also saw some of the attendees in this conference, in this workshop. Was very nice. So basically, yeah, we have some people attending the workshop in Seattle. Some of them got to know Andrew and G, and some people, interesting people. And I still have some time, but I will, basically, I also have the hat. I'm the treasurer of the Mexican Society for Artificial Intelligence. So this is the current board. We organize the Congreso Mexicano de Inteligencia Artificial, that is mostly like a Spanish conference for Mexican people. But from this year, we are publishing the proceedings in Springer. So if you want to send a paper in Spanish, I think for acceptance has to be published in English, but the presentation can be done in Spanish. We have the Mexican International Conference on Artificial Intelligence that is in English, and we get, for example, last year we have one of my friends from Harvard, Nassim Oshin, to give a keynote, but we have lots of people coming. It's a very interesting conference, but has been mostly Mexico, and probably sometimes we have people from Colombia and other places, but we want to have more people from Latin America for sure. And that's it. This is my contact details. I hope to talk with you around. Thank you.
Thank you. That was amazing. I can't believe someone can speak faster than I do. Yeah, I'm speaking slowly now. So thank you for rushing and for introducing. Also, you are invited. So thank you. You're invited to talk to you during the coffee break. So now we are going to have a coffee break. We are gonna, because we are delayed on schedule, we are gonna delay the coffee break 15 minutes, but everything remains as it is. So please be here to start sharp 11:15 for the next talk. So enjoy the coffee break.
Sale bien, ¿no? Creo que hay cosas que me están quitando muchísimo tiempo.
Y que apaguen eso.
Es algo pasado. Igual tiene poquita batería, eso, pero debería alcanzar.
Sí, no se alcanza. Esta batería dura mucho tiempo.
Ah, perfecto.
Pero, sí. Silence. Silence.
Hello. Hi. Hi, everyone. So it's my honor really to present Peter. So let me read his bio. We all know Peter is, he does not need any introduction here. He's a senior staff research scientist at Google DeepMind, an affiliated lecturer at the University of Cambridge, and an associate Clare Hall at, in Cambridge. He holds a PhD from the computer science from the University of Cambridge, obtained under the supervision of Pietro Liò. His research concerns on aligning neural networks with classical computation to assess and improve their ability, their out-of-distribution generalization, and he focuses on algorithmic reasoning. We all know Peter for this. Graph representation learning, categorical and geometric deep learning, where he has written a book that many of us have read. If you did not read it, Google it. You can download it for free, right? Yeah. Easily available. So his research has been used to substantially improve travel time prediction in Google Maps, guiding intuition of mathematicians towards new top-tier theorems and conjectures, which it was published on Nature. And then he was part of the team or led the team that did the first full AI system for tactical suggestions in associations in football, meaning our football. So his work has been featured in so many really famous press articles, but when I saw it featured in InfoBay, I thought, okay, Peter really made it. And the last thing, so Peter is very committed also to bringing AI in the world. He has led the Eastern European Summer School, which was in Serbia last year, and is involved there. He has been wanting to come to KHIPU for a long time. We have been wanting to have him. He doesn't have an easy schedule, but we have the honor to have him here. He drinks mate. For those of you who have mate, you can give him one. So please welcome Peter. Thank you so much.
says more than it should, I guess. Okay. Is it good? Okay, wonderful. So let's get started. So as mentioned, today I'll be giving you a completely revamped tutorial on graph machine learning with all animations designed from scratch. So if you've seen some of my tutorials before, you probably will not have seen at least 80% or 90% of this presentation. So I hope it will be interesting to everyone. So I would like to start by acknowledging that, I am going to talk to you about machine learning over a somewhat unorthodox modality, over graph structured inputs. And what I often like to say is that I hope my dream at the end of every tutorial I give is that, I tell you about graph representation learning and you walk away from the tutorial thinking we should all be doing graph representation learning. So let's see if I can make that happen, right? Let's start by trying to answer why graphs, okay? So I'm going to I'm going to try to have as little words on the slides as possible and just try to introduce the concepts in as intuitive way as possible. So we have here a graph structure. Hopefully this doesn't look too unfamiliar to most of you. And the key building blocks are nodes. So our graph is constructed of various nodes, which are like atoms of information. And also we have connections between the nodes, which we call edges, right? And altogether, the collection of nodes and the collection of edges form a graph, right? So this is your usual textbook definition of a graph. Hopefully, when it's visualized like this, it will be easier to follow all the different things I'm going to plug into this graph. Okay, so once we have a structure like this, what are some meaningful things in life and nature that we can model using this? For example, we might decide that the different nodes in this graph correspond to documents, papers, web pages, Wikipedia articles. So you might plug different text-based representations in the nodes, and you might decide to connect the two nodes if there's a link pointing from one to another, if there's a citation citing one paper from another, anything like this. And then you might be interested to say, take the understanding of this node and all of its nearby connections and try to classify each one of these documents for which topic it is. This is a very standard node classification problem, which is the crux of what, say, I trust many of you publish papers on the archive. Archive moderators every day have to solve hundreds of problems like these. You give them a stack of papers. They have to check that the topics you assign to your papers are correct ones. And if you get the topic wrong, then you have to wait for a month before your paper comes out on the archive, right? So this is one particular task, node classification, which is very common on graph data. You could also instead do node regression. So not predict a topic for each node, but some scalar value, right? One example, you could imagine nodes being different segments of road and edges being intersections connecting different roads. And you might be wondering, if you're in your car and you're driving from one part of town to another part of town, how long will it take you to traverse a particular part of road? This is now a node regression task. And there's no coincidence. I'm showing you this. This is actually one of my arguable claims to fame. I was part of a team at Google DeepMind that constructed a graph neural network system that predicts travel times inside Google Maps. And this is a system that's currently deployed worldwide, including in Santiago. So as this morning I learned, navigating Santiago traffic is pretty interesting. And, what's great about this particular system is that compared to the previous baselines that Google were using, it explicitly takes into account the topology of the road network. And therefore, it can anticipate when rush hours are going to happen or when different bottlenecks will happen better than the previous baseline. And the way in which this is served to all of you when you use Google Maps or a service that depends on Google Maps is in this form of a pathway that's selected, and you have different chunks of the pathway telling you where the node regressor thinks you're going to be waiting for a little bit longer. And this final travel time is also served using our model. And at the moment of deployment, this is the relative improvement we made against the Google Maps previous baseline in various cities around the world. Generally, the magnitude of how much the improvement was depends on how tricky the traffic was to manage. And one example from Latin America was actually Sao Paulo, where there was a 23% improvement when you started to take into account what the road network in Sao Paulo actually looks like. Okay. Other than predicting things in the nodes, you can also predict things on the level of the entire graph. So now my graph is a molecule, right? My nodes become atoms, like carbon, for example, and my edges become chemical bonds, right? and I might want to predict something about my molecule. For example, will it be a possible drug for a rare disease? Will it be soluble? Will it be toxic? All things that you might want to know before you start clinical trials, right? I would actually say that this motivation of predicting properties of chemicals prompted early graph neural networks to be discovered already in the 1990s, before we ever had the name graph neural network floating around. In fact, this is a great quote I got from Marwin Segler, who is a researcher who works in this intersection of AI and biochemistry. Chemistry disrupts machine learning, not the other way around. So already in 1995, chemists have realized that their molecules are graph structured, and if they want to do machine learning on them, they better take into account that graph structure. And in fact, this 2005 paper from Merkwirth and Lengauer, these molecular graph networks, basically had almost all of the bells and whistles you have in modern GNNs today. So chemists don't want to wait around for AI to catch up. They invented their own GNNs before GNNs became a thing. But this trend continued in the recent times. The resurgence primarily happened through these two papers in the 2010s. This paper from David Duvenot using graph neural networks to learn molecular fingerprints, and this work from Justin Gilmer using graph neural networks to do better quantum chemical simulations. And this then leads us to the crux of where these systems have been very meaningfully applied. And this is actually, in my opinion, one of the coolest applications of graph neural networks to date. Because as I said, you can throw them at big data sets of molecules, and you know whether those molecules are candidate drugs or not. And then once you've trained the model to predict whether something is a candidate drug, you can run it on any molecule you want, right? And it might just happen that some molecule you never thought about before receives a very high probability of being a strong antibiotic, and then you give it to chemists, and they figure out that, oh my God, this actually is a really strong antibiotic. I would never have known to check if this was an antibiotic, because it has a structure that's very unusual. But because it has an unusual structure, it means that it will attack bacteria that have developed resistance to the kinds of antibiotics we normally use. So there were these two different papers, one published in Cell, one published in Nature Chemical Biology, using GNNs in exactly this way to invent, well, discover, repurpose two new molecules, halicin and abaucin, both targeting potentially very antibiotic-resistant strains of bacteria. The cool thing about halicin is, it was previously used as a potential treatment for diabetes, which has, nothing direct to do with antibiotics, but this kind of GNN-powered search allowed us to find a completely new usage for it. And beyond just discovering new drugs, these kinds of approaches are also quite prevalent in material science. DeepMind's GNOME paper has discovered millions of new possibly synthesizable materials using these techniques. And also one somewhat left field idea, but one that was published in Science and leads to a potentially quite lucrative industry. You can use GNNs to understand smells better of molecules. And these guys are well on their way to revolutionizing the perfume industry by using GNNs as a basis. Okay, so that was molecular graph classification. Another one which you might also think about when you think of graphs are social networks, right? You can imagine different nodes as users in a social network. Edges are friendship links between them. And you might be interested to, say, predict what is the likelihood that a particular pair of nodes will be connected. This is a task known as link prediction, and you might imagine a social network using this to suggest to you who you should add as your friend, right? There's another very related concept where the nodes don't have to just be users, they can also be products, and edges can tell you, for example, which user has purchased which product, and this, or which products are purchased together, and this might then inform you another type of link predictor, which will say this user might really enjoy purchasing this product. This sounds like something you run into every day when you're on the internet, right? In fact, I will argue, if you're on the internet, you're very likely speaking with a GNN without even realizing you're doing this. And I'll just give a few examples of companies that publicly declared that they're using GNNs for various things. So here is Uber Eats. Uber Eats uses GNNs to recommend you which dishes to buy in a restaurant, which restaurants you should try next, all that nice stuff, using the same link prediction idea that I just showed you before. Airbnb has a blog post describing in somewhat vague terms how they use graph neural networks to recommend where you should go next for your vacation and where you should stay. And Amazon uses these graph neural networks to give you meaningful, diverse product recommendations. So for example, if you recently purchased Novak Djokovic's racket, you probably don't want to buy more rackets because Novak Djokovic is obviously the best there is, right? But you might want to buy some balls and pouches, headbands, things like that. So the P-companion method basically helps you deal with these kinds of things. Then Pinterest was actually the OG in this space, the first company to go public with their use of GNNs large scale in production. And the PinSage method, basically, for those of you using Pinterest, this graph neural network is directly responsible for the recommended content you see on Pinterest. And Spotify recently also went public with using GNNs to recommend which audiobooks you should listen to next by knowing which audiobooks you're listening to together and which users are your friends and what things they listen to. And more recently, LinkedIn went public with using GNNs to recommend you which jobs you should apply for next. And most recently, I think a couple of weeks ago, Snapchat announced that they're using these large-scale graph neural networks to recommend who you should be friends with next, what content you should look at, and also which ads to be served to you. So yeah, I would argue if you're on the internet, it's quite unavoidable. These are just the places where people publicly said they use GNNs. I'm sure there's many other places where a company did not announce publicly they're using GNNs. Another cool thing about graphs is that there's such a generic abstract structure that you can basically take any kind of popular data, or arguably more popular data like images. This is like the MNIST digit. And I hope you can agree with me that this is very neatly representable as a graph structure, namely a graph that has a very specific kind of layout where each pixel of the image becomes a node, and then you have some local connections connecting each pixel to its immediate neighbors, right? It's not hard to imagine how, if you do some kind of local information exchange around this graph, you end up basically simulating a convolution. Yeah? But one thing that graphs can do, and images cannot, is making sense of what happens when the data doesn't nicely fit on a plane, right? Very often when we have to deal with signals on the surface of the Earth or astrophysics signal, I know that Chile is quite popular for astronomical observatories, so a lot of the data from astronomical observations look like this because they're trapped by the surface of the Earth, right? And as you probably know, just judging by the size of Greenland on the map, if you decide to run a convolution neural network on a flattened surface of the Earth, well, good luck trying to fit anything meaningfully around the poles, right? But if you fit things using a graph, then you can start to talk about things around the poles without worrying too much about things blowing out of proportion. And indeed, when you model things on the surface of the Earth, like weather trends, you can basically imagine a graph structure of various points on the surface of the Earth, and they would just be connected to their immediate neighbors like they would for images, but without the limitations of images. And in fact, I'm not showing you this for no reason. There was another really cool work from DeepMind, GraphCast and GenCast, using these graph machine learning methods to do stronger AI-powered medium-range weather forecasting. And this was on the cover of Science. And also, it already has active potential to save lives and improve preparedness for natural disasters, because it can more accurately, over a longer horizon, forecast where a hurricane is likely to hit. So in this case, the blue are the different predictions from the weather forecasting system, and the red was the actual trajectory that the hurricane took. You can see already on a 7-day horizon, it basically imagines a plausible future for where this thing will go, right? And obviously, the more days you have to prepare for where impact is going to be, the higher chance you have to save a lot more lives and minimize damage. Okay, and just I want to leave you with a slightly more high-level point, which is you could also imagine graph structures in your brain, like in the different memories and experiences you have, right? So you can imagine a single node being like a concept of knowledge that you have. And the edge in this graph, the light bulb moment, I learned this, these two things are connected, right? And actually, this is how we build connections. This is how we learn, basically. And if you imagine, building up a graph representation like this inside an agent, and then strapping on some classifier to predict actions that you should take as a result of those memories, I think this could be a recipe for AGI. Or maybe put differently, I doubt you're going to be able to build AGI without an explicitly graph-structured component in there. So I hope that everything I've showed you so far has convinced you that it makes sense to study graphs. I hope nobody doubts me. I've revamped my entire suite of animations to hopefully put this point across as clearly as possible. Okay, so hopefully now I've convinced you that it makes sense to study graphs. Now let's try to see what these neural networks over graphs, these graph neural networks, actually look like. Okay, so this is our graph, just as before. it is a very nice way to abstractly think about the data, but as you probably know, if you've ever built or trained a neural network model, in order to actually train a machine learning model and represent your data in a way in which the machine learning model can do stuff with it, you cannot give it this abstract sparsified structure. You have to give it tensors, right? And there are very nice canonical ways in which we can present the data in a graph to a machine learning model, and you will see this in a lot of detail throughout your tutorial later today, which will cover this in JAX implementations. So one very standard way in which you can represent a graph to a neural network is you provide these two pieces of data. First, the node feature matrix, capital X, which just has the feature vectors associated with each node stacked one after another, and also an adjacency matrix, which tells you what are the edges of the graph in like a 0-1 fashion. Note the order of the rows and columns must correspond to the order of the rows of X, right? So for example, this cell here will tell me whether A is connected with D, right? And one thing I'll just make very clear is that just to keep the math simple, I am assuming that there are no edge features. Like you only have 0, 1, there's an edge or there isn't. Obviously, this is not always the case. In chemicals, you have single, double, triple bonds. You have lots of variety on what you can put in edges, actually. But all the takeaways will be identical, and the maths will be more brutal if I include all those edge features. So just to keep everybody's sanity in place, I'm deciding to just assume it's 0, 1, right? OK, so I need to stress one thing, which is the moment you've done this, the moment you've chosen to stack your features into a matrix like this, you've broken the law, OK? Like this is something you should not be doing. And why is that? Because there is nothing in this graph structure telling you inherently that this node comes before this node comes before this node, right? So you've made an arbitrary choice in how you ordered your nodes here, and this is bad, right? In order to compensate for the fact that we've done something bad, we need to ensure that our neural network doesn't depend on that choice, right? So let's imagine I have graph data, as I showed you before, and I have some neural network classifier which takes these two tensors and somehow predicts an output. What I would like my neural network to do is if I present it with a shuffled version of the data where I've changed the order in which I've seen the nodes, note I've changed the order of the rows and columns of the adjacency matrix in the same way, I have to have the same output in those two cases. This is a constraint that's necessary so that I'm not punished for doing something illegal by choosing an arbitrary order, right? So specifically, if you have your X and your A, your tensors, here you have accordingly permuted tensors. So permuted rows of the node features and permuted rows and columns. That's why there's PAP transposed of the adjacency matrix. This constraint is known as permutation invariance, and it's at the heart of the design of modern graph neural networks. And for it to be satisfied, this must hold for all permutation matrices P. So I will consider something to be a valid graph classifier only if this condition holds. OK? Now, sometimes you don't want to predict just one thing for the whole graph. You might want to predict things in the nodes, as we discussed before. And in those cases, actually, you shouldn't expect equality when you permute the inputs, but rather you should expect a sort of predictability, right? So in the case where you're predicting stuff in the nodes, note now your output has something for each node, right? It's no longer just a single vector. It's a collection of vectors. And actually, what we're requiring is that the output will now change if you permute the inputs, but it must change in a predictable way, in a way that follows the permutation, right? So what this equation is saying is, for any permutation, it doesn't matter if I apply it to the input or to the output of my function, I should get exactly the same result. And this is known as permutation equivariance, okay? And there is one very easy way to satisfy this constraint, and that is to just have a local function that acts on every node separately and maybe on its local neighborhood of features. And if you do that, you're guaranteed that this property will be satisfied so long as this local function doesn't depend on the order of the neighbor features that you feed into it, right? So as long as this local function is invariant to permutations, this whole function will be equivariant to permutations. And really, all that I've just shown here is just you can see this in a lot more pretty and clear manner if you draw it like that, right? So what are we doing in a graph neural network? We are basically taking a node's features and taking the features of all of its immediate neighbors and passing those features onto a latent space H in a way that depends on all of those feature vectors and in a way that doesn't depend on the permutations of those feature vectors. Okay. Once you have that, you can actually now construct a general blueprint for solving any one of those problems that I showed you at the beginning. So classifying molecular properties, classifying friendship links, regressing travel times in Google Maps. This one slide will tell you all you need to know. And arguably, I think it explains 99% of modern deep learning as well. So you have your inputs with some node features and some adjacency matrix connecting them. Your GNN, as we just discussed, will take your node features into some high-dimensional latent space. And for now, I'm going to assume it doesn't touch the adjacency matrix. We'll get back to that in a bit. And now, if you want to do node classification, you just strap on a classifier on top of each H vector. This is a fully equivariant function. If you want to do graph classification, now you have to be careful that your outputs are invariant, not equivariant. So you need to somehow aggregate all of your node vectors together with some aggregation function like summing or maximizing, anything which doesn't depend on the order. Whenever you see the O+, just think this could be a sum, this could be a max, anything which doesn't depend on the order. And then you feed that resulting vector into a graph classifier. And finally, if you want to do link prediction, another kind of equivariant prediction, you basically have a classifier over the features of the first node, the features of the second node, and in case you have any edge features, you can also plug them in here. Okay? So this one picture, I argue that most, if not all, deep learning setups will be one pathway through this construction, depending on what is the granularity of the structure you have and what is the prediction that you want to do. Okay. Now, I know that it was mentioned at the beginning this will be a geometric deep learning tutorial. This is actually going to be just a graph neural network tutorial, but I will quickly hint that this idea of taking permutations and building functions that are symmetric with respect to permutations is just one instance of a much more general picture. You can choose a particular domain, omega, where your data lives, and a symmetry group, which contains the transformations you want your model to be invariant or equivariant or resistant to, right? And just by choosing those two, you can use the ideas in geometric deep learning to basically recover the equivariance condition for that setting and basically rediscover all of the fan-favorite architectures. So for example, as we just discussed, GNNs operate over graphs and respect the permutations. Convolution neural networks operate over grids and respect translations, and so on and so forth. You might notice some other familiar faces here. We will discuss them later. And this actually, once you understand how to build these models, you can build general purpose deep learning architectures by just stacking these equivariant layers one after another and then finishing with an invariant layer at the end if you need a global classifier rather than a local classifier. And if you want to know more about this, we have a lot of resources, a book, blog posts, code, lecture courses at geometricdeeplearning.com. So you can find anything you want or need about this particular general part of the picture there. But here we're going to focus on graphs. Okay, so I've told you about the key condition, the permutation symmetries that make a graph neural network what it is. But I haven't yet told you how to implement it, right? I haven't told you how to satisfy this condition. And that's what we're going to talk about now, right? I need to stress that the investigations in this space have taken place over the course of many decades. And these here are just some of the earliest papers that we've been able to find where people are trying to do machine learning over graph structures in a way that's equivariant to them. So specifically, Alessandro Sperduti had this paper at NeurIPS in 1994, I believe. So this is the earliest instance we know of a NeurIPS paper that explicitly works on a graph structure. Somewhat around the same time, Goller and Kuchler have also released this technical report on backpropagating through structures. So these are some of the early signs in the 90s about graph neural networks. The name graph neural network and kind of the direct applications of it have actually mostly taken place in Italy through the work of Marco Gori and Franco Scarselli in Siena, who have popularized the term graph neural network in 2006, and also concurrently through the work of Alessio Micheli in Pisa, who invented the neural network for graph framework, which was also quite related to many architectures we use today. And I mentioned I had a chance to go to this computer science department / psychiatric hospital, where I had the chance to meet Marco as well. And he's a really, really fun guy to speak with. Really enjoyed my visit there. If you ever get a chance to visit Siena, go for the graphs, stay for the wonderful scenery. Okay, so how do we then actually build these local operators, right? We've mentioned that to build a model, to build a graph neural network model, all you have to tell me is how to process a node and its immediate neighbors to get some updated representation. So let's, people have tried various ideas over the years, but what really caused the field to blow up around 2017 was to really just keep it super simple. Like, don't think too much about theory, just try to do something that's scalable and works. And specifically, one idea that gained a lot of popularity is let's just average, right? So take every node, multiply its features with a matrix, and then compute the average over all of your neighbor's features, right? Really simple, really, really easy to implement as well. Couple lines of matrix code, right? You strap on any activation function you want, and you have backprop to learn this W. And actually, this is not quite the most popular graph neural network model. You actually get slightly more interesting dynamics if you do symmetric normalization. So you divide by the square root of the sender node's degree and the receiver node's degree. This allows the messages to be a bit more conditioned on the shape of both the sending node and the receiving node, and generally leads to slightly more interesting outcomes than here. But this model over here, this is the graph convolutional network, or GCN, which is the top-cited graph neural network model to date. And it was published by Thomas Kipf and Max Swelling at ICLR 2017. And I should stress that it's a result of taking this basically long line of GNNs built by doing like spectrally inspired operations, like trying to do what would a Fourier transform look like on a graph, right? And then basically they took all these concepts and they maximally simplified them, and they arrived at a model that actually worked really well on a lot of data sets, right? So, but if you want to familiarize yourself with some other works that also take inspiration from the spectral angle, you can look at the original graph Fourier transform paper from Jean Bruna, Chebyshev networks from Michael Deferard, which uses Chebyshev polynomials to approximate the Fourier transform, and then some other concurrent works like the mixture model networks and GraphSage. Okay. Now, this paper, like this GCN paper, basically completely blew up when it was released, partly because it was really easy to set up the experiments, to run them on a CPU, to quickly try out different ideas. It really captured the imagination of a lot of people, and the methods basically started just working. However, it was not without controversy, and actually Ferenc Huszár very quickly responded with one of his signature blog posts, trying to attack these models and kind of demonstrate that there are some things that they cannot do. And specifically, remember I told you one of the nice selling points of graphs is that images are a special case, right? So you should be able to reconstruct any image CNN as a graph neural network. But if you do just simple averaging on a regular graph, you can hopefully convince yourself that all of your filters will end up looking like this, like circles, because all the nodes at an equal distance away from you will have the same structure and will therefore receive the same averaging coefficient, right? So you actually cannot represent all image CNNs using these models. And to circumvent this issue, we basically need to remark that you cannot use just the structure. So in the previous equation, we used just the node degrees to tell us how to weigh different neighbors, right? But whenever the graph is regular, like an image, this won't help you because all the degrees will be the same everywhere, okay? So if we cannot use structure, what else can we use to distinguish different nodes? What other data do we have access to? Anyone have any ideas? Okay, positions. And for example, if my nodes are documents, what do I have access to? Right? You have access to the features of the nodes, the text itself, right? So let's use the features to tell us what are the neighbors that we're going to select, right? So specifically, rather than using the degrees to tell us how much to value each neighbor, let's learn a function that takes the features of the sender node, the features of the receiver node, and outputs a scalar coefficient, right? This type of function, you probably heard about it. It's often called an attention mechanism, which is the reason why this class of models is known as graph attention networks, right? And This paper, which I have published at ICLR 2018, was one of the earliest instances of a graph neural network which actually could simulate an image CNN. You might have to plug positions as well to allow for different angles to be represented differently. But one thing that's important to note, if you decide to go down this particular line of works and study them further, is that the data sets at the time when this paper was published were very easy to overfit and super simple. So the actual attention function we used for this alpha was really simple and actually provably weak. It actually only took 4 years before data sets became a little bit better. And then there was this GAT v2 paper, which basically explicitly called out that the original function we used in GAT was too weak, and that you can replace this with a more generic MLP, and you'll get all of the nice universal approximation benefits you would have otherwise lost. OK. So these types of models are now sufficient to express arbitrary image convolutions, provided you have good features, of course, or good positions. But they'll still only aggregate neighbor features as a sort of learned weighted sum. Can we do something more generic than a weighted sum? Turns out we can, and that is the message passing neural network framework, where now you're not just taking averages, weighted average of neighbors. Now the receiver is participating actively in computing what is the data that gets sent to it, right? So you first have this message function, which takes the features of the two connected nodes and computes a vector telling you what is the data being sent along this edge, right? Once you compute all of these message vectors, you have a mailbox of different things. You have to somehow summarize that mailbox. So you have your aggregation function, like anything permutation invariant, like summing, maximizing, averaging, that takes this bag of messages and just gives you one aggregated message. And finally, your update function takes the node's previous features, the aggregated message, and updates the features into a latent space. And the only parametric parts which get optimized via gradient descent are these two functions, so the psi and the phi functions. And you can imagine those are just any single or two-layer neural networks, like, say, this multi-layer perceptron with the ReLU activation. And this whole function is fully differentiable. You can stack many layers, optimize with gradient descent, much like you would do with any other type of model. OK, now, this is a super generic layer, and many different lines of research basically ended up discovering it from completely different perspectives. Probabilistic graphical models, interactions in physics, you name it. And here is just a small list of papers that you might want to read if you want to get a feel for how message passing as an idea developed from 4 completely different directions, including structure to vec, which tries to represent them as a probabilistic graphical model, and interaction networks from Pete Battaglia and others, which tries to study physics interactions and basically derives an expression like this as a way to model forces between particles. OK. So hopefully this gives you a nice whirlwind tour of different ways in which graph neural networks can be built. You will build a lot of these for yourself in the tutorial later today. I'd like to dive a little bit into the topic of computation graphs with you right now. Okay? And specifically, so far, I've always said, you know, our graph neural network modifies the features, but it leaves the adjacency matrix alone, right? We've basically assumed that we have this ground truth, optimal input graph, and you will never, ever need to modify it. I hope you agree with me this is far from an innocent assumption. Let's try to unpack why is it not an innocent assumption. First of all, even if you have graphs that are perfectly correct, they might still be a really bad idea to use them. I hope at least some of you are computer scientists by background, so you might have heard about the various algorithms for checking whether pairs of nodes in a graph are connected. And you know, this is an actual graph where I might be querying whether pairs of vertices are connected, so it's a correct graph. It's perfectly correct. But I hope you can see how I can be really adversarial and give you a long path where your GNN will need linearly many steps to figure out if these two nodes are connected. But for the computer scientists in the audience, you probably know that I can reorganize which edges I take into a so-called disjoint set union data structure and basically reduce the number of layers needed from linear in n to the inverse Ackermann function in n, which is basically less than 5 for all astronomically valuable numbers of n, right? So, you know, the takeaway from here is it doesn't even matter if the graph is correct. Sometimes it's just a bad graph, and you might want to use a better one. But then in the real world, perfectly correct is a super rare thing. I mentioned in the beginning molecules as atoms connected by chemical bonds, right? You know, perfectly correct for the task you want to do often becomes a problem when you scale up these inputs. And one of the problems that graph neural networks have tackled in the recent past are protein folding problems. Proteins are really huge molecules that kind of fold in on themselves in 3D space, and suddenly, you know, the protein is like a polypeptide sequence. It's a relatively linear molecule, right? But suddenly when it folds, things that are super far away in the molecular formula end up becoming really close together in 3D space, and they're going to interact, right? So suddenly the molecular graph, which, you know, we know from chemistry is a really good approximation for what's happening in the physics of the molecule, suddenly it stops being such a good paradigm for modeling these kinds of inputs, right? And you might want to change what is the graph you're using even in those cases. And also, I want to stress some graphs are just really, 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 really bad in the sense that I can't even fit a good neural network on the training data when I have graphs like this, let alone generalizing better to test data. And one specific example where graphs are really bad is if your graph has bottlenecks. So if you have this is a so-called barbell graph where you have two cliques of tightly connected nodes, and you have just one bridge edge connecting the two of them. I hope you can agree with me on a high level, you can read this paper for more proofs on this, that this poor edge is under a lot of pressure, right? If you want every node from here to be able to communicate to every node from here, basically this guy over here has to act as everybody's postman, right? It has to accumulate all the possible things you might want to send from here to here. You can actually prove that as the size of the cliques grows, the vector size you need in this edge grows exponentially. So it basically becomes practically impossible to learn useful functions on graphs like this. Okay? So hopefully with these three items taken together, I hope you agree with me, it might be a good idea to reconsider what our edges are sometimes, right? To rewire our graph. So how do we do that? Well, one option is we can just decide to be lazy and assume there's no edges. Like if I don't know what are good edges, I'll just assume there's no edges, end of story, right? You end up with a graph that looks like this. It's a very simple graph. Every node just talks to itself. All nice, right? Your neighborhoods are just the node itself. And you can show that actually all graph neural networks over that particular graph reduced to the so-called deep sets model, which was published at NeurIPS in 2017. It's a pretty simple model, but quite powerful for the right kind of problem. Okay, so if one option was to assume that there's no edges, can anybody give me another option? All of the edges, right. So let's assume rather than being pessimistic, let's be lazy. Let's assume everything is connected and let the poor model figure out by itself what's important, right? And here, if you do averaging style GNNs, they're not going to be more expressive than deep sets again, so we need to step it up and use attention, like we described before. So now your neighborhoods are the sets of nodes. This is the formula for an attentional GNN. I want to ask the audience, does this equation look familiar? Do you know some model which has an equation like this? Exactly. This is a transformer. So a very interesting takeaway from this is that transformers, the natural language processing model, are themselves graph neural networks operating over a fully connected graph, or in case you're using GPT rather than BERT, fully connected causal graph, right? And using the attentional flavor. Now, note that it being a graph neural network would imply its permutation equivariant, which sounds a bit weird because the inputs are text and there is a sequence. Well, think again, how are those positions embedded into the model? You have position embeddings, which is like a side channel information, and the model is not always under a requirement to use that information. The actual operation of computing attention is a graph operation, not a sequence operation. And we'll see in a bit why this is a pretty important thing to keep in the back of your minds. And you can see attention is basically inferring the soft adjacency matrix, but in a way that very easily scales over dense matrix products. And therefore, one way I like to think about this is that transformers are the GNNs that are presently winning the hardware lottery, which is basically saying that they are the class of GNNs best aligned with GPUs and TPUs and similar accelerators we have today, because you can implement all of these fully connected attentional mechanisms just by using dense matrix products. This is a very beautiful connection that I don't have enough time to tell you about more, but if you want to read more about it, Chaitanya Joshi wrote this beautiful blog post, literally titled Transformers or Graph Neural Networks, so it's not hard to find, and it will tell you a lot more, going in depth into the equations of the models to show you how the two are perfectly aligned to each other. Okay, two other things you can do. So these are just assuming no edges or all edges. These are lazy or pessimistic approaches. You could instead decide to take some edges, but not all of them. So let's imagine I have some starting graph. A non-parametric rewiring method is just some algorithm which will change the edges in my graph to something hopefully a bit more favorable. Now note this one doesn't have any parameters, so it only depends on the shape of the graph, doesn't depend on your features. Of course, you can also do parametric rewiring, which we sometimes call latent graph inference, where now your rewiring method depends on your features and has parameters. But generally, this is much trickier to optimize than the non-parametric one, because now you have to backpropagate through a discrete decision. Yeah? And as a result, non-parametric rewiring methods are actually the most popular recently. And they're also quite popular with design of transformer attention masks and similar things. I don't have a lot of time to tell you about non-parametric rewiring, but I will quickly tell you about some of the key approaches in recent years that have been pitched in this space. So first, you have basically 3 broad classes of options on how you can non-parametrically change the edges of your graph. The first one is to just use diffusion, in the sense that, OK, you assume that your input edges are already reasonably good, and you might just want to add some extra shortcuts to allow you to jump quickly to other parts of the graph. So what you do is you basically take different powers of your adjacency matrix and you add some thresholding operation to kind of learn this, to have this new graph, which is a bit more broadly connected, right? And this is something that's super elegant and versatile. So as long as your input graph is already good, this typically will make it even better. But it relies on a very strong homophily assumption, which means that it basically assumes the edges are good. It assumes that the things connected with an edge will share the same label, right? My friends will like the same things that I like. This is often a really good assumption, and it's the reason why you have scalable GNNs in so many industries. But sometimes homophily is not a good assumption. Sometimes, I'm very active on Twitter myself. People, I retweet their posts. Sometimes I agree with them, but sometimes I absolutely disagree with them and I want to argue with them. You shouldn't classify as the same way in that particular case, right? So sometimes this is not the best idea. Instead, we might want to try to do a more smaller scale change. So something that maybe won't change too much the semantics of the graph, but just improve the bottleneck properties without harming other things. And one landmark paper, which was one of the best paper awardees at iClear 2022, was this idea of you can relieve the pressure of the different edges in the graph by basically imagining the graph as a discretized version of a more complicated manifold. Now, I won't dive into Ricci flows here. I don't know much about them, and we don't have 2 hours to talk about them. But I hope that you can sort of understand how a graph like this with a sharp bottleneck relates to this kind of manifold with a very tight bottleneck, and how a graph with a bit more relief on that pressure looks a bit more normally behaved, right? And you can actually quantify this level of bottleneckness using the notion of curvature. And negative curvature generally tends to correspond with bigger bottlenecks. And therefore, in this particular paper, the authors just find a way to compute the Ricci curvature on a graph and then hunt for edges with the most negative curvature and add some extra edges around it just to make the pressure easier, right? OK. The third option, which is my personal favorite, I'm biased because I worked on it myself, but basically, I feel like we do a lot of these like surgical changes, but we don't really know what we're doing. If our main aim is to get rid of bottlenecks, why bother looking at the input graph at all? Let's just go brutal and generate a graph which we know is good, right? A graph that's sparse, that carries information very efficiently, and then you just iterate one layer of GNN on your original graph, one layer of GNN on that good graph, and so on. It turns out these kinds of really good sparse graphs are well known in mathematics. They are known as expander graphs. There are known methods to construct them. And you can see this here is an expander graph. Every node is very sparsely connected, has only 4 neighbors, but information travels really quickly in those graphs. You only need like log n steps for information to mix perfectly. And actually, with this kind of method, we just took a usual code base of a baseline GNN and we replaced every second layer to go over a graph like this rather than the input graph. We immediately gained improvements in test accuracy. So, and this graph has nothing to do with the task you're trying to solve. So it points to something quite interesting. OK. I want to close off by talking a little bit about large language models. Because as we discussed, transformers are graph models, and therefore you'll probably find a graph somewhere. From what I've seen in the recordings, you've already gotten an introduction to autoregressive LLMs yesterday, so hopefully this will feel relatively familiar. Let's say we have a text, a house of, and I want to continue it to be a house of cards. We have our embedding layer, which gives us the embedding of each token as a vector. And then we alternate 2 types of layers. We have a feed-forward network, which moves our features into some higher dimensional space, usually by some deep multi-layer perceptron. And then we have this causal attention, right, where you update the embeddings of each individual token by taking into account all of the tokens that came before it, but not the tokens that came after it, because that would make it very trivial to predict the next token, right? And then from each one of these embeddings, you predict the next one, and you supervise the system to be better at doing that, right? I hope you agree with me that there is a graph in here, right? And when there's a graph, I become happy, and I find some interesting things to study there. Turns out these graphs are really, really bad graphs from the perspective of bottlenecks we talked about before. And to understand just how bad they are, I'm not going to quiz you. I'm going to ask you something just to get a feel for the temperature of the room. If you've already seen this paper, please don't raise your hand. So I'm going to ask frontier LLMs, Gemini, ChatGPT, Claude, and so on, what is the last, so I'm asking it not to copy a whole thing, just copy one digit. So I have a bunch of ones followed by a 0, and I have a 0 followed by a bunch of ones. I'm asking for the last digit or the first digit. In both cases, the answer is 0, right? And I'm increasing the number of ones and checking when it's going to break. Question for the audience. Which one of these two do you think is harder for the language model? Raise your hand if you think it's harder to predict the last digit. Okay? And raise your hand if you think it's harder to predict the first digit. Okay. A lot more of you have said it's much harder to predict the first digit, and as you might expect, the majority is wrong. You know, like, you try to anthropomorphize these LLMs, and you think they'll make the same types of mistakes humans do, right? Because for us, it's obviously easier to predict the last digit. Therefore, for an LLM, it should be the same, right? No, actually, the models collapse way, way sooner on predicting the last digit than predicting the first digit. And turns out, if you understand graphs, it will become very obvious why that is. But at least initially, this is quite counterintuitive. Now, the reason why, I'm just going to skip right to the answer for why this is happening. The reason for why it's happening is because of this causal structure of the computation graph of transformers. Basically, all the paths you need to predict the next output must cross in this final layer of the final token. And this is the only information that predicts what comes next. You're compressing this whole wealth of information into just a single vector over here. And this, I hope you can agree with me, allows me to construct basically families of inputs where eventually I'm going to have two different inputs where the last token gets so close together that the model is going to be unable to answer differently for those two inputs. Specifically, it will stop being able to answer differently when the gap between the two vectors goes below machine epsilon. For those of you not familiar with numerical methods, machine epsilon is the smallest number that your computer can reliably represent. Yeah? Computers don't represent real numbers. Computers only represent certain rational numbers, and they don't represent them evenly well, right? And the moment your representations of the last token for two different inputs fall below that machine epsilon boundary, the model won't be able to tell them apart. It will have to have the same probabilities for both of them. And indeed, we observe, this is in Gemma models, as you increase the number of ones in a sequence, the gap between the final token embeddings in subsequent vectors approaches this machine epsilon for B float 16, which is a dashed line here. Okay, so this explains why the models will fail eventually, but it still doesn't explain why the first digit was so easier to guess than the last digit. But now you have this graph in front of you. I'd like to ask the audience, does anyone have an idea why the first token is much easier to predict than the last token? Sorry? Exactly. So I'll let LaTeX do this for me, right? I've literally just asked LaTeX to color each path from the early token using a light blue and each path from the late token using a light red, and it mixed the colors by itself, right? It's pretty obvious. The number of paths for earlier tokens grow exponentially compared to the paths for later tokens. It's most bad for the last token, which has exactly one path. So if you have a loss of information anywhere in that last path, tough luck. You're not going to be able to predict that. The modern LLMs are topologically predisposed to predict things at the beginning better than things at the end. And in fact, you can even prove that in the limit, if you have an infinite layer LLM, the first token will be the only thing that matters. All the other tokens will disappear. And we've explored this in this nice paper showing how transformers can't really see well without their glasses. So, so you might want to do things to get them glasses. This was a paper we published at NeurIPS a couple of months ago. And we now have follow-up work, which basically shows that if you change something about the graph structure of that feed-forward graph, you might be able to give transformers a bit of glasses here and there. And this was actually work I've done in both of these papers. We collaborated with João, who is one of the organizers of KHIPU as well. Okay, so this is all the technical content I wanted to show you. But now I hope that at least some of what you heard has made you excited or made you want to know more or potentially even get in on the action yourself. So here's a few pointers if you want to get in on the action. Of course, we can discuss later on, and there will be a tutorial, lunch breaks, everything, right? So first of all, if you want to dive into graph machine learning and you don't want to bother writing out all these equations in matrix form in kind of raw NumPy or something, or raw PyTorch, you don't have to. There exist bespoke graph neural network libraries for all three of the basic frameworks. So you have PyG and DGL for PyTorch, you have Spectral and TFGNN for TensorFlow, and you have Giraffe, our own JAX graph neural network library, which will be the framework of choice for your tutorial later today. If you need good data, good machine learning requires good data, there's some really good data sets of various scales that you can explore. The Open Graph benchmark from Stanford has a diversity of drug discovery benchmarks, topic classification benchmarks, product user co-purchase graph predictions, stuff like that. And I'll also call out the TU data set for its historical significance and benchmarking GNNs, which is a more limited resource competitive programming style approach to benchmarking. If you would like to contribute with your original research in graph machine learning, I warmly invite you to submit your contributions to the Learning of Graph conference, which was successfully held over the past couple of years. And in the next year, it's actually going to be the first time we're going to do Learning on Graphs in person in, I believe, in UCLA in the United States. So yeah, if you want to work more on graphs, here is a very great venue to consider submitting to. And I think with the deadlines when they're going to be, probably if you start now, you'd have quite a bit of time before you'd have to submit some work. And lastly, I believe that in Chile, there are some really fantastic ecosystems. As I mentioned, this is my second visit to Chile. The first time I came was partly by invitation of Pablo here, who basically leads world-class work in graph machine learning here in Chile. And also Mircea Petrache, who also had a chance to interact with a fair bit, does some really exciting work on geometric deep learning. These are the people I've interacted with the most, but my general takeaway is the environment here in Chile is really conducive to fantastic GNN research. So if you're a local student, maybe reaching out to some of these people might be a great way to get started on some interesting problems. And lastly, I hope you like football. I certainly like football. In fact, I originally come from Serbia. One very popular movie we have in Serbia is Montevideo, Bogtevideo, which depicts the travels of the Yugoslavian football team to Montevideo for the very first Football World Cup, when some interesting things happen on our match against Uruguay. But anyway, but basically, people in my country are really proud of sports, of their sportsmen, and I grew up watching a lot of football. And one of the most fun projects I got to do at DeepMind was to use these graph neural networks and geometric deep learning to actually power football analytics predictions in a way that actually could benefit the football club. We've developed this together with Liverpool and published it in Nature Communications. And if you want to stop by the Google booth at 3:30 p.m., I will be telling you all about it later today. That was my last slide. As I mentioned at the beginning, everything is connected. So I do hope that we'll also have a chance to stay connected today throughout the day. And afterwards, you have my email, you have my webpage here with all of my social media. If you have any questions now, later, or at any point, please don't hesitate to reach out. I hope you've enjoyed this as much as I've enjoyed putting it together. Thank you all so much. Muchas gracias.
Wow. That was a good talk. So let's do, so we are kind of late for lunch. So Peter is going to be here. He's going to be at the booth. So let's take one or two questions, depending how long it goes, and then you can talk to Peter at the coffee area.
Hi, thank you for the amazing talk. So I wanted to ask, what are the assumptions for the leak prediction problem that you mentioned at the beginning? Can you comment a little bit about that problem and how it's set up?
Mm-hmm. So the question is about assumptions concerning the link prediction problems. Did I hear that correctly? Yes. So basically, that's a really good question because the picture I showed in the slides here is a little bit of a naive representation, given how much time I had for individual parts. Like, the pictures assume that you just take the features of the two nodes and you predict like a 0-1 label, and that's it for whether a link exists. But in reality, you have to be a little bit more careful depending on the class of GNN you use to make sure that you won't hit issues because of the model's equivariance, and also because two different parts of a graph that structurally look very similar might end up classified the same just because of that structural similarity rather than actual feature similarity. But the way it typically works is you have some equivariance mindful way of extracting features of your nodes, and then you can compute something like a dot product or similar between the two embeddings. And then what you do is you push the embeddings of all the links you do have to be positive. You push the embeddings of randomly sampled pairs to be far apart, like usual negative sampling idea. And then, you know, some pairs will be officially negative, but the model will not be able to push them apart. And those are the pairs that you declare, those are the new edges or possible candidates for new pairs. So that is, to expand a little bit, this is what the link prediction setup usually looks like in practice.
Last question.
Hi, thank you. I'm working with networks in epidemiology, genetic distance between viral sequences. And when you show this expander thing, I was wondering if it could predict directionality of an epidemic, because that's one of our biggest problems.
So this is a very interesting question. Interestingly, I started my PhD looking at some network science projects also studying epidemics. So I know a little bit about the basics of like the infection models, but not too much. I do think that the use of expander will be able to help you see things that the observed graph won't necessarily be able to tell you, right? Because you have contact networks for epidemics of the people who, you know, declared it and for whom you knew the entire travel history, but there's so much factors that you won't be able to see, right? And generally, a good assumption when you have things you can't see is that you should have some template that allows the model to kind of discover those connectivities by itself. And yes, I would fully agree with you that like using an expander template or a fully connected template, if you can afford it with the number of nodes you have, depends on the surface, I guess, that you're modeling. It will definitely help you to find connections that with the original graph you wouldn't be able to, because probably there's going to be some bottlenecks in that graph, biases, because, you know, clicks of people, you know, you tend to be friends. If you're someone who like reports a lot of this data, your friends might be of similar mindsets and also report a lot of that data. But if you're someone who, you know, doesn't trust vaccines or whatever, you won't report this data, your friends will not report this data, so you'll have a very interesting bias effect in the network. So this will try to correct for that, I would say.
All right, well, let's thank Petar once again.
Thank you all so much.
Guys, small announcement. So we delayed until now, but then the postponing that. Thanks.
Ey, dos. Ey, ey, ah, ey, ey. Ey, 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 ey. Hello. Prueba de audio 1, 2, 3. Prueba de audio 1, 2, 3. Prueba de audio.
2, ¿no?
Hello. Okay, we are starting with the afternoon session. Great. I know there is still people in the poster session, but we have to start now. Okay, so in our, oh, it disappeared? Okay, I think it will come back at some point, I hope. There it is. So for today afternoon session, I'm really, really happy to have here Ira Tena from Google DeepMind. So Ira completed a doctoral degree in medical image computing at Imperial College London, where we actually met, and since then we are really good friends. She is a staff research scientist at Google DeepMind, working on robust and safe AI with a focus on generative models. Previously, she was a senior machine learning researcher with the Cortex Applied Research Team at Twitter UK, and she was also an EMBO fellow at MGH Harvard Medical School. Her research has been featured in The Economist and the BBC, among other places, and she's passionate about community outreach and increasing diversity in technology. So I'm really, really happy to have her here, and yeah, I hope you will enjoy the talk on diffusion models.
Thank you, Enzo. Very excited to be here today and introducing you to the fascinating world of diffusion models today and the various applications that they've unlocked in the past few years. So back in 2020, diffusion models were a niche interest on the fringes of generative modeling research. But today, they are the go-to model for image, audio, video generation, and have started having much broader impact beyond just media generation in fundamental sciences. For example, beyond models like Stable Diffusion and VIO, samples of which you can see on the slide, diffusion models can be employed in drug discovery, for example, to predict the binding structure of a small molecule ligand to a protein. And here you can see samples from very popular models like Stable Diffusion, Imogen3, VO2, and Runway as well. But let's start with the structure of this lecture. First, I'm going to introduce some fundamentals around generative models. Then I'll mention the basic principles behind diffusion models and talk about how we can train such models and sample from them. I will also cover how people tend to evaluate these models at scale, given that human evaluation is very expensive. And lastly, I will cover an application of diffusion models in safety-critical applications, and one such application in healthcare, and how they can be used as a learned augmentation technique to improve generalization capabilities of discriminative models. Let's start with some fundamentals. What is generative modeling? Generative modeling has to do with trying to learn a model that approximates a data distribution P of data. This is intended to summarize all the information about a data set at hand with a finite set of parameters, P theta of X. So let's assume that we want to learn a generative model of cat images that you see on the top right corner. What you see at the bottom right is a simplified version of what I described earlier, where we have a model family and its projection in 2D space. And we try to identify the model parameters theta that will make the observed data most likely to incur under that model distribution. In other words, we try to learn the parameters of the model within this model family, such that the model distribution P theta of X is close to the data distribution over cats in this instance. Now, why do we want to do that in the first place? One reason is that we can generate new samples that are similar to our data without having access to our data necessarily. We can also evaluate how likely data is under P of X, but also use them for other tasks, like, for example, classification. Now, back to the original formulation, our optimization problem can be framed as a minimization problem, where we have some measure of distance between the two distributions, p data and p theta, which is the one that we're estimating. And we try to identify the parameters of the model that minimize that distance. The distance between two probability distributions can be, for example, Kullback-Leibler divergence. One challenge with this is that X is often high dimensional. So, for example, even if we are looking to capture the distribution over images that are relatively small, so for example 128 by 128 pixels, the dimensionality of X is already more than 16,000. So learning such a data distribution is difficult, and we need to make some simplifying assumptions to tackle it. So in terms of the classes of models, there are two primary classes of generative models, conditional and unconditional. Unconditional generation allows us to generate samples that look like random samples from the training data that our model was trained on. So that means that we have no conditioning signal, as we often call it, that guides the generation or any other additional context like label, style, text, description, etc. In conditional generation, where there's like one schematic example here, on the other hand, we have a conditioning signal, which can be a class label, for example, a dog or a butterfly, when we have a model that has been trained on, for example, species labels. And alternatively, it can be text tokens, so some representation of text that we can use to condition our model, or it can be other priors, for example, a shape prior, which serve the purpose of improving the fidelity of the generation. So in general, having access to some priors is beneficial, and there is a spectrum in terms of how much information these priors carry. Before diving into diffusion models, I want to set the scene and talk about a couple of other classes of models that were prior to those and were kind of dominating before diffusion models took over. So starting with a more commonly used one that you're probably familiar with, autoregressive models. They are very popular, and one type of such model is very prominent today, and that you're probably all familiar with, is a transformer. One nice thing about autoregressive models is that they do not apply any restrictions on the type of the underlying distribution. Instead, there is an assumption about how the distribution is parameterized. In particular, we assume that each dimension is sampled sequentially and conditioned on the dimensions previously generated. The joint distribution then that you can see on this formula here can be written as a product of the conditionals for every dimension. Hence, the dimensions need to be sortable in some way. The motivation for that is that modeling the conditional is easier than learning the joint distribution. This also allows to parallelize training, which is the case in transformers, and it can also be more memory efficient. In terms of how this conditional distribution can be parameterized, we often use a neural network to approximate it. And in terms of how we can train such a model, then the objective, we normally use maximum likelihood estimation, which means that we're trying to maximize the likelihood of each sample in our data set under the approximated distribution. And we sum over our examples. And here I'm showing some generated synthetic images from an early version of an autoregressive model, Pixel CNN, from back in 2016. So you can see where image generation started from and how it evolved over the years in the next slides. So an alternative approach to generative modeling were generative adversarial networks. They were pretty like the go-to class of models until diffusion models came into the picture.
And they were actually framed quite differently. So instead of explicitly modeling the data distribution, what we do instead is train a model that approximates it by posing training as a minimax game. And there are two components in this minimax game. There's a generator, g of theta, and then there's a discriminator, d of phi. And the two have competing objectives. So what the generator is trying to do is maximize the log likelihood on our training data, while the discriminator is trying to distinguish between real and generated samples. So the two objectives are competing against each other. The generator is trying to produce as faithful and possible synthetic examples to fool the discriminator, and the discriminator is trying to tell apart real and synthetic examples. Now, some challenges that emerged with generative adversarial networks that were introduced back in 2014 are due to this minimax game. So because of this kind of zero-sum game between the generator and the discriminator, the optimization procedure can become quite unstable, and such models can be hard to train. At the same time, there's a potential for mode collapse, which limits the diversity of the generated samples. And finally, they can be difficult to evaluate as well. But then we can see that already by 2019, the quality of the generation using big GANs improved already quite a lot compared to what we saw with Pixel CNN. Now, given all this and other classes of generative models that I'm not covering in this lecture in the interest of time, but variational autoencoders, normalizing flows are classes of models that you should be familiar with if you're interested in the space of generative modeling. What are some desirable properties that we want? One is using flexible models to parameterize a distribution. So for example, being able to take full advantage of deep neural networks and their expressive power. Another aspect is proper probability evaluation. And this is important for example, to perform outlier detection or for model compression as well. But most importantly, we want to ultimately improve the generation. And that doesn't necessarily only mean obtaining better samples, but also having more control over what we generate. So these are all desiderata that diffusion models fulfill. So let's start with the intuition behind diffusion. Let's recall that in statistics, we often work with simple distributions, such as the Gaussian distribution. So instead of learning to model the full joint distribution over our data, what we can do instead is divide the problem into easier sub-problems. In particular, we can learn a transformation from an easy-to-sample distribution, such as Gaussian noise, to our target data distribution. So what diffusion models do is that they offer a general framework for learning such transformations, essentially. This is what a diffusion model does. The trick that they use is reducing the problem into a series of sampling problems from a distribution P of X. And we can construct a sequence of random variables by successively adding independent Gaussian noise with some small-scale sigma that you can see here at the bottom. So this is called the forward process of diffusion. So as you can see at the bottom, which is one example in one dimension, we add noise over the course of t steps, and the probability distribution over our data becomes flatter and flatter at every step, which means that it starts to look more and more like noise. So we are flattening out the peaks of the distribution. And note that the index t here is not referring to the dimension anymore, as it did for the autoregressive models,
I presented earlier, but is referring to the time step in the diffusion process instead. So here's how the diffusion process looks in 2 dimensions. So we start from x null, which is our clean image. In this instance, we have an image of a cat. And then we use a noise schedule sigma t to control the rate of corruption during the course of the diffusion process until we eventually turn our image into noise. So unlike the previous formula, we add the scale alpha t to our original clean image for practical reasons in order to avoid the variance exploding and growing uncontrollably. So this formula on the right shows how we can get from the original image to a noisy image at some intermediate step t using this noise schedule. And another way to think about this is that xt is essentially a linear interpolation between a sample from a Gaussian distribution and a sample from our data distribution x0. And the choice of alpha t is essentially determining whether the variance will explode. In this particular formulation, where alpha is the square root of 1 minus beta squared, it is variance preserving, and this is exercise you can take home to prove. So this is an interesting exercise. So we learned how to noise images, but what we're actually interested to generate new media or new structures is reverse this process. In order to generate an image, we need to run the diffusion steps now backwards. This means that we need to learn a generative model for the conditional distribution pxt minus 1 given xt. So this is easier than sampling from the target distribution in one step, and this is what diffusion does. It also becomes simpler if the per step noise sigma is sufficiently small. So eventually, this sampling process is reduced to a regression problem where we try to estimate the level of corruption that was applied to produce this noisy sample. So for a small eta, and the diffusion process defined in the previous slide, the conditional distribution itself is close to a Gaussian distribution. And here is a summary in one slide of how this process works for 2-dimensional images with denoising diffusion probabilistic models. You can see that starting from a clean image on the left-hand side, we progressively add a fixed level of noise over a number of steps t. In the reverse process, which is also referred to as sampling, we perform denoising, meaning that we gradually remove noise from our signal. So what we do to train for training these models is at each step we sample a time step t that is between 1 and the maximum value t. Then we add noise given our noise schedule and produce a noisy image xt from x0, which is a clean image. And then our objective is to predict x null, which is the clean image, given xt and the time step t, by gradually removing noise from the signal. It is worth noting that the higher the number of diffusion steps, so the higher the value of t, the capital T, the easier the problem becomes because it gets easier to learn the reverse denoising process. At the same time, this comes at the cost, sampling cost or inference cost, as we call it, which increases the more steps we use to noise our images. So there is a trade-off that we need to strike between the two. In terms of training a diffusion DPM model, we sample a data point from our original training data set. This is our first step. And then a time step t uniformly between 0 and 1. So we can normalize the time step t, where at time step 1 we have the most noisy image, at time step 0 we have the cleanest image. We apply the noise schedule to obtain our corrupted x. Then we can either try to predict the noise. In this instance, we have a neural network, f theta, that is predicting directly x null, so the original image. But alternatively, we can have a different objective that predicts the noise. So if we have prediction for one, then we can always convert it into a prediction of the other. In practice, though, they aren't exactly equivalent because the choice of parameterization does affect the relative weighting of noise levels in the loss, which is quite important. But once we have trained a model, then they are equivalent. Another benefit of predicting the noise is that the learning objective becomes simpler and has better stability during training. Now, in order to sample from such a model, we start from Gaussian noise with variance sigma q, and we repeat the denoising process for delta t steps. That is, we sample from that distribution and then progressively remove the noise predicted by the model, given the output of the previous step and the time step t. And then this is a Markovian process, meaning that we need to denoise the previous step before we move on to the next. So we've covered denoising diffusion probabilistic models, but one issue with them is that the sampling process can be quite slow due to its Markovian nature, meaning that every step is conditioned on the previous time step. A large T capital allows the reverse process to be close to Gaussian, so that the generative process molded with Gaussian conditional distributions becomes a good approximation. This motivates the choice of large t values. For example, one typical value is 1,000 for the time steps. Now, what they proposed in this paper called Denoising Diffusion Implicit Models, they introduced a more general formulation that includes DDPMs for a certain value of sigma t. Additionally, if sigma t is 0, the forward and backward processes then become deterministic. And what that means is that starting from the same original noise leads to the same output image. However, the training objective of DDPM remains the same for any of the values of sigma, which means that the model trained on the original DDPM process can still be used by any process by the family. So our neural network first predicts the noise, and then we use it to derive, so the noise is epsilon theta of xt in this formula. And then we use it, we repeat, we interchange between the two steps that I've highlighted there. First, we use the noise to derive x null from our current xt, possibly with a large error. And then we use the same predicted noise to add to x null, and then go back to a noisy image, but that is less noisy than the previous step. And this is how we can resample essentially the space. So let's make this a bit more concrete. Let's assume that we have a diffusion model trained with 1,000 diffusion steps, and then we start with sampling from step 999. We predict noise with our model, and then we use this predicted noise to make a prediction for x null, which is pretty bad to begin with. But then we take one step. Using this value of the predicted noise, then we take a step in the direction pointing to xt again. So we go to step 799. So the image still looks quite noisy, a bit less noisy. It's hard to discern with just like bare eye. but trust me, it's a bit less noisy than the one we had before. And then we use this new noisy input to make a new prediction for x null. And now our prediction is a bit better. Then we take another step towards xt, and then we move to step 399. So we repeat this process, x null gets a bit better, and then we repeat this one more, and then eventually our final prediction improves. So the higher the number of steps that we use, then the better the quality of the x null prediction. An alternative formulation that people have proposed involves predicting the scoring function, where p of x is a probability density function, so what you can see on the right-hand side. The scoring function is the gradient of the density function with respect to our random variable x. So notice that the gradient is taken with respect to the random variable rather than the model parameters theta here. So what you see on the plot on the right is the density and the scoring functions for a simple 2D Gaussian. The density function is color-coded with darker colors corresponding to areas with higher density, meaning higher probability. And the scoring function is the vector field, so the arrows that you can see. And that gives the direction in which the density function grows more quickly. In this approach, to sample from a diffusion model, we follow this process. First, we initialize the input to random noise, and then we iteratively denoise the input by taking steps in the direction of the score function, meaning the direction in which the log likelihood function increases the fastest. We make sure to add some noise at every step in order to avoid getting stuck in the modes of the distribution. The scoring function points towards higher probability, so it helps reverse the diffusion process, which flattens out the probability as it runs forward. And on top of that, the score function preserves all the information about the density function. Now, one way to improve the quality of generation is classifier guidance. So the only ingredient that is required to turn an unconditional diffusion model into a conditional one is a classifier. If we have access to a differentiable discriminative model, P of C given X, this is our discriminative model, predicts the probability of a class given our input, then we can compute the gradients with respect to our input as well. With respect to the generated x. So then once we have a classifier, then all we need to do is to compute the gradients of the log probability of x given that class. So in order to know how to move in the space, in order to make our sample look more like it belongs to that class, then we use the sum between the gradient of the log likelihood plus guidance scale, the factor gamma here, multiplied by the gradient of the classifier. And this classifier is applied can be applied at any step. So it's not applied on the clean images necessarily. It needs to be trained with a diffusion model, which means that we cannot use off-the-shelf classifiers for this because they need to be trained on noisy inputs. So this is kind of one limitation. But we use the gradients that flow from this discriminative model to update our diffusion model as well. So now, what is the effect of this guidance scale? So I'm showing for a textual description, panda playing a guitar, and starting from a value of 1 for the guidance scale. you can see that as we increase guidance scale, then the effect also increases. And the images become more crisp. But beyond a certain point, then images are too saturated. So we need to find like a good value for the guidance scale. Now, because of this issue that I mentioned with classifier guidance, which is that we need to essentially train a separate network on top of our diffusion model on the noisy inputs, classifier-free guidance came to the rescue to solve that problem. And what it does is it removes this reliance on an image classifier, but still allows us to steer the generation towards a conditioning signal. Rather than sampling in the direction of the gradient of an image classifier, we can feed the classifier signal into the sampling process by leveraging the Bayes rule. So on the right-hand side, you can see how the conditional of the generated content given the class can be phrased as a conditional of the class given our generated content and P of X divided by P of that class. And then eventually, if we apply the log and compute the gradients of that with respect to X, we find that the conditional score is essentially the sum between the classifier score, which is what we want to estimate, plus the unconditional score. So we remove the classifier now, and what we do instead to obtain this classifier score is we randomly drop the conditioning while training the diffusion model. So we essentially mix the score estimates of a conditional and unconditional diffusion model. So it's a difference between the two scores. We achieve that by jointly training essentially the conditional and the unconditional models. So we obtain the conditional score while applying the conditioning, and the unconditional score by dropping the conditioning, and then that gives us the value that we're interested in without having to use a classifier head on top. So this is the most popular form of guidance used in models today, by the way. Now, one issue that we haven't touched on so far is the fact that diffusion models are quite expensive to operate in pixel space. So imagine that nowadays the images that are generated are over like 1,000 by 1,000 pixels often. So that's very expensive to do in pixel space at such high resolution. However, visual perception works differently at fine scales and larger scales. And it is not necessary to model all possible realizations of particular textures, for example, with our diffusion model. Instead, we can use an autoencoder to compress our input, and this is what they do in the CVPR work, where they propose to use an encoder to downscale the images to a latent space, and then use this latent space with any kind of conditioning. It can be a semantic map, it can be text, other representations, or other images, to condition the denoising network before decoding the clean latents back to the original image space. So we start at the top, we encode our image, and then arrive at X null in latent space, and then in the reverse process we apply our conditioning before reversing back with the decoder. So that makes diffusion a simpler and less memory-hungry task. Now, for text-conditioned diffusion models that are very commonly used today, we assume a training pair of images X and their corresponding captions Y. And we have a contrastive clip model that is trained on noisy image embeddings in order to learn joint representations between image latents and textual descriptions. A clip text embedding is then fed to an autoregressive or diffusion prior that produces image embeddings ZI conditioned on the captions, the input captions Y. And then this embedding is used to condition a diffusion decoder which produces the final image. And note that this clip model is frozen during training of the prior and the decoder. But eventually, to obtain our generated image conditioned on the captions, then we use the product between the prior and the decoder. Now, what is learned in this latent space? What is it really capturing? Is there something that is semantically meaningful, is the question. And this example shows that if we interpolate between the clip embeddings of two images, we have a painting on the left of Van Gogh on the left-hand side, and then we have an image of two dogs on the right-hand side, and then we interpolate between the two in the clip embedding space. And then what we observe is that the images that emerge when we decode with the diffusion model maintain both content and style from both of the images. Another nice piece of work that I wanted to highlight is work on representation learning, because we've talked a lot about diffusion models for image synthesis, and what can they do in terms of representation learning. So this work that was published at CVPR last year showed that you can actually do quite a bit. So the model, this SODA model, which is the bottleneck diffusion model, incorporates an image encoder which distills a source view into a compact representation that in turn guides the generation of related novel views. The authors show that by imposing a tight bottleneck between the encoder and the denoising decoder and leveraging novel view synthesis as a self-supervised objective, they can turn diffusion models into strong representation learners. And here I had the video of interpolating between latents that is not showing up, unfortunately. What they do then is they apply layer modulation, which means that they partition the latent vector Z into sections. And then they use each set to modulate a pair of layers, which then promotes specialization among the latent subvectors. And then you can see on the bottom right that just like light rays refracted through a prism, they are encouraged to capture different visual traits at different levels of granularity, like pose and structure at internal layers, and color and texture at external layers, and object details somewhere in the middle. So we go from like coarser to final details depending on where in the decoder, which representation of the decoder we're looking at. So, and now some examples of recent image and video generation models that have been developed at DeepMind and released late last year. So you can see that compared to the very original pixel CNN samples that you saw, these models have advanced quite a bit, and they can produce both like cartoonish but also more photorealistic images. So unfortunately, yeah, videos are not showing up, but I'll save this for the end. So beyond media generation, diffusion models have had various applications in fundamental sciences as well. So GenCast is one such example, and it was used to produce probabilistic weather forecasts. So instead of operating in pixel space, GenCast is adapted to the spherical geometry of the Earth and learns to accurately generate the complex probability distribution of future weather events given the most recent state of the weather as input. Other applications include protein structure generation and modeling docking. Now, one topic that is not often mentioned, I guess, in the diffusion lecture, but I wanted to highlight that because because I spent quite a bit of time on it myself, but also because I think it's quite important to understand what are like established metrics of generation, showing what are the limitations and what are kind of more recent approaches to scale evaluations of generative models that are primarily diffusion models. There are some commonly used metrics that are looking at just the images alone. So such image quality metrics are threshold inception distance, for example, which provides a symmetric measure of the distance between two image distributions in the inception V3 latent space. And this FID metric requires a reference set, which is normally ImageNet or COCO 2014. The inception score also relies on a feature extractor, and then what inception score is measuring is basically mapping the generated images through inception V3 image classification model, and then the goal is to maximize the metric is maximized when the inception V3 model confidently predicts a single label for each image. So we want low entropy essentially on the logits of the inception V3 model. Another aspect of the image generation that we are interested in measuring is diversity. We're not only talking about diversity in representation, but it can be diversity with respect to color, with respect to shape, material. Is a very complex kind of concept to work with. There's various works out there and metrics that are often used to measure diversity. FID is one such metric. It captures both fidelity and diversity. Then there is the Venn score that relies on a feature extractor, but then depending on what this feature extractor is and what it has learned, it can give you very different results. So this is something to also be mindful of. And then there are alignment metrics that are looking at primarily for text-to-image and text-to-video models. They're looking at overall alignment. CLIP score is one such example that uses a vision transformer backbone. And one limitation with CLIP score is that it may not capture fine-grained details of images well. And then there are other metrics like visual NLI that require fine-tuning for a particular application. So as diffusion models have become more omnipresent, it is important to characterize their capabilities or skills. And one ingredient that we need is, first of all, to elicit these skills in order to be able to measure their ability. So what that means is that we need to curate a set of user instructions or prompts that elicit those skills from the model. And what we did in this work is that we looked at some classes of skills that we want diffusion models to be good at, and these include things like attributes, like for example style or material. We want diffusion models to be able to capture those properly. They involve relationships, spatial or scale related, like is one object on the left of another object, or is one object smaller than another one, and other capabilities like text rendering and counting. So for counting in particular, is quite a challenging skill for generative models today. So they still struggle to generate the right number of objects, and depending on what these objects are, it can be particularly really tricky. So they really struggle with eggs. Hard eggs are fine, boiled eggs are a bit more tricky to generate. So yeah, if you take a look at this work that was published at NeurIPS past year, it really dive deeper into how we can evaluate numerical reasoning with a range of tasks, looking at exact quantities, approximate quantities, and more complex reasoning, like, for example, fractionals, parts of a whole, and so on. So the first step is listing the behavior, so developing the benchmark. The next step is obtaining some golden annotations, right? So in order to obtain good quality annotations, we need some human annotations normally, and we need a good template to collect those annotations. And for image text alignment in particular, we looked at 4 different ways, 4 different templates of doing that, starting with the Likert scale, which is commonly used in behavioral science, and a score of 5 indicates strong agreement that the generated medium and the text align, while 1 indicates strong disagreement. Then we have more fine-grained annotations at the word level, like if we have a description of an image, like a cartoon cat in a professor outfit writing a book with a title, what if a cat wrote a book? You can see that for model 1, it's not a cartoonish image, so this is like an element of the user instructions that is missing, while that is the case for model 2. Then we can use generated questions that annotators then can respond with yes or no, whether that element is present in the generated content. Or we can look at overall side-by-side comparisons, like which generated content we prefer. So what we did in Gecko is, once we had a way to elicit the behavior, a way to obtain the golden annotations, then we wanted to develop a metric that allows us to then measure image text alignment or image video alignment at scale, and without having to constantly rely on human annotations, especially when we want to compare multiple models, or if we want to choose checkpoints during the model development cycle. So it's a 2-step process. First, we generate, using an LLM, pairs of questions and answers. So the answers are the expected ground truth, given the textual description, to the question that has also been generated. And we do this with few-shot prompting. And then we have a visual question answering verification step, where we feed the generated question and the generated image, and then we check with the verifier whether the response matches the expected response given the prompt. So given a textual prompt, a dog is to the right of the cat, we would expect a dog to appear in the image. So if the answer of the VQA verifier to the question, is there a dog, is no, that means that this generated content, piece of content, should obtain a low score. This is kind of the intuition behind. And then what we found was that by using this approach and comparing 6 different pairs of models that are kind of state of the art, with such a metric, we could get almost perfect agreement with the ground truth human annotations using the templates that I mentioned before. While for the CLIP score, which is very often the one measured in text-to-image generation models, that was not the case because it misses on many of the fine-grained details. We applied this to video models as well, and again, there is this two-step process of the QA generation and VQA verification, and the findings were very similar when we compared to the human ground truth and the gecko metric. So last but not least, I would like to talk about how these advances in generative AI can have impact on safety critical applications like healthcare. I'm talking about a project that we published last year at Nature Medicine. So the main motivation of the project was actually challenges that arise in real-world deployment. Two of the most significant challenges have to do with, on one hand, distribution shifts. So models that encounter a new label distribution in a new domain, or a different demographic distribution, or shifts that have to do with the acquisition protocol, for example, scanner type or imaging procedure, or in the capture process, like user captured versus clinician captured. And then another challenge is subgroup disparities, or what we often refer to as like fairness. So these arise due to non-uniform distribution of sensitive attributes, which can be age, ethnicity, or sex, and lead to imbalanced and unfair performance outcomes. There have been several works out there that have explored such bias and fairness issues of data sets that are commonly used in the medical community, but also models that are very commonly used. And they've identified the performance disparities for like chest x-rays, for example, for certain demographic subgroups or intersections thereof. In this particular work, they identified female, young, and black patient subgroups that were underdiagnosed, meaning that the classification models were more often predicting healthy status for patients with underlying conditions. Similar issues can arise in, for example, in dermatology, where if algorithms have been more often exposed to images, for example, of younger individuals. And how do these biases emerge? Here are a couple of scenarios that have to do with like prevalence disparities, for example. These arise when there is like a causal pathway between the sensitive attribute and the prevalence of the disease. And this can be through a fair or an unfair pathway. In those instances, we observe individuals belonging to different subgroups being represented with different prevalence among the targets. So in the fair example, age is clinically recognized risk factor for Alzheimer's disease. In the unfair example, a patient's race is spuriously correlated with the disease prevalence due to disparities in access to healthcare. So this is an unfair pathway, and this is kind of something that we would like to fix. Then there's presentation disparities that have to do with causal pathway between the sensitive attribute and the disease-related physiology. And there we can observe individuals belonging to different subgroups presenting different disease features for the same underlying condition. And then these can arise through fair pathways, for example, in the case of breast cancer manifesting differently in men and women, or due to natural differences, or in an unfair case, patients in different locations are scanned at different stages due to inconsistent, for example, referral policies, and that can cause presentation disparities. So in our work, what we proposed was to leverage all labeled, weakly labeled, and unlabeled data to train diffusion models with label and property conditioning. And then once we've done so, we can use the conditioning and sampling strategies as levers that can help downstream classification models become fairer and more robust to distribution shifts. Then we can sample images according to a fair distribution and create a more balanced synthetic data set. And eventually, we can combine this synthetic and real labeled data sets to train more robust medical classifiers. So the sampling approach, we found it was expected, but also empirically we found was very important to obtain good performance. And here I'm just showing an earlier work that used the glide model to generate with text conditioning some kind of domain-specific models, like in different medical contexts, like histology, X-ray, MRI. And then you can see that there is some understanding of domain, like medical knowledge, but they are overall like pretty limited without proper fine-tuning and conditioning. So they're not really like at a state where we can rely on them. So we need to properly train models for those purposes, which is what we did in these settings with varying complexity, starting with the simplest one in histopathology, then radiology and dermatology, where as we move to the right, they become more challenging because there are high-resolution images that need to be generated, and the shifts are more complex as well. But what I'm showing here is that in each of these three settings, and diffusion models allowed us to capture the data distribution well. And for example, in chest radiology, we observed that they would preserve the primary characteristics of the condition, like high cardiothoracic ratio for cardiomegaly, and so on. And here I'm showing that when we look at quantitatively, how does overall performance get affected by the synthetic data on the x-axis versus the subgroup performance gap. On the y-axis, we see that using learned augmentations with diffusion models can actually be quite impactful. So I think I'm running out of time. So I'm just going to conclude with this slide of like, why does synthetic data make sense? First of all, we can do better density estimation and thereby better data augmentation. But then we can also use the compositionality kind of capabilities of diffusion models, meaning that if we have observed some combination of properties, then we can generate images that look like those properties for a different label, for example. And then we also found that they allow models to generalize better, align feature distributions better, reduce spurious correlations, while producing diverse and canonical examples. And with that, I would like to conclude today's lecture, and yeah, please let me know if you have any questions. Thank you.
Okay, thank you, Ira, for the amazing talk. And covering so many different variants of these models. So is there any question? I think we have time for one, or maybe there. Yes, there. This is the only mic. Okay. There is another one. Can you bring it there? Okay, go ahead. It's turned off.
Sorry about that. So it's not exactly a new idea, but recently there's been a lot of work using diffusion models for text generation, in particular the Latent team in China, and also Inception Labs released a coding assistant that basically use transformers with diffusion rather than autoregressive models to generate text. I was wondering what your thoughts are about that direction.
Sorry, can you repeat the question, because I'm not sure I heard it.
Yeah, the question is, there's been some recent work on using diffusion models for text generation.
For text, oh yeah.
I mean, I've used the models, they are amazingly fast. They're not as good as the autoregressive models. So I was wondering what your thoughts were.
Yeah, I think this is like a very promising research direction. I think it's still at the more kind of early stages, but it's definitely, yeah, in terms of like reducing the inference time is one of the main challenges, I guess, there. And then once that is solved, I think there's a lot of promise for diffusion models in text generation as well.
Now it's me. Is there any other question there? There, yeah, okay, cool.
What would it be challenging applying GANs for microscopic imaging of those samples, for example, with parasites?
Hello. The question is, would there be challenge in applying GANs for microscopic images of blood samples? For example, for parasites identifications applications? It is safe? Is safe?
Is the question if it's safe to use generated images in the medical setting? Am I getting it? So there's a bit of echo.
Yes.
So yeah, it's a bit of it's a very fair question, and the only intention with using synthetic images is this in this context is only through as regularizers, essentially. So we would not propose replacing real images with synthetic images in a safety critical domain if there are other options, if it is an option to go out and collect better data. But what this approach that I presented was trying to achieve is, given that you have a lot of unlabeled data anyways, then how can you make the most of it, and how can you capture the data distribution better and potentially interpolate between data points that you're not using with like just a label conditional model. But then using those synthetic images in isolation is not something that I would advise people to do, but is a way of essentially a controlled way of augmenting a data set. This is eventually what it comes down to.
Okay, we are already over time, so thank you very much, Ira, again. Okay, and now we are having our two sponsor talks. These are shorter talks of 15 minutes. And the first one is going to be from AMD Latin America, which is one of our sponsors here. And it's going to be given by Hernan Sanchez. So Hernan has been working in the industry for more than 40 years. And during 16 years, he was the director of content for a TV program, actually, EduHeart. But then he joined AMD in 2011, where he was leading a campaign called Tech Tour 2011, and basically helping students from 50,000 students from different universities in Argentina about AMD technology. And nowadays, he is the solutions architect of AMD in Argentina. So, Hernan, the floor is yours. Thank you.
Good afternoon, everyone. Thank you very much for attending this session today. My name is Hernan Sanchez. I'm working on AMD as solution architect. That means I need to interpret and understand the client requirements, the client ideas, and help him to size the solution. And eventually, time to time, I need to have him, to hook him when he cry, when he see the budget. Okay, okay. How many people here speak in Spanish? Please raise your hand. Oh, it's better for me. Okay, I'm switched to Spanish. Okay, thank you. Veamos. Una vez más, les voy a pedir que levanten sus manos aquellos que estén utilizando este tipo de servicios todo el día, todos los días. A ver, vamos a ver. Bien. Prácticamente todos han levantado las manos, de hecho era lo previsible, y así como nosotros, más de 8.000 millones de personas en todo el mundo están usando estos servicios. Y les comento esto porque al fin y al cabo, estos servicios, estamos viendo allí los logos bien significativos, están utilizando nuestro hardware que tiene que ver con procesadores AMD EPYC y que tiene que ver con nuestros aceleradores Instinct. Y bien, esto da a las claras cómo la industria confía en nuestras soluciones. Ahora bien, de alguna manera y en una época se hablaba de subir todo hacia la nube y de alguna forma en AMD tenemos el concepto de democratizar el acceso a la AI y tal vez algunas cosas de la nube bajarlas a tierra y llevarlas a la mano de todos los usuarios. Tenemos procesadores en notebook que tienen inteligencia artificial a través de procesadores neuronales específicamente diseñados y equipados para esto, y por supuesto hasta las soluciones más grandes para hyperscalers. Las soluciones son muy variadas, desde soluciones de productos embebidos que tienen capacidades de inferencia en detección de imágenes, detecciones de formas y que se utilizan en líneas de producción, hasta networking inteligente, por supuesto también aceleradores, tanto sea para HPC como Machine Learning e inteligencia artificial a través de inferencia y por supuesto nuestros procesadores EPYC que tienen el mayor paralelismo y que también claramente ayudan muchísimo allí. A lo largo de los últimos años AMD ha desarrollado toda una arquitectura de procesadores que a nivel de data center y precisamente para dar el mayor poder de cómputo para todo este tipo de desarrollos, hemos avanzado y al día de hoy estamos teniendo en nuestra quinta generación procesadores que en este tamaño que les estoy mostrando tenemos 192 core físicos y cada uno de ellos puede atender 2 threads diferentes. Esto nos da el mayor paralelismo, la mayor performance, no solamente por core, sino también por socket, y esto realmente es muy bueno para este tipo de tareas. Ahora bien, veamos, sigamos avanzando. En definitiva, esta última generación de procesadores tiene características que realmente destacan y que mejoran en cada una de las generaciones que sacamos al mercado. Estamos hablando de arquitecturas de Core Zen 5 la última versión de arquitectura de Core, la más avanzada, la más segura también. Tenemos algunos procesadores que están fabricados en 3 nanómetros, otros en 4 nanómetros, de acuerdo a los diferentes SKU de los procesadores. Tenemos hasta 192 core, como les decía, pero también arrancando desde 8, es decir, que tenemos una dimensión adecuada para cada tipo de requerimiento. Por supuesto, todos ellos soportan AVX 512, un tema súper importante, y tenemos algunos de estos procesadores que, a pesar de su gran cantidad de cores, alcanzan 5 GHz frecuencia, con lo cual estamos hablando de performance a nivel de CPU realmente importante. Respecto de la generación anterior, y que también ocupaba el mismo tamaño de socket y son socket compatibles, hemos mejorado un 17% el IPC, la cantidad de instrucciones por ciclo. En definitiva, esto nos permite pensar en data centers que a lo mejor están colapsados de tamaño y que requieren, ya son tiempo de ser renovados, y que podemos dar una solución donde tal vez una dimensión de 1000 servidores se puede reducir a 131, con todo lo que esto significa. Menos espacio, menos energía, menos, obviamente, presupuesto de operación, y como ustedes pueden ver, con ahorros que son realmente muy importantes y significativos. Pero, ¿qué pasa con esto? A ver, gran parte de ese espacio que hemos ahorrado y sin consumir más energía de lo que se consumía anteriormente, podríamos estar agregando 1.1 millones de TOPS y podríamos tal vez, otra opción, estar duplicando o multiplicando por 2.5 el poder de cómputo, agregando más procesadores, más CPU. En definitiva, de esto se trata la optimización energética que tenemos con nuestras arquitecturas y que en toda esta cuestión, justamente, de inteligencia artificial, machine learning e inferencia, donde, sobre todo en machine learning, requerimos mucho poder de cómputo, son factores realmente importantes. A nivel de ecosistema, digamos, olvídense de esta cuestión. Todavía hoy en día hay gente que pregunta si los procesadores EPIC son compatibles. Les recuerdo que AMD ha desarrollado el código AMD64 que permitió entonces la retrocompatibilidad, con lo cual olvídense de ese tema, no es un problema. Ahora bien, dentro de los requerimientos típicos que tenemos hoy en día, en las grandes soluciones, tenemos soluciones que requieren procesamiento de CPU, tenemos soluciones que tienen requerimientos de Machine Learning a inferencia de muy alto nivel, y tenemos algo que por ahí en el medio es un híbrido entre ambos. En todos estos casos, nuestros productos pueden tener la flexibilidad suficiente y permitir la performance que se requiere para todo esto. Pero aún así, siendo nuestros procesadores host de tarjetas gráficas, pueden brindar claramente el mejor desempeño, y es así, por ejemplo, que nuestro competidor en aceleradores, NVIDIA, recomienda también nuestros procesadores como host de nodos de GPU. En definitiva, y ya hablando de GPU, también tenemos una historia, un roadmap importante a lo largo de los años. De hecho, bien, allí arranqué con nuestra arquitectura CDNA3, pero antes de esto estaba la CNA2 y la CNA, que no tenía número, la 0 o la 1, si así quieren. Y hoy en día, esto que les he marcado allí con ese recuerdo, son las GPU que actualmente están en el mercado. Estamos hablando de nuestra serie MI300 para muy alta performance. Estamos hablando de la 325 recientemente salida y la 350 que estará saliendo hacia finales de este año. Ahora bien, vamos a ver, no todas las soluciones tienen una dimensión importante. En este sentido, quiero apuntarles allí también nuestras tarjetas del tipo MI210. Ahí estamos hablando de tarjetas que son del tipo PCI Express convencional. Es decir, si bien estamos hablando de una tarjeta de doble ancho, de altura completa y profundidad completa, pero al fin y al cabo es una tarjeta que es mucho más flexible en el sentido que no requiere un montaje especial, específico desde ya, y de hecho con su arquitectura CDNA2 y 64 GB de memoria HBM, tiene muy buena capacidad, tiene muy buen ancho de banda y muy buena performance que nos permite trabajar y resolver realmente múltiples requerimientos. Obviamente, cuando escalamos en requerimientos, en necesidad, las MI 300X son sin ninguna duda bastante más poderosas, porque fíjense, estamos hablando de 192 GB de capacidad de memoria HBM. Cuando trabajamos con modelos realmente muy grandes, con muchos billones de parámetros, el tema de la capacidad, la cantidad de memoria es sin ninguna duda uno de los cuellos de botella, uno de los puntos débiles que a lo mejor nos empuja a tener que utilizar mayor cantidad de GPUs. Bien, fíjense que aquí, en este caso, en un único chip, tener esta capacidad con esas velocidades es realmente interesante. Comparado contra, digamos, las H100, que son las generacionalmente las que debemos comparar, vemos que realmente los diferenciales a nivel de performance son importantes, son significativos, y en términos generales, cuando estamos hablando de Machine Learning, decimos que tanto nuestro hardware como el de nuestro típico competidor están en una razonable igualdad de condiciones. Pero cuando hablamos de inferencia, claramente tenemos beneficios más que significativos. Ahora bien, la 325, esta nueva tarjeta que hemos sacado, este nuevo chip que hemos sacado, fíjense ustedes, estamos hablando de memoria HBM3E. Esta memoria stackeable, allí obviamente el departamento, el stack que le hemos puesto es bastante grande solamente para que se note, pero esto nos permite tener entonces en esta tecnología de memoria pilable muy buen ancho de banda y bueno, como les comentaba, muy buena capacidad. La MI 325 tiene una capacidad de 256 GB, ahora fíjense ustedes, estamos hablando entonces de cuadruplicar la capacidad de memoria que teníamos en la MI 210 y esto nos permite una vez más trabajar con modelos mucho más extensos o por supuesto trabajar con mayor paralelismo. Todos estos chips son virtualizables y son particionables, con lo cual esto nos permite también tener múltiples instancias de trabajo paralelo. Y cuando hablamos de performance, si vamos a medirlo, por ejemplo, en FP8 estamos hablando de 2.6 petaflop por cada uno de los chips. Ahora bien, típicamente en términos justamente de performance competitiva, y en este caso estamos hablando de inferencia, y en diferentes modelos, particularmente, fíjense, Meta llama ahí el 3.1 en 70 billones de parámetros respecto de nuestro competidor, hay una diferencia de 20% y en otros modelos también diferenciales importantes. Ahora bien, estos chips se pueden organizar en este tipo de motherboards que les estoy mostrando aquí, que se llaman UVB, es un estándar de la industria, donde podemos agrupar estas 8 GPU, con lo cual tenemos entonces por cada nodo de cómputo de GPU una capacidad de 2 terabytes de memoria con una capacidad de cómputo en FP8 de 20.8 petaflops en un único nodo. Entonces, realmente, a nivel de ancho de banda, de interconexión entre cada uno de estos chips y del ancho de banda de memoria interno es realmente muy superior y esto es uno de los diferenciales importantes que podemos notar. Entonces, no solamente una cuestión de disponibilidad del hardware con más fácil acceso y sin esperar grandes demoras, sino también reducción en el costo de adquisición, en los costos de mantenimiento y mayor paralelismo. Estamos hablando de un retorno de inversión claramente más fácil y sencillo. Bien, en definitiva, todo esto hay que complementarlo también a nivel de software desde ya y tengan en cuenta que todo el software que nosotros promovemos para nuestras tarjetas se llama ROCm. Actualmente estamos en la versión 6.3 y ROCm es totalmente open source. Esto es realmente importante y está compuesto no solamente por desde ya los drivers, librerías, compiladores, herramientas y por supuesto todo lo que tenga que ver con los frameworks, de manera tal que aquellos que trabajan con frameworks van a encontrar en los frameworks más comunes, PyTorch, Onyx, JAX, TensorFlow, van a encontrar que la compatibilidad es out of the box. Es decir, cuando nosotros instalamos todo nuestro paquete ROCm, estamos instalando todo este universo y de esta manera entonces tenemos supercompatibilidad. Ahora bien, tal vez algunos de ustedes levanten las manos, aquellos que estén trabajando no sobre frameworks, sino que estén trabajando a bajo nivel. Only one, two, ok, three. Poquitos. Pero justamente ahí es donde se produce la disrupción, ¿sí? Donde tenemos la capacidad de probar cosas distintas, diferentes, no trabajar tanto en la caja, que es muy bueno porque nos permite acelerar la salida al mercado de una solución o de alguna cuestión, pero justamente para ustedes que están trabajando más a bajo nivel, posiblemente lo estén haciendo en CUDA, ¿no es cierto? ¿Sí? Muevan la mano, o así, o así. Ok, tenemos también utilidades que nos permiten convertir código y muy fácilmente, porque nuestras librerías son espejadas, tenemos utilidades entonces que nos permiten la conversión de código y muy fácilmente y rápidamente podemos estar convirtiendo esto. ¿Cuál sería ese beneficio? Una vez más, tener la alternativa de poder probar un hardware que es más asequible, que nos permite tenerlo con menos tiempo, con mayor disponibilidad y con menores costos en general, inclusive de mantenimiento, y dentro de una plataforma totalmente open source. También es interesante comentarles que ROCm, desde hace ya algunas versiones, ha ampliado el soporte y también no solamente nuestras tarjetas CDNA, INSTIN están soportadas, sino también tarjetas comunes como las que podemos tener para ámbitos profesionales o para gaming, como las RDNA. Esas tarjetas pueden ser mucho más baratas, mucho más accesibles y las colocamos en una PC común y silvestre y nos permiten con nuestra plataforma ROCm estar trabajando también con todo esto y poder pensar en desarrollos muchísimo más modestos, arrancando mucho más desde el llano. Bien, aquí les dejo y luego vamos a ver cómo les acercamos este material, pero si nos saquen foto al slide, donde tienen allí varios códigos QR para acceder a diferentes recursos, como nuestro ROCm Developer Hub, donde van a encontrar montones de información, KHIPU.AI, esto es lo que nos permite justamente, y van a tener toda la información respecto de qué manera poder convertir código CUDA en código portable, que luego pueden compilar para ser ejecutado tanto en uno como en otro hardware. También containers listos para ser usados, eso también es muy bueno. Y el de abajito, ese que está ahí, aquí van a ver dónde están los diferentes stands, están las chicas de AMD tomando algunos datos, y si no también pueden hacerlo y registrarse a través de este QR, porque hacia el final de la jornada vamos a estar sorteando entre todos los que se hayan inscrito allí una tarjeta AMD Radeon RX 7800 XT que justamente está soportada por la plataforma ROCm. Así que bueno, no se pierdan también esa oportunidad. Bueno, básicamente eso es lo que quería compartir con ustedes y sepan esto. Nuestra intención es hacer cada vez más accesible esta tecnología y que tengan opciones verdaderas para poder desarrollar todo el potencial que ustedes hacen, que hacen magia realmente todos los días. Muchas gracias.
Thank you very much, Hernan, for the presentation. You can scan the code, participate for a GPU, so that's amazing. Just, yeah.
Okay. Thanks.
Okay, and while
There's already. No, no tengo.
Okay, and so our last speaker before the break, the coffee break, is Jose Ignacio Orlando, Nacho. He's an associate researcher at CONICET. He's working with the Yatiris lab at the Pladema Institute in Tandil, Argentina. He also serves as the director of AI labs at Arionkoder through a CONICET-STAN partnership. And additionally, he is a part-time professor at Facultad de Ciencias Exactas, UNICEN, where we studied together actually. And we met there as well, friends. And where he teaches fundamental of data sciences and workshop on applied mathematics. So Nacho, the floor is yours. Thank you very much.
Thank you very much, Enzo. Thanks, everything. Not necessary. All right, so today I'm going to wear my industry hat. So sorry for the academic people, maybe you will get bored. But I would like to start this presentation by asking, especially the younglings, how many of you are consider yourselves academic persons? Raise your hand. Okay, many hands. Nice. I would also leave your hands up. And how many of you, and raise the other hand, those who are below the 50% probability of looking for a job in the industry at some point? Okay, there are some hands there. I've been there at some point. I find the way to do that. I would like to tell you a little bit about what we do at Arionkoder.AI Labs. AI Labs is basically a team of data scientists, machine learning engineers, and product designers, and we all work together to deliver value to users from different customers that we have, solving real-world challenges with machine learning. And we do this exploiting three things. Our scientific expertise, most of the people that belong to AI Labs are PhD level. A design mindset, we work closely with people from our product team designing applications that are covering the pain points from our users. And last but not least, we make use of smart engineering, which is an important part of developing tools for real-world impact, let's say. And for those who are interested in pursuing a career, I would like to say that there are lots of opportunities right now in when it comes to LLMs. And one of the things that I struggled with, I'm coming from the computer vision community, was trying to find the best way to learn all these things about large language models in a way that enables me to communicate with engineers that are working in the company. And one of the first stops that we need to make when it comes to finding that relationship or that sweet spot between one thing and the other was understanding a question that maybe the oldest in the room already have heard about in the old times of AI, but for the younglings is probably something new, which is the difference between automation and augmentation, which is an important thing to understand when it comes to user pain points and requests from our customers. So when we talk about automation, we are talking about using machine learning to replace a manual, tedious, and time-consuming task. Classic supervised learning, we have inputs, we have outputs, and we train a model to automate that process, right? In automation, we have a different mindset. We are talking about using the automation abilities in an augmentation way. So we try to help users to do the things that they do faster and more accurately using the abilities or the properties that are provided by them thanks to these automation tools, right? So most of the time, companies are looking for this. So it's a completely change of mindset. You need to start thinking about how you can use automation to augment tasks in an industrial setting. And when it comes to using LLMs, we know that the whole landscape of LLMs starts by training LLMs, doing fine-tuning on them, doing prompting, and there are many applications after that, right? So the first question comes, okay, I need to understand transformers in depth, I need to understand Q, key, V, the attention, the dot product, and all that in-depth information. And there is a good news for those of you who are coming from computer vision, for instance. You don't need to understand transformers that in-depth to already make real-world impact with LLMs, right? Why is that? Because in general, we don't train LLMs in an industrial setting. We cannot spend 6 months working with, I don't know, 2,000 GPUs training a model to make a difference. We barely make fine-tuning of LLMs. We just do that if we really need LLMs to speak a very particular language. And we can leverage lots of pre-trained models that are already available through open APIs, right? Not OpenAI, open APIs. Like Cohere models, for instance, Mistral, Mistral models, and many providers that come with their own APIs for serving with large language models. So what I'd like to focus on this presentation, and I'm going to go super fast, is which are the different applications that you could incrementally learn about if you want to pursue a career in the industry. And I will bring you some of the examples of the things that we have done in Arionkoder.AI labs for serving some of our customers, so you can see different real-world scenarios where these could be applied. And the main frameworks that you need to learn about for this particular thing are not PyTorch, not TensorFlow. You need to learn a little bit about LangChain or Llama Index, which are frameworks that enable you to interact with different LLMs in a proper manner. So let's start by LLM prompting. I guess that most of you are experts already in prompting ChatGPT when you need to proofread a paper, if English is not your mother tongue, and things like that. And so LLM prompting is clear, I guess. The idea is to instruct an LLM to do something for us. What is the approach that we usually follow when it comes to prompting an LLM? The first step is always understanding the task that we want to automate. We need to clearly identify what are the processes that are followed to automate this task, because this is going to be part of the description of the task that we are going to provide to the LLM, okay? And one important factor on that is that all these tutorials that you could see online with prompt engineering techniques, take a look at them, because they provide really useful elements for you to do that. So for example, this idea of putting at the beginning of the prompt or before explaining the task, take your time to think about the solution. It's already demonstrated that if you take that into consideration, you will be able to achieve better results. Also, the idea of chain of thoughts, like focusing on instructing step by step how to perform a particular task, that's also helpful. So you should always try to leverage those tools that are already available online. In terms of recommendations, and well, here is an example. Sorry for the squares that you see. This had to be reducted because of the information that was there was sensitive. But here is an example of how, or of one of those applications in which you can leverage LLMs. In this case, what we've been doing was taking very, very complex PDFs with contracts, tables, figures, and things like that, and we prompted GPT-4o using also its vision capabilities to extract different fields in JSON format that we could then feed inside a database, and then we could make queries out of that. So you could see that it was very simple for us, but we were able to process very, very difficult documents. Our recommendations when it comes to LLM prompting: first thing, use the vision capabilities if the content of the documents is very complex, for instance, if you're processing documents. But in other applications, you could also use prompt engineering to extract information from images as well. And last but not least, craft a data set for evaluation. We use LLMs in a zero-shot learning way sometimes, but this idea of building a training set now becomes building a test set, so we could calibrate the prompts and evaluate our performance there and repeat as many times as necessary so that we make sure that our implementation makes sense. Something more complex than pure LLM-based or LLM prompting are LLM-based workflows. This is related with RPA, robotic processing automation. We're talking here about automating different pieces of a process using multiple prompts or multiple calls to different LLMs. So the idea here is that we take a very complex process and we try to map it, for instance, using a flow diagram, something very easy to see. And then we try to identify in that pipeline which are those components that are suitable for automation using LLMs, right? So then the next step is just to write a prompt for every single one of those steps. So everything that I told you already about how to prompt an LLM applies here as well, but for each of those components that we are automating. One example here is an application that we have built for the eligibility process of health insurances in the US. You know that the health system in the US is pretty much complex than the one that we have here. And understanding how to pursue that process is very complex. So we mapped that process and we implemented all the necessary components so we can have a fully automated way of determining if a person is eligible or not for getting a reimbursement from a social security. Two recommendations here. pay special attention to the format of the inputs and the outputs, because you will gonna have many LLMs interacting one another. So in general, we use JSON format for that, and there are tools like Pydantic that enables you to instruct the LLM to use always the same format. And also craft a test set. You will hear me a lot talking about that. Then we have retrieval augmented generation. I guess that was the starting point for many of you who started to use LLMs and are not NLP native, let's say. Retrieval augmented generation is a task in which we provide context to the LLMs by doing semantic search on vector databases using embeddings that we extract from both from the query of the user, but also from different chunks of text that we extract from the databases. The idea here is very straightforward, and there is already a recipe for this. There are more complex ways of doing RAG, but in a nutshell, what we do is we take text, we chunk it in different pieces, we pass each of these pieces through an embeddings model, we generate a vector representation of each of these paragraphs, and we use that to build a vector database, and then given a new query, we try to match that embedding and see which are the closest ones. And then we use that as context in a prompt so that we input the user question, we have the system prompt, we have the user question, all these context, and then we get the answer, okay? So this is something that we have implemented. Lots of companies are trying to do that as well. It's basically a chatbot that is connected to our knowledge database. And basically, we can ask questions like human resources questions. Can I take vacations? What kind of things do I have to accomplish to get this bonus or things like that? Well, this information is already in text form in a database. In this way, you can get a natural language answer automatically. This is really nice and really fun to play around with. There are very nice videos online to learn how to do this. Our recommendations here is review carefully the quality of the data that you're using as context. We have seen that sometimes we believe that the model is failing, and it's not the model failing, but the data that is already in the database that is not very good. And last but not least, evaluate all the components. Here you have the retriever, which is the component that takes elements from the database. You have the generative component that is the one that is producing the answer. So all these components are important and you need to validate them. There is an opportunity for automation of that validation using also prompt engineering, using a second LLM as an evaluator. So you can consider that as well. And it can give you at least a clue of how accurate the solution that you're implementing is. And last but not least, we have AI agents. We're going to call them LLM-based agents because we are machine learning practitioners, so we know that there is a difference between one thing and the other. So agents are special systems. Sometimes they are confused with the LLM-based workflows, but here we are talking about autonomous systems that perceive the environment, make decisions, and take actions to achieve a specific goal based on some degree of reasoning. Here, what we use is text as a proxy for reasoning, okay? AI agents are intended for applications in which we need a lot of free will, okay? So the first thing that we do in general when someone asks us to implement an AI agent is, do you really need that level of autonomy? So for example, if you're working with a chatbot that will need to use this tool or the other based on different requests from the users, then it's important to develop an AI agent. If that's not the case and you already know that there is a sequence of steps to follow, use an LLM-based workflow because it's much easier to implement first and it's much safer, let's say, in terms of the different misusages of this. So what is our approach to implement AI agents? We first start by asking ourselves these questions, and then we identify a proper agentic architecture. You will see that there are lots of posts online about different architectures to do so. Then you need to implement the tools for this model and the perception components. And last but not least, you need to implement the system prompt. And here is an example of this chatbot. We incorporated into this solution the capabilities of querying a database. So for instance, you could ask how many people is on vacation right now, and that requires running a query on a database. So we use a specific tool for that. And when we ask a question that we could answer with our knowledge base, we use the tool for retrieval augmented generation. That's all. That's all my presentation. If you want to know more about what we do, or if you want to know a little bit more about what we do in other verticals of AI, like computer vision, medical imaging, and so on and so forth, you can stop by our booth. Sorry. You can also follow us on LinkedIn, Instagram, and X. And we are hiring, so if some of you are already curious about opportunities in the industry, there is a QR code in our booth, and I'm free to chat whenever you want. Thank you.
Thank you, Nacho, for the presentation. Okay, and now I think it's time for the coffee break, right? So we will be back at 4:15, right, Fefo? Yes, 4:15. Please be in time. We are going to have the last talk of the day, Sara Hooker. So we need to finish in time because then we have the practicals, and otherwise all the program gets delayed. Thank you.
funciona. ¿Pero esa?
No sé.
Yo sé, el solapero
Yeah, testing. Okay, perfect.
No, move it up.
Up?
A little bit up. Creo que estamos entendiéndonos.
Hello? Yeah, okay, nice. Okay, now the pressure's on. You have this big bio to read.
Maybe I can stop here.
Cut a lot earlier, yeah, please. Cut.
Okay.
If I had known it would be read out loud, I would have told Jenna to send us a version.
Yes, I was trying to talk to you before, but I couldn't find it.
Okay.
Everything is working.
They're missing one microphone. Is there a microphone here? Like one of the ones for questions?
No. Nope.
¿Dónde está el...? ¿Sí? Pero voy a ver si está funcionando el micrófono, pero dice. Este se desmutea, pero ahí está ok.
Okay, check.
Sí.
Yeah, yeah.
Yo reviso si hay que subirlo o bajarlo y detallarlo.
Okay, a little bit louder. Okay. Okay. Yeah.
Hay un agua para ti aquí.
Okay, gracias. Perfect.
Ustedes me dicen, ¿eh? Cuando la jefa diga, cuando el jefe diga y la jefa diga. So, hello, please take your seats. Welcome back from the coffee break. And now I have the enormous pleasure of introducing Sara Hooker to you. Sara Hooker leads Cohere.AI, the dedicated research arm of Cohere. And with a long track record of impactful research at Google Brain, Sara brings a wealth of knowledge from across machine learning. Her work has focused on model efficiency training techniques and optimizing for models that fulfill multiple desired criteria: interpretable, efficient, fair, and robust. Sara leads a team of researchers and engineers working on making large language models more efficient, safe, and grounded. So please, a big applause for Sara.
Good afternoon, KHIPU. Good afternoon. It is so lovely to be here, and I'm really looking forward to this talk. This is the last talk of today, so did we find the microphone for questions? We did. Where's the microphone? Okay, excellent. You are our first victim. Let's all stand up. I would like to play a short game to bond us all as a group as we go into this very serious topic. So please stretch your arms to the ceiling, to the side, to the other side. And now we're going to play a game. So it will work like this, and let's see if it works. The person who has a microphone will pass it, and as you pass it, say a language. There's only 2 rules. The language cannot be repeated. It has to be new. And we're all going to clap after each language. And we're going to see how far we can go. So let's keep it quick. Okay, so I will begin. So I will say English. Okay?
Portuguese.
Spanish. Alemán.
Korean.
Chino.
Italiano.
French.
Japanese.
Indonesian. Mandarin. Africans.
Hindi.
Mapudungun. Swahili.
I think we
Russian.
No. You get one more go. Otherwise, we have to stop it here. A lot of pressure.
Arabic.
Ukrainian.
Finnish.
Quechua.
Danish.
Indonesian.
Oh, okay. We're done. Officially 2 strikes. Thank you, everyone. You may sit down. Amazing. Okay, this was a good way to begin. I will not be talking about our work on multilingual today, but we do also have a lot of work on multilingual, so I'm happy to chat separately. Feel free to find me. We did 101 languages, so maybe that exercise highlights the complexity of getting to 101. And in general, our lab does a lot of work on just how do we make AI work for the globe, and so I'm happy to talk about it. We also just work on multimodal. We released a vision model. Oh, and the other thing I just wanted to briefly mention in case it's interesting is that we give out a lot of research grants for compute. So if people are interested, I know a lot of people are studying, feel free to also ask or talk to me about it afterwards. But today's topic is something that I've just been thinking about for a long time. And I thought it's very timely to talk about. It's this question of whether our primary ingredient that has fueled a lot of our favorite recipes over the last decade will be our primary ingredient going forward. I'm going to talk about the diminishing returns to scaling. And I will ask you a question today, which is at the heart of our field, which is bigger better? And I will also share some thoughts on how we're changing the spaces that we optimize as a field. What's interesting is that this question matters because it's informed the way that our field has been shaped. So Michael Jordan, the computer scientist, said, "I can't think without metal in my hands." And we see swag for GPU poor. We also see companies essentially assume that scaling is inevitable and state that they're going to do it responsibly. And so the implicit is that this is something which is a given, that we're going to scale and that we're going to build bigger and bigger models. It's also informed how we treat our field, like who's allowed to own what hardware, who's allowed to participate. It has meant that contributions have shifted from academia to industry. It's meant that the way that we publish has changed. it's also determined who gets to participate and who doesn't. So who gets to build the breakthroughs and who is not part of the room when it happens. And so I would say, in many ways, this is one of the most profound questions. It's impacted policy. So even the EU.AI Act executive order have this notion that there's a certain inflection point at which models have much more risk. So at 10 to the 26 flops, that's when a model is deemed risky and worthy of further consideration. And what's interesting about this is that it all rests on the presumption that bigger is always better, and that bigger, more capable models imply more risk. And so today, let's ask that together and let's think about it. So it's worthwhile starting with the role of scale and data in recent breakthroughs. So our recent period of our field and how we've built these breakthroughs seems to tell a very compelling story that bigger is better. So we see that with every new generation of model, we've pushed out this size factor. This is across modalities. So vision, NLP tasks, we see ever bigger data sets. It's also involved large increases in both simultaneously. And so we see this massive kind of expansion in both training times, amount of compute, and also the number of parameters of the models. This is captured by Rich Sutton as the bitter lesson. The only thing that matters in the long run is the leveraging of compute. What Rich is saying in the blow to every ego out there is that all our fancy, more complex approaches are not as good as simply leveraging scale. So the first question is Sutton right? Who wants to weigh in? Where's the microphone?
I forgot the question. Can you repeat, please?
Is Sutton right?
No, what he said.
He said, okay. Well, let's see, but let's also let people weigh in, and you can kind of gather as we go. Rich Sutton said, all you need is scale. So we don't bother with fancy algorithmic approaches. Just have a general representation, letting a model learn patterns for itself coupled with scaling. Yes, excellent. Okay, shout it out, and I can repeat.
So we try to do discriminative tasks, right? And we operate on the assumption that reality is discrete, like there are things that exist.
Okay.
Actually, like the data of reality is continuous. So the way that you slice a problem makes it easier to solve or harder to solve, regardless.
Yeah, this is a very nice insight. Part of what you're talking about is our search space, right? So like there may be certain things that we know a lot about, and we've sliced it and diced it and created features for, and have a lot of domain expertise. You may even be able to get away with maybe statistics there if it's well represented enough, if it's well defined enough, and we have enough previous historical behavior of how it behaves. Nice. So I think that's a point saying Rich is not right, correct? Okay, I gathered. Okay, what else? Who wants to take the point that he is right? Oh, courage, come on. There's many people who think that he just won a Turing. Okay, who thinks he's right? Let's at least do a hypothesis. Why could he be right? Okay, go ahead, excellent.
Well, I guess you could, like if you could train the machine enough, you could argue that they can generalize to learn everything if you give enough.
Yes, this is a very nice point, right? Like let's say that we have, normally in machine learning we assume we have access to a sample of the underlying distribution. But if you have all the data in the world and it's well represented, then yes, the model could learn if you train long enough, if you have enough scale. So that's fair. That's like interesting, yeah. Okay, what else? Why else could he be right? Excellent, yes. You can shout it out as well.
I think Sutton is partially right.
Okay, excellent.
Maybe he's telling compute as a consequence of having a lot of data. But we care more about information than data. And one evidence of this is that we have to filter a lot of redundant data before training a data set. So maybe he's partially right because we need a lot of compute if we have a lot of data, but maybe if we find a way to actually have more meaningful information, we will have more efficient models in the end.
This is excellent. So this is a point which we'll talk about later, which is that you know, this notion of scaling and more compute, by delegating representation to the model, we're saying we don't actually want to specify how features are extracted or what's extracted. And what I think Omar is suggesting is that because of that, we scale way more the compute because we may be throwing in junk. So we can get to that later. Yeah, that's interesting. Maybe one more point here. Who would like to speak? Excellent. Yes. Yeah.
Usually brings improvement. Thanks.
It's okay. I can repeat if you continue.
Right. I think Sutton's partially right. Right in the sense that scale usually brings improvements in models. Not right in the sense that we shouldn't bother with algorithmic improvements. I think those two axes are somewhat orthogonal. So given any amount of compute with better algorithms, we can achieve better performance. And also the other way around. Given some algorithms, we could scale them up and achieve better performance.
Yeah, very sensible answer. I love this one. It was very, yes, okay, nice. I think what you're saying is for a given amount of compute, we can use it in, from ways which range from poor to excellent, right? So given a fixed amount of compute, how we use it is interesting. But more compute, we could always fill the space of like available use cases, even if we make it more efficient. Very fun. Okay, let's go for it. So there is an argument in favor of this approach, and I'm surprised no one said it. Evidence. There is really all the breakthroughs over the last decade or so have been us throwing compute at the problem. So this is a very compelling reason we should pay attention to this. And it's a very simple formula, which also, I think, appeals in some ways. But we see this in many ways. We see that size often kind of confers different properties. We can disagree about what they're called. There's an active debate if they're really emergent or surprising. But there's no denying that we see large differences between scales. So like even quantization sensitivity changes a lot above 7 billion parameters than it is below. And so we see a better propensity to model and more fluid responses for generative models. We also just see simple differences, like for instruction tuning, this idea of few-shot performance really depends on scale. So you can have good zero-shot performance, however we define that. It's kind of also an active debate whether anything is truly unseen. But we can have better interpolation properties if we're above a certain scale. So this again suggests that scale is important. If you look at Chatbot Arena, so the best models, so it's quite interesting because the model which reveals its parameter size, it's the best, is DeepSeek, but even that is very hefty, so 685 billion parameters. So this is very large models that are dominating the top of our leaderboards. And what's interesting is that a key limitation of this approach of just throwing compute into, oh, and by the way, one of the reasons I would argue this is very favored is that unfortunately, even in industry labs where a lot of the computers, you have quarterly bets. And it's very easy to say, let's throw more compute at it. It's much harder to say, let's revisit some of the core building blocks of our algorithms. This is interesting because it still doesn't address one of the core limitations of this approach, which is that we don't actually know that much about the relationship between parameters and generalization. And there's a few data points I'll share here. So models at the same performance are getting, at same parameter size, are getting better over time. But also, small models frequently outperform larger models. So all models over 13 billion are in the gray. And then the best daily model is in green. So this is the open leaderboard on Hugging Face. And it shows that we see more and more large models over time being outperformed by the best small models. We also see this with our work. So IXpanse outperforms far larger models. We even amplified this with Aya Vision. So we outperformed models 11 times its size. So our model outperforms Llama, which is 90 billion. And what's interesting about this is that this is part of a larger picture where we have actually a very highly uncertain relationship between compute and performance. Why? And maybe I'll share some data points. So one is what was brought up actually during our discussion. So this idea that data quality compensates for the need for compute. So we find that repeatedly, if you remove low quality data, you can arrive at the same level of performance using less data. So things like deduplication, pruning, more highly optimized estimation of quality. We released work, I think a year or so ago, which was led by Max Marion. So this shows we extended to pre-training at scale, and we use very simple estimators to remove the majority of data. And what we find is that you can achieve the same performance while training at as little as 30%, and this is at pre-training scale. And we also show this for even annotation. So if we prioritize where we apply human annotation, we can achieve the same performance and avoid ties much more effectively. But, but we also see this in the fact that the relationship between weights itself is not well understood. So diminishing returns to adding parameters. So this is an old school example. So we saw this in computer vision, which convolutional neural networks saturated on many of the tasks that we use to measure progress. This is inception V3 versus V4. So you double the number of parameters from 21 million to 41 million, but you only see 2 percentage points in accuracy. And this is an example for convolutional neural networks, but arguably, we see the same now. So recent releases are often 11 times the estimated parameter count of previous ones, but there's a noticeable shift in the expectation of what gains can be achieved with transformer-style architectures. There's also redundancies between weights. So researchers, this is a very nice paper. Nando's on this, nice. I knew it was one of it was one of the early papers from Misha. They find that you can predict the values of the weights in the network using a tiny holdout, so just 5%. And furthermore, like if we need so many weights, why can we get rid of them all afterwards? So we did this very nice landscape survey on sparsity. A lot of my earlier work was on sparsity, and you can achieve incredibly high levels of sparsity without giving up performance. What's interesting about this is that what it suggests is all these weights are mainly needed to condition your optimization space during training. And afterwards, we can get rid of it. So in some ways, this is telling us we're bad at optimizing. And once you realize that, you start to think, wow, we're really inefficient in how we train these networks. And a lot of this is because we've chosen empirical risk minimization. So we optimize for average error. What this means is it takes more capacity and longer training to learn. And the majority of features are learned early in training, but we spend massive amounts of the training period learning these rare features. I did a lot of work on understanding the role of capacity. So what do we learn as we vary the size of these networks? And what we find is that actually the majority of weights are used for a tiny slice of the distribution. So when you remove 90% of weights, what you lose is the rare examples in the data set. Put differently, we're using the majority of weights to encode a useful representation for a tiny slice of the overall distribution you care about. I have some examples here. Who wants to guess what this example is? Disk. This is a toilet seat. And here I have another example. So this is scale independent. It's not impacted the performance as you vary the size of the network, but this is scale dependent. What about this? Beer. This is espresso. And then this is maize. What about this? Women, perfume. Plastic bag, nice. Who said bag? Excellent, yeah. What about this? Star Wars, okay, actually very worthy guess. Yep, cloak. So you may have gathered these are very difficult examples, and this is what you lose as you vary capacity. We did other work which shows the learning trajectories, and most typical examples are learned extremely quickly at the very beginning of training. In fact, most of our pre-training compute, these massive amounts of compute, are learning the long tail of examples. And we see there's two types that we rarely distinguish in machine learning because we don't treat source of uncertainty. So we have both atypical and noisy examples, which have very different sources of uncertainty. So one is reducible. If we have enough examples of something atypical, we'll learn it. Another is noisy. It's irreducible. We just have to remove it. But right now, all our ways of addressing this really struggled to differentiate. And so some of this early work was trying to leverage patterns and loss trajectory to try and identify different signatures for these different examples. The other thing that is interesting and which really causes chaos with our ability to understand the relationship between compute and performance is the role of architecture. Why would architecture matter? Who wants to jump in? Okay, Enzo, go for it. Nice. Excellent. Inductive bias. What do we mean by that? Like, what's an inductive bias of like some of our popular architectures? Okay, excellent. Said like he's taught a computer vision course. Excellent. Nice. I don't know if you're allowed to answer. Bravo. Yeah, what else? So I think what we had there was some of the properties of convolutional neural networks. Nice. What else? Okay, excellent. Yes, this is another one. So these are really nice because they allow extraction of features more efficiently. So convolutional neural networks really reduce the computational costs because of this. Yeah. What else? Oh, excellent. Two hands, side by side. Let's go. Okay, you go first.
Frequency bias.
Oh, tell me more. What do you mean by frequency bias?
Well, especially in vision, lower frequencies are learned earlier during training.
Bravo. Okay, I do love that. Very timely. Nice chime in. Yes, I mean, because of our objective functions, you know, it's interesting though, because that's a property of deep neural networks and our loss functions. Yeah, it's very interesting. I think we haven't merged beyond that when we've gone from convolutional networks to transformers. They're both characterized by this. We're still doing, oh, okay. Oh, okay. Wow. That was very different. Okay, excellent. I'll go with this one. So yeah, I think that's a very nice example that's characterizing all our deep neural networks. And in general, any optimizer that is leveraging a kind of batch aggregate loss function. Nice. And then to your, yeah. Yes, so you're getting to the heart of the question of why this matters. So why architecture is being one of the most fundamental shifts in our scaling properties. That's why no scaling law could have been predicted before convolutional networks, and no convolutional neural networks scaling law could be applied to transformers. They fundamentally change a search space because often they're changing the properties of scaling and changing the efficiency of doing so. Yeah, anyone else want to add to this prior's conversation? I think it's very important because I actually think we forget how heavy our priors are. Like something like tokenization, extremely heavy prior, right? We're representing all of our input space in a way that's already quite dense. So we've made a decision about how to represent it. Language itself is a heavy prior, right? What have we, it's dictated by our communication rate. So most languages have the same rate of communication. And I think that's often forgotten is that the way our data is represented is really a prior of our physics and our limitations in ability to process different inputs. For example, all audio data that is recorded to be deemed worthy of recording, it's mostly in the frequency that we can hear. And it's very interesting because even cameras process images automatically before we even process them to make it look like how we see the world. So priors, we talk about it in architecture, but it's very heavy in the data space as well. This is a very worthy conversation to have. Okay, any more ideas here? What are the priors? Okay, go on.
The difference between VITs and swing transformers are these swing windows to capture the hierarchy.
Yep.
Yep, this is very true. So sliding window attention, this is very interesting, and this is getting at, different context lens. It's really unlocked a lot of our ability to do that. Okay, so this is important. I think that, so much of what's interesting to think about is that we really adopted neural networks based on empirical success, but there was a long body of work which led to that. And we've already talked about some of these aspects, but one of the critical reasons why this was able to process a high-dimensional input space, so images were traditionally thought of as so high-dimensional that most of the work in the 2000s was about feature reduction. So handcrafted features like Sobel edge filters that would try and reduce the dimensionality before you even process it. And the reason why convolutional neural networks were effective is that they made it more efficient to extract features. Shared weight, so we've talked a little bit about this, but the shared weight kernels mean that you can apply the same filters across an image, which makes it very efficient. Pooling operations, so this is notoriously something that Jeffrey Hinton is very cross about, and he always says it's really unfortunate that it works so well, and so it stuck around. Because if you think about what a max pooling operation is you basically only take the maximum value and you discard everything else. So it's incredibly hacky, and it's shocking that it works, but it allows us to dramatically reduce information and makes it way more efficient. And then also hierarchical feature extraction, which we've gone in a few places, but each subsequent layer kind of builds. So you see different features emerge. And so, for example, early layers of the network are known for really being edge extractors. I think this is much more clear in convolutional neural networks even. And then we see transformers. So we see self-attention mechanism, the parallelizable nature. So it scales much better. And that's one of the reasons, even for vision problems, a lot of people have switched to transformer because of the scalability, which is interesting. It's actually not clear. I think there's very fun work to be done there in the future. And then the lack of recursion. So because of this ability to extend context, you gain a lot. And so I would argue that it's both algorithmic and also architecture innovation that determine the rate of return for compute. And this is what the very nuanced comment at the beginning was getting at, is that it's this rate of return that matters. So for a finite amount of compute, you want to understand how much do I get back in performance. And this means that compute alone does not dictate the pace of progress in our field. And what's often missed in this statement is that architectures to date have very much dictated both that slope as well as the ceiling. And it's very interesting to think about that because it's the most important prior in conditioning the search space available. And so this will lead nicely into what we'll talk about next, which is what now? So where do we end up? So I may have convinced you that we are now in a period of decreasing returns in compute, but maybe I don't have to. I think all I have to convince you of today is that it's very expensive to follow our current optimization protocol. So even if we're not in decreasing returns, the amount that we pay for increased performance is very high. We're paying a lot to learn rare and atypical features. And as a point of comparison, our brain is incredibly efficient. So we run on the energy equivalent of an electric shaver, and that's because of key choices that embed efficiency. So there's pathways which allow us to combine certain inputs with higher efficiency. For example, it's much easier for you to walk and talk than walk and read. We also are very good at certain tasks and very bad for others. Like we're very bad at sequential processing. As much as we love chain of thought, we like it because that's how we have to think through difficult problems, not because it's inherently the way that these models should think through difficult problems. I think my hot take is I think chain of thought is a temporary Band-Aid because it's really just trying to mimic something where these models are already very good at parallelizing a lot of these challenging questions that we have to do sequentially. And then we simulate a lot of what we see. So unless I move, like now, if I stay still, you're probably simulating it. You're not doing a full forward-backward pass, which is very energy efficient. And we have log-scale vision, so you won't notice unless I do something sizable. And there's a reason for that, because we don't want to absorb all the information around us. We want to prioritize. We also, and I think this is often very much underestimated as a factor of our intelligence, are able to perturb our environment. We have movement. So if I am not sure about something, I can walk forward, I can pick up, and this gives us a very good calibration of uncertainty. And we use this all together, which for most of computer science history we haven't, so it's very interesting. And then in contrast, a lot of what we do with deep neural networks is painfully inefficient. So we don't have adaptive compute. We have a mixture of experts, but they're not exactly specialized. They're more like a hack for our inference budget. We increasingly also have these really tricky things where we're still seeing all examples at least once. And we use global updates. So that means that we have things like catastrophic forgetting. We forget what we previously learned in these networks. We also really have these batch issues where we're optimizing for batch performance. So where do we end up? I think here. This is the next part of the talk. If scaling is slowly dying, where do we go next? Or how do we change this rate of return for compute? I do love this quote. So what we have before us is some breathtaking opportunities disguised as insoluble problems. Oh, it's okay, I'll hold. People can take photos. I do like this quote. I think what's important to remember is that computer science as a field is very young. So it's only been around 77 years. And our pursuit as a field has really focused around this idea of optimizing an algorithm. We abstract away, in the research field, we abstract away typically the data set, and we abstract away typically the deployment, and we focus on the model. And the pursuit has always been this general, intelligent machine. And what's fascinating about that is that I would argue that within the last 2 years has fundamentally changed in a very significant way. And our tools for optimizing as a field are profoundly changing very rapidly. And that the focus is not just the algorithm. I will say that we now optimize in the data space, which has been something that wasn't possible before. But also, we are experimenting more and more with gradient-free performance boosts, meaning we don't update the weights at all. We just do acrobatics around the weights and see performance gains. This fundamentally changes how we teach computer science, how we think about our optimization tools, and our purview of responsibility as researchers. And this is fun, I would say. So what do I mean? I'll talk about all of these, but I'll start here. We have some promising directions for optimizing in the data space. One is pruning, which I talked about earlier. I would argue that this is really articulated as spending more capacity on the data we care about, trying to isolate those noisy data points and remove them, trying to, if you're able to, remove some of the more frequent and focus on the less frequent. And we've done a lot of work on that. I won't spend too much time here. But I think that that's really about addressing the misuse of capacity. We don't want to spend time on noisy data because it's not learnable, even if we throw compute at it. So it's largely a regularization problem. I would argue this is largely the issue of our pre-training. Our pre-trained models have to be massive because we're throwing the garbage of the internet at it. And if we were able to have a successful estimator to identify what was better quality, or if we were able to scale the data that we have that's higher quality later on, we wouldn't have to divide it into this hacky 3-stage process: pre-training, instruction fine-tuning, and then preference training. Because one of the key things that's varying there is just the structure of the data. And we just are trying to steer it to be more like the distribution we want to serve, and less like the distribution we have readily available. And so we've done a lot of work on pruning. I'll put this here. But here's where I want to spend time today, which is this idea of moving away from static data sets. So optimizing in the data space. I would suggest that this is very specific to this point in time. So we've largely treated data sets as fixed. Why? Why do we treat them as fixed previously? Is that a hand? No. Oh, it went down so quickly. That was excellent reflexes. Who wants to speak here? Yeah, excellent. Go ahead. Okay. One at a time. Yeah, go for it. Whoever was first.
Expensive to collect?
Yes, it's so expensive to collect. Yes. Who else? Who's going to say something next? Excellent.
Benchmarks like ImageNet, make training on ImageNet, evaluating on ImageNet,
Okay, so in what sense? Like they're expensive to collect, they're...
It's available and everyone are comparing.
Okay. This is a fun point. What you're saying is you get stuck as a research field. Yeah, why would you collect another data set when people will want you to benchmark on ImageNet anyways? Okay, bravo. This is a very nice point. This is a point I call the stickiness of science. It's why we were stuck with adversarial LP norm research for too long. Slightly cheeky side comment there. Okay, what else? Yeah, very nice. Go ahead.
Okay, so I previously worked on lower source languages.
Yes.
So in that case, sometimes, and I will say most of the times, native speakers do not agree on some things that the rest of people think they agree.
Yes.
Like
yes.
Dialects or
Yep.
definitions, alphabets, etc.
Yeah, this is actually very important as a concept, inner annotator variability. So any given concept, whether it's a single classification, discrete space, or if it's a notion of how to take on a task, annotator variability is very high. And the notion of ground truth, as we know, as a single label, is actually a myth in the real world often. So this is a very nice point. So you have to reconcile. So not only do you have to collect, you have to reconcile. What else? Maybe one more comment here. Who wants to go? Okay, I have two, so we'll do two. Nice, go ahead.
It's difficult to convince people to evaluate their models on new data sets.
Yes. Okay, so that was a nice +1. This is good. I agree. I think there's an inherent inertia in absorbing new benchmarks. We're seeing that now with language, is that benchmarks are so quickly saturating. It's making it very, people are not sure where to jump to. What will last? Yeah, okay, and then we had one more. There was someone, okay, maybe over there. Yeah, go ahead.
I was thinking it's difficult to know when you change the data set if you have improved because you have
Yes. Yeah, the lack of reference point. Yeah, very nice. And part of what you're all getting at is it's a lot of effort to create a new benchmark, right? So yeah, all this work, so the cost of annotation, annotator variability, we haven't talked about this, but there's also just difficulties obtaining some types of data, right? So there's a selection bias in who will respond or provide data. And often you end up with weird biases in what parts of the distribution that captures. But what it means was, until very recently, we were stuck with the data that was collected and with the issues of the original net annotation. So I actually did do a grumpy paper about ImageNet. This was what do compressed deep neural networks forget. We found that a lot of what was most sensitive to capacity was the incorrect examples. And so when you scale, you just memorize the incorrect. So it's very interesting. I think that this is what makes it so profound, I would argue, and there's two reasons for that. One is that it makes the label space a lot cheaper. So I've been involved with the Data Provenance Initiative. We've done a lot of work characterizing the data we have available and the data provenance. A lot of what we've relied on, because we've worked with thousands of data sets, is a combination of expert annotation and also using LLMs to provide proxies to understand the scale. But this is important because often our desires for annotation change across time. So our data sets and how they're used are not fixed, but are often revisited. I wouldn't use synthetic data yet, but I think about something like harm. I do a lot of work on fairness. And fairness is very tricky because the notion of fairness changes over time and across time. So by geography, we have different power dynamics. So in the US, there's legally protected features like race and gender, but in India, it's caste, and in Africa, it's often tribe. And what's interesting is that it's also, you can think of this as even how over time our language uses change. So if you think about your favorite comedy show or comedian from 10 years ago, if you rewatch them now, it might be a bit awkward. You know, like our humor and our boundary changes over time. And so this is why we want ways to revisit data and are more nimble and to catch things that we didn't catch before. But the second, and I think this is very important, is that synthetic data being good enough allows us to think differently about our primary construct in machine learning classes, which is sampling IID. So you sample, and it's representative of your distribution, your underlying raw distribution. And why this hasn't worked for things like NLP or for other problems is that your sample often is completely different from how you want the model to generate in the end. And so you're doing all these acrobatics after you sample to try and get it closer to what you want. And what synthetic data does, it allows us to think about strategically structuring our distribution, which is very profound. When you sample at random, you end up with all those inefficiencies we talked about. But if you target your synthetic data creation, you can start to think about the parts of the distribution that you most need to improve in. So self-driving cars is a very intuitive example of this. This is a poor Waymo that got stuck in cement. I actually love Waymo, but this one was not so lucky. But those are the type of examples that actually we want more of, because they're very rare, but when they happen, they can be very, it takes the car out of commission. There's also examples of different weather conditions. And if you can simulate more data in those parts of the distribution, you can see a lot of very important gains in performance. The criteria being you need a teacher that's performant enough. So this is Louisa. I think Louisa's somewhere here. If she, okay, Louisa's there, nice. So this is work that we did that I think is very nice, which gets at this, which is, okay, so we know now that it's feasible and cheap enough to shape the data space. How much can we shape it? Can we steer it? And so what we did was we looked at really thinking about how do we kind of condition teachers towards certain properties of the data. We call this active inheritance. And we aim for non-differentiable properties, which is also fun to think about, because so much of our optimization depends upon it being differentiable. And what we show is we can see massive gains in properties that we target. So we looked at text diversity, which means the richness of the text, so improving text richness and toxicity as well as length. And we look at passively versus actively inheriting. And what this is part of a wider body of work. This was led by Ayomide, where we strategically sample from a pool of teachers to craft the distribution that we want. And we target teachers which are good at certain parts of the distribution. And this is where I think we also start to avoid mode collapse. So properties where we oversample from a given teacher, so we just inherit passively all the limitations of that teacher. How much time do I have? Excellent. Okay, we're good. Nice. So let's talk about this gradient-free performance boost. So what is a gradient-free performance boost? Let's go. It's a bingo card. There are a few, so let's go. Who has one? Excellent. Yes, go for it. Pardon? Chain of thought. Yes, that's on the list. Yeah, technically, yeah, very nice. It's very, yeah, perfect. Yeah, go ahead. Okay. Technically, that's not gradient-free because you still need to train the model. But I have looped in some things there, like, so data distillation, so synthetic data distillation, technically you do still train, but you're sampling the entire data space and it reduces your number of gradient updates that you need. So I think that could fit into that, like low compute. Yeah. Ah, go ahead. Excellent. Yes. Yeah. Yeah. Ah. Bravo. So you're talking about applying rule-based approaches on top of models. Yeah. Yeah. So I actually think this is a very profound point because it gets to this idea that sometimes the cheapest way to address something is to apply a much simpler approach on top of a model, whether that be in the pre-processing step or if it be like how the model is presented. We see this actually with a lot of our current models. The way that they're actually hosted often involves rules applied on top of the model, very simple rules, and it's kind of fascinating to see. Like, for example, on certain onboarding flows, you'll just ask what your name is, and then that is applied as like a conditioning of the preamble. So it's not a rule, but it's a very cheap trick. No gradient updates required, but it achieves the same effect of like a big boost and like you're feeling that it's addressed at you. It's very interesting. Another rule that actually is very interesting for performance is speculative, like this idea of decoding immediately as you have tokens. So the streaming of tokens. This actually makes no difference to the optimization, but it makes a difference to how we receive the algorithm. We like to see it appear as it processes, otherwise it feels like high latency. So this is very fun. I like this point. What else?
In the case of LLMs, prompting techniques like few-shot prompting.
Oh, nice. Yes, very good. Yeah, so few-shot prompting, excellent. That's on the bingo card. Yeah. Okay, nice. We have a triangle. Go for it, João. Majority voting, very nice. Yeah, actually we see that a lot in both LLM as a judge, reward models, as well as you can imagine some of these best of case sampling methods could also be framed as majority voting methods, so very nice. Yep, okay, who is next? Yeah, go ahead.
I would say that what I would call best of kind sampling or self-consistency.
Yes, yeah, all these fall into the same nice bucket of approaches. Self-consistency is nice. What is self-consistency for people who don't know it?
It's sampling different solutions for the same problem and picking the majority of the solutions, like different solutions for different results, and the most common result would be.
Yeah, very nice. So I guess the difference is for self-consistency, often you don't need a reward model. For best decay, you sample multiple times and then you use some external score. For self-consistency, often you just measure the similarity or like you can measure some other indication and then you can go from there. So it's very nice. These are all, the cost is an inference pass, but you're not updating any parameters. Yeah, and then we had some, oh nice, okay. Ah, RAG, yes. Beam search, yes. This is very interesting. I like both these. Okay. Yeah, go ahead. Pardon? What's reflection? Ah, yes, yeah, reflection or reasoning. Yeah. This is very nice. Yeah, you can have multiple stages where the partial or critique, so another version of this. Very nice. Maybe one more here and then we'll go. RAG, this also counts. I think RAG is very nice. It's one of the examples I have as well. Yeah, so we're just seeing this. Yeah, I think here the question is, what can we do when we don't allow for any gradient updates? And it turns out a lot. And part of why I think this has been unlocked recently is that when we have generative models, it actually creates a very rich interpolation space. And there's many ways we can traverse that. And prompting has always been a very hacky way of traversing that. That's why your prompts don't work when you go from one model generation to another, because it's almost like we're tea leaf reading. We're like, what works for this particular high dimensional space? But I see increasingly that we're getting more sophisticated approaches of conditioning the space and extracting the best performance. And this is super interesting. So We have things that require some compute. So some of the most profound developments have been things like multitask, instruction preference, chain of thought. Arguably, you can either use in training or you can use it inference, reasoning. And oftentimes you need some examples to show the model to induce good behavior like this, but it's very limited. And sometimes you can just do a zero shot. So it can also be like a zero compute technique. But as was mentioned, there's even more that don't require. And I'm surprised no one said maybe one of the most, I guess, popular directions right now, but it includes things like tool use. RAG is an important one, best event sampling, self-consistency, a lot of ones which are about majority vote. I like that that was brought up. Distillation is an interesting one. I also put it here because you could use distillation and then put it in FuseShot, but it kind of belongs in between. It reduces compute costs, but if you use it for training, it's not compute free. Increasing context length. This is another profound one, right? So even RAG and introducing context length, these are different ways, and they have different properties, but they're different ways of extending your database beyond parametric, beyond weights. And then model merging and agents. I'll just point out, so we did a lot of work on model merging. This can be very effective for balancing multiple objectives. This is work led by Akansha. And this is very good when you actually have very distinct models and you need to merge the properties. And it requires zero gradient updates. So you're just merging at inference time and you can on the fly come up with a different balance of properties. There are very interesting questions about when is the weight space too different to do something like this, and what is the best conditioning of the weight space to make it a good merge, which I think is fun to think about. And then we've also done work on RAG, so this is led by another Louisa with a Z, but this is work that we use RAG to do continual learning. So I'm gonna stop here and open up. I do wanna leave one big picture idea, which is that I would argue most of our intelligence is gradient free. So what that means is that, you know, we develop as humans. We definitely, our brain develops and changes. But our intelligence as humans is not individual. I hate to crush the ego of everyone out there. But most of our intelligence comes from the ability that we are in this room sitting like this, that I'm standing, that everyone knew to arrive here at a certain time, that everyone had a notion of the nature of this discourse that we're having. And that's mainly based on our desire to belong and to really adhere to like our societal norms. It's a very collective intelligence in that sense because it makes global updates very cheap. I think that this is something that is often missed in how we framed our pursuit of intelligence, is that the notion of mimicking the human brain is actually not really the goal. But it's our collective knowledge that is the objective. And our desire to combine that knowledge, which is very inherent to how we are incentivized. And the reason why I bring that up is that I think that it's very interesting as we move into this new era of this expanded optimization space to think about these notions of units like models combine and optimize in different ways. I'll be candid, the biggest game changer is still going to come from a change to that unit. The next architecture is still very critical because it changes the rate of return of everything else. But this is a very exciting time to be working on these topics because our levers are much more varied. So I think it's very possible, and I would argue necessary, that the next breakthrough will fundamentally require a different way of modeling the world, and may require a different combination of hardware, software, and algorithm. I didn't talk about the hardware lottery here, but I think we're very much in it. NVIDIA is calling its recent line of GPUs, it's the transformer engine. So we've just doubled down and put all our poker chips on the table for deep neural networks. So hardware and software matter too. But I think that compute is the least interesting thing to throw at a problem. And increasingly, we should be asking ourselves to justify additional complexity. So I think here we can learn from hardware architects. So Moore's Law is a very nice example. So Moore's Law was released in 1965, and it was this idea that by shrinking transistors, you could double the amount of transistors on a chip. It turned into a self-fulfilling prophecy, but unfortunately, it made the life of a hardware architect extremely boring. Very risk adverse, because the whole goal was you could still get a lot of gains from transistors, and so the whole field became about pushing transistors onto a chip. One of my favorite Turing lectures is by David Patterson and John Hennessy, and the end of Moore's Law is slowly approaching. Moore's Law is something else that's slowly dying. And David said, actually, this is very good for the field of computer architecture, because life is not boring anymore. And in fact, it's the golden era for designing architecture, because there's much to do. And so I think this is a lesson we should take to heart, because this field is going to change very fundamentally and probably for the better. And with that, thank you so much. This is amazing. Thank you. So I don't know if we have time for, do we have time for questions? One, two, okay. Okay, here we go. Yeah, so I'll take the hand over there. Yeah, I can repeat it out. Oh, okay, there we go. Yeah, I can repeat it, yeah. Yeah.
Also becomes harder. So you start thinking about it, and it's like you have to take 15, 20 years of like advances in the field back and just go to the essentials again. So I think it's very scary for a lot of researchers to try and just diverge so significantly from the current paradigm of developing the field architecture.
Yeah. So I probably won't repeat that into the microphone. But I do think you're pointing out a very good grumpy point, which is that it's very hard to stray from the beaten path. I kind of got at this at the very end. But another good example is capsule networks. So capsule networks were Geoffrey Hinton's one of the ideas that him and Sara worked on, and I thought it was a fun idea because it was trying to do something different from convolutional neural networks. At least it was trying to say, well, there's some things about convolutional neural networks that are not great, that, you know, an image is still processed even though it's all still scrambled because we apply the same filters everywhere and it's still classified as an image. Another thing like this is state space models, right? So it's also doing something interesting that's different. And the sticking point is hardware, and it's because we've optimized, and frankly, I'll say more about software as well. So with capstone networks, squashing operations were a massive issue. There's a very excellent paper called Machine Learning Systems Are Stuck in a Rut. And the researchers who helped Geoffrey Hinton implement his system, because Geoffrey Hinton famously works in MATLAB, wrote this paper after having to implement capstone networks. But it was all about how our systems are broken. We've over-indexed. And the reason why is efficiency. By domain-specialized hardware, we've really indexed on one operation only. What is that? Who wants to throw it out? What have we optimized for with all our GPUs? Bravo, nice, yeah. So matrix multiplies. But I will say it's also this, it's software. And what I mean by that is that it's also very difficult to port any part of your stack right now. Like if I work on TPUs, I'm working on JAX. If I'm working on GPUs, I'm probably working on PyTorch. The portability is extremely limited, so if you go from GPUs to TPUs, you're losing automatically 40% of PyTorch functions. And then you get a slowdown for the rest. And so you're locked into a stack, which means you cannot experiment or see different patterns in your ideas. And this is equally dangerous. So it's a software portability issue too. So I don't have a response, but I do heartily +1. And I think that's a very critical problem. We are probably out of time. Yeah, excellent. Thank you, everyone. That's so nice.
Okay, I'll leave this too. I think it's not working, but...
Yeah, it was very low, right? Yeah.
Yeah, I think it guys, sorry. We are now having 2 more spotlights, and then we have some announcements, so don't leave, please. Sorry. So we are going to use this. Are you going to stand here or above? See? Okay. So. So, as announced, we are going to have 2 spotlight talks. The first one is from Rodrigo Bershai. Rodrigo, who's standing here, received a doctoral degree in electrical engineering in 2010, and electrical engineer degree from Universidad de Chile in 2003, and his master's in applied mathematics from ENS de Cachan, France in 2006. And currently, he is an associate professor of the Institute of Engineering Sciences in la Universidad de O'Higgins in Chile, where he was director of the Institute of Engineering Sciences, from 2020 to 2023. From 2015 to 18, Rodrigo was an assistant professor at the Computer Vision Lab of Kyoto University in Japan, and before that, he was researcher on Chile, Japan, and Germany, working computer vision, machine learning, and intelligent systems with various applications. So please welcome Rodrigo. Thank you.
Okay. Thank you for the introduction. So today I will talk about the research we do in computer vision in our university, in what we call RISC Lab, Robotics and Intelligent System Lab. We do various topics, but I will focus on computer vision. First of all, just to mention a little bit about the university. The university was created in 2017, so it's quite new, 8 years of age. It's located to the south of Santiago, about 100 kilometers, so quite close from here, our main campus. The university started very recently, so we are still growing, and it has a very strong focus on research. It was created because in that region there was no university, basically. Being so near from Santiago, where we have many universities, there were no university, and it is an important region in terms of economic development in Chile. So we address various topics in the lab related to agriculture, computer vision, and in particular we are working with event-based visions, And also we have some research on energy management, math education, and robotics. I will focus on the first two, because we don't have enough time to go through all of them. So first, I will talk about precision agriculture, in particular about cherry orchards, understanding that this is our main research now. So we are working on building robots. We are not there yet, but the idea is to have a robot first to understand what is happening in the field, and later maybe do some manual tasks. Now we are trying to understand what is happening in the development of the field. So why it is important in our region of O'Higgins is because the growth of fields and planted field is going up very quickly. So you see this graph here going exponentially. It's a real graph from 2000 to today, basically multiplying very quickly the volume of export with a market of over 2,000 million US dollars. And the problem that this is causing is that the price is going down and the quality is going down, because it's difficult to maintain high quality for all producers. So we want to understand what is happening in the field to help the producers. So the first thing we are trying to do is to understand the phenology and do some simple tasks. Looks simple, but they are not so simple for do it with Diffusion. So the first one is finding the fruit, finding the flowers, finding the structures in the field, and count them, understand the development, the state of development, and we want to be able to give some concrete numbers to the producers so they can take decisions and make better estimations and improve the production. So the first thing we did is to look at data sets, available data. And if you look at the data for fruit detection, for example, the main data set available is called Mine Apple with 1,000 images for detection. So it's quite small. Apples are planted almost everywhere in the world, so you should be able to get a lot of data. There was no data. So we decided to work with this data set, and also we built our own data set for cherries. This is available, it's published, so you can go out there and download it and use it for your research. This data set includes annotations at the bounding box level and segmentations. And also we annotate 3 levels of maturity, so green, orange, and red, basically 3 levels of maturity development. So we have now some data, now we can do something for the producers. In this work, we also built several detectors. We have a baseline. I will not go into details, but we are now able to build some good detectors. And also we have a paper that should come out soon when we propose some new methods, but this is not included here. With these detectors, now we can detect fruits in the trees. So if you can see, the fruits are very small, and the cherries are small, they are clustered, they are occluded, and when you have a video, you have some blur, so it's a difficult problem. And here, what we are doing in this video is detecting and then tracking over time. Here, this is a slow motion video, and the video was taken with a person moving with a cell phone in the hand, handheld cell phone. So here we can also, it's not included here, we can detect basically the trees due to the distribution of the fruits. With this, now we can send some students to the field, take many videos, and make a map. And we have the distribution of the number of fruits we see in each aisle of the field, something like this. So this is a distribution of the number of fruits in the different aisles. We are also working to bring this to vehicles, what is difficult, because we have more variability in the movement. We have jumping of frames, so difficult to associate and to do tracking when you have jumps between the different images. But we can get this kind of map for each level of maturity. So we know how many fruits we can see, the proportion of fruits in green, orange, and red level of maturity. So this is the one thing we have, and we are working with producers. They count manually. They take a tree and count how many fruit they see there. So we have some samples here, and we can cross that data with our data and better estimate, for example, the volume for the whole field. That is something we are already doing with some producers. The second thing we did is to understand the climate within the field. The common strategy from the producer is to put one agroclimate sensor for a big land, just one. So we decided to see what happens if we measure more in detail what is happening in the field. So we put, for example, 4 sensors, and we measure over a long time period, every 20 minutes, temperature and humidity. We get a time signal, and now we can build some maps. We can build some maps with the variability along time and space. For this, we use Gaussian processes. And then with this, we can have, with a few sensors, we can have a virtual sensor in every tree. So we can estimate what is the climate for each tree. And we can see that there are some differences. And this difference, I didn't include it here, but they give meaningful information for the producers about the difference of production, what is happening in one tree and the other one. How much cold this tree receives in winter compared to this other one in the same field. We see some important differences. And the third thing we did is to combine vision with climate data. So phenology with climate data, we have now a map of how many fruits we have in the field over time, and we have maps of climate. And we can combine the information, or what we did is to adjust a model to be able to estimate the maturity of the fruit in the field from climate data only. But the calibration is done with fruit counting information. Okay? So we use fruit counting, which is expensive, to calibrate our model using agricultural data. What we are doing now is not yet published, but currently working with master students is related to taking what we did already and bringing it to 3D. So we want to build maps in 3D, what is located the fruit in the different parts of the tree, and estimate better the size of the fruit, which is an important parameter in the case of cherries. This is ongoing work. The second topic I want to mention is about event-based vision. Probably some of you know this kind of camera, but it's relatively new, so I will explain briefly what is an event-based camera. We are all used to traditional cameras that take one picture. The same picture is taken at the same time for all pixels. That is how the hardware is designed for these cameras. And you have some, let's say, problems. You have some latency problems to get the data from the camera. You have blur, and you have problem of dynamic range. So you get some, for example, saturated areas in the image. And event-based cameras work independently and asynchronously for each pixel. We can see in this video overlap information from a traditional camera and an event-based camera. The event-based camera samples the changes per pixel asynchronously and independently per pixel, and give us information basically continuously over time. And so we can get a lot of information about the movement and the dynamics of the scene. You can see there the event generation model, so how the camera is sampling. Basically, the camera is looking at the change for each pixel. So every time each pixel changes, you get a signal, and you get the timestamp, the time, a very high time resolution, and you get going up or going down. So you get a kind of signal that is not an image, but a sequence of changes for all pixels, and asynchronously. So you don't know if you will get or not the information, depending if there is a change due to movement of the camera or movement of the object, or change in illumination. You see changes. This camera only sees changes. And this kind of information is similar to spikes. Yeah. So here are some examples, taking events and mapping them into images. So we take the events and we plot them as images, and you can see the movement of the hand, the movements of the blinking eyes. For example, if you want to do face tracking with event-based cameras, you don't need to detect the face. You need to detect the blinking. So there are some papers detecting only the blinking, and you track then the blinking. So you can solve the problems in a different way. Also, you can see, for example, behind the glasses, if someone is blinking with dark glasses because of the way that information is captured. So some problems we are trying to address in some specific applications. So first one is how we represent the data. So we have this kind of spikes, trends of events, they are not images. So how we represent this information to process it later. Other problems that are interesting in what kind of neural network we are using. For example, standard, commonly now a standard in our community, so artificial neural networks, spiking neural networks, or others. So we are trying to understand a bit better what is happening. So here is one example of our works. We started with some already existing problems and data sets related to gesture and expression recognition. And we took some existing models and analyzed the models and the networks and the data to better understand what we can do. And for example, we can see that with event-based cameras, this is just an example of the result. We can actually get a very good result with 10 milliseconds of data, which is much faster than traditional camera, not 30 milliseconds frame per second, no, much faster. So less than a frame, you can actually recognize what is happening with less than a frame. Another example, I will go quickly because I don't have much time. So here we do some kind of, let's say, transfer learning because we don't have much data to train the network. So we use images and events together to better learn and transfer the data from reconstructing faces and be able to transfer that to be able to classify events. So I will skip this. One more example of what we can do with these cameras. So some of these cameras include frames and also can capture inertial data. So we said, let's try to estimate depth. So you can, when you have the movement of the camera, monocularly, only one camera estimates depth. And here are some results of this kind of task. So we have a single network using frames, events, and EMU, inertial unit, to estimate at the same time a depth map of the image. And also here we can see the estimation of the pose of the camera. So how the camera is moving over time. And actually turning is quite difficult. The scale is difficult to do, but we can actually estimate well the depth. Just one more comment. We also have some research related to math education. So we are building, with a colleague from the education side, tools for helping children to recommend what board game is good for the children, for that specific children or group of children, to better understand some math content at the 6-7 years old level. And with this I will end. So we had last year sponsored by KHIPU.AI, so I want to thank for the organization. We have a summer school in robotics. We had over 100 participants in Rancagua. Here you can see some pictures. And we will have it again this year because we have a very successful project. And everyone is invited if you want to work on robotics and AI together. Thank you.
Thank you very much, Rodrigo. And now we have our second spotlight by Eric Carvajal. Eric is a researcher and professor at the Electrical Engineering Department in Universidad de Costa Rica, specialized in microelectronics, digital integrated circuit design, and computer architecture. He got his bachelor's in electrical engineering from Universidad de Costa Rica in 2014, his master's in integrated circuits and systems at the University of Texas at Austin in 2017. And this phone goes to sleep, so I can't read. Saving energy is not a good idea, sometimes. And also his PhD in computer engineering at Texas A&M University in 2021, where his research focused on the application of machine learning for hardware engineering, aiming to accelerate the design and validation of microprocessor performance. And currently, he continues working on the same line of research, but now focusing on the usage of open source tools to democratize the design of integrated circuits. So please welcome Eric, our last spotlight.
Yeah, I prefer this one. Thank you very much. Thank you very much for the space today. Today I'm going to give a brief spotlight of what we're doing in Costa Rica, specifically at Universidad de Costa Rica, where I'm working. So first, I'd like to start clarifying where I come from, because it's usually confused. Costa Rica is in Central America, which is in the center of the American continent, not the country they like to call America. And we are right there. That's not an island, just because that's also commonly misunderstood. We are not Puerto Rico, okay? Just to be clear. Okay, so that's Costa Rica, and then right there in the center is the capital, San Jose, and the main campus of Universidad de Costa Rica is right there. Okay, so the Universidad of Costa Rica is the largest university in Costa Rica. We have about 45,000 active students and about 5,000 professors. But we'd like we're starting to regionalize more in order to get to places where the university was not very active. So now we have campus like all over the country. And this is the campus, the map of the campus. It started there, that we call Finca Uno. And the university has everything pretty much. So right there we have basic science, architecture, law, economics, computer science, letters, health science, arts, education, agronomy. And just we couldn't fit anymore there. So the university started buying other fincas. So over there, that's the more iconic building we have with the sunflower mural. So that's where the humanities are taught. And over there is Finca Tres, which is the sports installation. Now we have also like a hospital, and we have odontology and human movement and things like that. And we have an ecological stadium, so that's pretty nice. And then there's Finca Dos, which I did backwards just because it's where I work in. And right there is the building of electrical engineering. And there's a lot of research centers over there. And that's the lab I coordinate, which I called Lima. So at the University of Costa Rica, as you saw, there's a lot of disciplines, and we are all pretty much in the same campus, but it's very, very big. So it's very hard to know who is doing what. And that is not very efficient, right? Because there's a lot of people that are working on their own, and they are duplicating efforts and dividing resources. So with that spirit, or with that in mind, we actually, when we heard about KHIPU.AI, we wanted to go there. So we proposed to start doing the Pura Vida AI Forum. I asked ChatGPT to do the logo, and then later someone told me that toucan is not from Costa Rica, so okay. So that was our vision, to promote collaborations and contact networks. make visible the work that we're doing at the university, even inside the university, like make it visible inside, and promote diversity of ideas. And this first edition, it was my first time organizing an event, and I really appreciate what you guys are doing because it's so hard. And so we decided, okay, let's just do it for University of Costa Rica. Let's start small and see how it goes. So we ended up with about 60 people in person, and we did a live stream, and we had 100 unique viewers yesterday when I checked. So it was pretty, I would say, multidisciplinary. Most of the people that participated were in engineering, both professors, researchers, and students. But we also had people from health science, economy, agronomy, letters, social science, everything, whatever you can think of. And then the speakers, we also had a pretty diverse set of speakers. I like to highlight some of the projects that were presented there. I'm not the expert in any of the fields that I'm going to talk, so just bear with me with the very brief explanation that I'll give. So one project was about supporting small agricultures. So it was about early detection of diseases in horticultural diseases, in horticultural. So there was, this is a greenhouse in one of on the satellite campus of the university, and they had some issues with the leaves. This is a pretty, I'll see a lot of research on this, trying to identify diseases. But the thing is, what they wanted to do is targeted towards the agricultures, right? And they don't have probably the latest high-end smartphone. They probably won't have, I don't know, access to cloud or something. So it had to be pretty low budget. So what they did is they developed a very small model and for detecting these diseases, and they were able to achieve pretty decent accuracy. Another one was for cannabis identification. This was the work that they did in collaboration with Spain. And so in Spain, there's like a quantity and variance of cannabis that you can grow. So you can't grow more than a certain amount. And there's some specific species that you're allowed to grow. So what they were doing is they were developing a model to count how many plants were germinating, and also identify if they were of the allowed species. So public transportation in Costa Rica is very different, I would say, than from here in Santiago. Even though we're sardines in the metro today and yesterday, it's even worse in Costa Rica because there's no metro, it's only buses, and they're very old. And you don't really know when they are coming. It's very regular, and we are still sardines. So, we have one professor in the electrical engineering department, which is actually working on AI for like ETA prediction and occupancy prediction for all these things. Then in the health science, we have some indigenous communities also, and the Faculty of Medicine is trying to reach these communities. And they have some AI-oriented projects, and they want to do this approach being very respectful of the communities. So you have to be able to communicate with them properly. So they are doing some projects for translation with their language, so they can speak, they can communicate with the indigenous communities. And they also have a project for identifying plants and their medicinal usages. So the communities are also very attached to this, so that they want to respect this and do that. Then they also have some work they were doing on the microbiology department on identifying the gut or looking at gut microbiome on monkeys. So apparently these guys are the closest to humans in the digestive system. So they were trying to identify what kind of microbiome they have in the gut and do DNA sequencing and trying to use machine learning, or they were using machine learning to identify if this microbiome in the gut was related to this disease, the duodenal stenosis, which they are. I don't know how to read that, but they are. Then, just last project I wanted to highlight, there's a professor who's also working on developing Costa Rican voice. So for children, they are starting with children, so they have some voice donation campaigns, and they are building generative models to have a voice that sounds like a Costa Rican boy or a Costa Rican girl, and they want that they want these boys to grow with the people. So they want these boys to be able to change as we change our voices when we go through puberty and everything. So this is targeting more like autistic people, autistic children who are non-verbal or things like that. So now I just want to go briefly on probably one of the projects related to AI I have at my lab. Just very briefly, I won't say probably ML, not AI. So one thing is there's no AI without chips. And so it's very important that we always keep that in mind. So there's a whole design flow for integrated circuits from where you have your specifications to when you're ready to go to the fab and actually manufacture it. And it looks very nice, it looks pretty and linear, and it's not, because every time something's broken, you have to go back, and you might have to go back several times and go back multiple steps. So it takes very long, right? It's a very iterative process, and there are some things that will break in later stages that you can only fix on earlier stages. So it's kind of a pain. So we want to do less iterations, but we need to be able to know what's broken in order to fix it. So what we're doing is, in this part of the flow, basically logic synthesis is a process that transforms code, hardware description language, into logic gates, and then placement and routing basically is what it sounds. You place the transistors somewhere in the chip, and then you connect them. And so basically, what we want, so at placement, you know where the gates are. You know they are connected somehow, but you don't really know how the wires look. You don't really know any of that. There could be a lot of gates that are very close together, and you have to do detours and everything. So the estimations of timing that you can do at pre-routing are not really accurate. And doing routing takes very long time. It's like the longest step. So what we're doing is taking this flow, and instead of doing the whole flow and then going back with resources to tell you something's wrong and you have to fix it, so what we want to do is extract data at some of the intermediate steps, feed that into a machine learning model, and then have some delay estimations, and in order to, and these two should be pretty close. So that gives feedback to the people who is designing very quickly, and you can fix things earlier. This is very fast. And these are just some results. I'm not gonna go over it, but we made two cases. So the thing is, this graph is showing error, and blue is the tool, like the placement error, and the orange and the green are the estimations. As you can see, green sometimes not that good, even worse than the tool, but orange overall pretty good. And what we did, instead of predicting how much the delay will be, is we're predicting how much do you have to add to the delay that you already know will have. So like a delta, just like a prediction, like a correction factor, and turns out that worked pretty well. So we got, now the model was better than the tool pretty much every time. So this led to pretty significant speed up of what it takes to have that feedback over 170 times. You can know that something is broken. And that's all I had. Thank you very much.
Thank you very much, Eric, and great to see how KHIPU.AI events are going everywhere. Okay, so just a comment. So now we have the practicals, and these are the rooms. Oops, sorry. I was told to announce that please don't leave garbage in the place. Try to take it with you because we found some stuff around. And so now there are gonna be, I think, are there volunteers for guiding people? Nope. Nope. Okay, so can I get the screen, please? Yes. Eh? Okay, so those that are gonna go to engineering, which is gonna be for graph neural networks and vision language model, gathered together here, and you are going to be guided by Fefo or someone. And for those, for the social cultural, is this showing up or no? Yes, okay. Why there is petard there? He's coming back, no? Okay. Here we are. So these are the rooms. Graph neural networks 202 engineering, social cultural evaluation of AI here in the economics building PC2, and vision language models K203 engineering as well. Okay, and see you tomorrow. Please be at 9 a.m. here because we are going to try to start in time. We are going to start in time. What?
Guys, sorry, because we changed the rooms because of space. The social cultural evaluation of AI would be in room PC1, not 2.
Really?
And it's on the second floor in this building, okay? The information is also in the WhatsApp group, so you can check it there.
Ay, chico, pregunto para confirmar. Quiero que me confirme.
Tranquilo.
Ya está. ¿Cómo? Yo me la robo. Yo la miraba de media abajo. Cagaba de la pobreza, ¿ves? Que no tenemos ni nada.